So this is focused on cosmic dawn in EOR. The first two talks are going to be an overview of the field and followed by a set of focus talks. Chair for this session is Madhurima. So I think we'll just get started. Take it.
Hi, good morning. First, we have our speaker, Leon, from University of Groningen.
Okay, thank
So
you.
I'll give you a warning at 5 minutes and 2 minutes.
Okay, great,
Yeah.
thanks. Well, it's a pleasure to be here, and I would like to also thank the organizers for inviting me to give this overview of basically ongoing and planned approaches to the detection. And as I said, ongoing, and no detection, of course, has been made, apart maybe from the edges signal. And this is a daunting task, so what I will do is I will give a bird's eye view of this field in the beginning. There will be more talks coming today and in the upcoming days that go into a bit more detail on some of these experiments. And then the second half, I will talk more about the research that our group is doing, which is of course also part of this of these experiments. So of course one might ask, why are all of us doing this? Why are we trying to detect a 21 centimeter at very high redshifts? It's very, very hard to detect 21 centimeter at all. Even at low redshifts, the highest redshifts might be pushing redshifts of a half or a little bit higher these days. So why go to redshift 6 or beyond? So, okay, so what can 21 centimeter cosmology tell us? Now this I think is still a beautiful image showing a slice through the universe as function of time or frequency, look back time, through the 21 centimeter signal, where you see, for example, at very high redshift, the dark ages, and as time progresses, the first stars appear, you get Lyman alpha coupling, X-ray heating, and you can see that this has an impact on the 21 centimeter signal. And of course, we end with the epoch of reionization, and then the universe is largely ionized. And this is really a treasure trove of information on astrophysics, on cosmology. And if you go to the dark ages or maybe the early cosmic dawn, it's also a treasure trove in fundamental physics. And that's really what drives us. This is the last sort of unopened window on the universe. Of course, people are now observing sources in these redshifts. But the 21 centimeter signal fills the entire volume and can measure information on very, very different scales and also very, very different information. Now, of course, it's radio astronomy, so we measure things in brightness, temperature, and you can turn this 21 centimeter signal in a brightness temperature, which, if you look at the numbers, are of order millikelvins or tens of millikelvins. And the fluctuations that you measure in this signal, that's what we're really after, or the average of this signal, depends on the density fluctuations of the baryons, of course, omega baryon, the cosmological parameters, the spin temperature, the CMB temperature, and also velocities of the field. And the whole game is to measure these brightness temperature fluctuations, or the average, and then sort of invert it to learn something about ionization, density fluctuations, velocities, spin temperature, etc. And then, of course, at one step below that, right, what sources are responsible for this. Now, the signal can generally, and of course this is a broader audience, and the people in this field have seen this and probably are sick and tired of these plots, but just to bring it home, right, the two signals is the global signal, the average of the 21 centimeter signal. You can measure it with relatively simple instruments. So that's shown here, and for example, here it's seen in absorption against the CMB, so it's of order maybe minus 200 millikelvin. This is the signal of the dark ages. And of course, it depends a lot on the physics that you put in what this signal looks like. So the X-ray heating, the Lyman alpha coupling, etc. And if you look at the fluctuations as function of redshift on particular angular scales or K-modes, you see that also here the signal can drastically change as function of the model, as function of time. So this is really the two things that current experiments and future experiments at least initially try to measure. Now, of course, we're all doing this still from the ground, and at the end of my talk, I will say a bit about the future, of course, on space-based instruments, especially if you want to go to the dark ages, you need to do that from space, preferably the backside of the moon. And the reason is that ionosphere and interference are really causing havoc. Of course, interference causes havoc everywhere, but the ionosphere is really cutting us off once you start reaching the dark ages. Or at least it's a serious problem. This is just another image from Andre Messinger showing how the signal changes as you change some of the underlying, like the heating parameters here. You can really see how the signal changes. So there is a lot of information to be gained here. So this is also a plot I always show on the various stages. Of course, you start with the dark ages at very, very high redshifts, where the spin temperature decouples, and you start seeing the signal in absorption against the CMB. And as I mentioned, you really need high redshift, you need space-based instruments to observe this. But it's really all about fundamental physics that you can learn there, because it's linear theory over there. It's like the CMB in a movie. CMB is a snapshot. The dark ages you do as function of redshift. Then you have the cosmic dawn. You get the first stars appearing, so you learn about that. You learn about baryonic bulk flows, etc. And then reionization, of course, kicks in. You get feedback. You get population 2, population 3 to population 2, transition of stars, galaxy, general galaxy formation, and the emergence of the visible universe. So let me now go quickly on what kind of experiments are trying to measure these signals. As I said, some of them you will hear more about this even today and this week, so I will not go in depth on many of these experiments. Also because I'm not part of them, so I don't have all the detailed knowledge. Now, in general, of course, we measure an image or an image cube as function of frequency of the sky that has point sources, right? Diffuse emission, unresolved point source, so confusion noise. And of course, it has noise and a 21 centimeter signal. And this looks like a noise cube. And indeed, all the experiments currently would want to measure this 21 centimeter from below the noise. It's simply not sensitive enough to measure the signal above the noise. So this sets it already very much apart from the CMB, where the initial signals are, of course, above the noise. Now you can make a Fourier transform of such a residual cube, and what you will see is that there might still be some foregrounds in there, but there are also all kinds of instrumental artifacts that sit in this two-dimensional power spectrum as function of a spatial K perpendicular and along the line of, say, K parallel. But there's also a window, an EOR window, where the signal might be relatively clean. Many experiments focus on this because it is relatively clean, but some experiments, like ours, try to remove all these effects here in the foregrounds as well, because that opens up this entire space and increases, obviously, your signal to noise. So you lose a lot of signal to noise if you just focus here, but your life is much easier here. Here, life is difficult, but your signal to noise can be much, much larger. So just to give you back the metric of how do we build such an instrument to detect this, it's all about surface brightness, sensitivity, large volumes. Because you're measuring a power spectrum, you need a lot of volume, you need a lot of modes, and you need lots of sensitivity. And that's sort of captured in the scaling relations, where you have the size of the core within which you have your receiver elements, you have your number of receivers, and you have the total collecting area. So if this is small, it means you cram everything in a very small volume, all your stations, your noise goes down. Of course, having more stations crammed in a volume, the noise goes down. More collecting area, the noise goes down. So this tells you exactly how to build an instrument, and many of the instruments that are currently in the first generation follow more or less a constant number here. So the smaller instruments, higher filling factors, larger field of view, you can, for example, compensate for a lack of collecting area. With LOFA, for example, we have a much larger number of receiver elements in collecting area, but the field of view is again small, so that those compensate. So this really drives all of the specifications, at least in terms of sensitivity. So these are the experiments that have been done or are ongoing, the top 3, as far as I know, are no longer active, but they have, of course, published results in the past. I think 21 centimeter CMA has not published the power spectrum, but it has published results. And these are the ongoing experiments, LEDA, MWA, LOFAR, HERA, SKA, and NanoFAR. So just a reminder of many of you in the overviews, you often forget NanoFAR. It's a new instrument that I will talk about that is being built in Nancy in France, specifically focusing on low frequencies and for us the cosmic dawn. So I will say something about some of these in the second half of the talk. Now just to come home with the results, where are we in this field with all of these experiments? As I said, I will not go into detail on each of them because I simply don't have that knowledge. I have the knowledge of what we are doing, of course. So this is a function of redshift. These are upper limits on the signal. These are some nominal standard astrophysical models from predictions, numerical simulations, or analytic simulations. And this is where we are. So everybody started up here years ago, and even with the same amount of data, this has gone down drastically. Also with LOFAR here, there are many others here. Unfortunately, the colors don't work out too well here. But as you can see, over time, we have gone down orders and orders of magnitude. That's not orders of magnitude more data being put in here. It's usually the same amount of data. It's just much, much better analysis, processing, RFI removal, calibration, etc. And we're not that far anymore off from some of these models, probably an order of magnitude. Now, in the cosmic dawn, this is much worse. The signal is not that much greater, maybe a little bit. But we're up here. And that is simply because the galactic foregrounds are extremely bright at high redshift and lower frequencies, more or less following that sort of diagonal here in the same integration time. So actually not that far off from the same limits in terms of thermal noise, but we're very far off from a detection there. So that's, of course, the next frontier. Most of us are focusing here at the moment and starting to sort of dabble around over there as well. Now, what about these global signals? So we're talking about this type of signal, right? These wobbles in the global spectrum, volume averaged. Now, if you ask yourself, how long does it take to measure this signal here in the cosmic dawn? It's of order a day to go down to 10 millikelvin. Of course, it's not of order a day because systematics here, right? This is a dynamic range on the foreground of maybe several thousand to several tens of thousands of Kelvin, and you want to go to maybe a 10 millikelvin RMS. So that's not easy. So, but theoretically, you can do this in a day, and if you want to go to the dark ages, it's half a year, which is not unreasonable either. So, but here, your challenges are even larger, and these kind of experiments are probably likely to be done from the moon. So this is just an overview of the various ongoing, as far as I know, ongoing active experiments. There are other ones in the past few years, but as far as I could see, they were no longer active, or some of them transformed themselves into these experiments. So, and again, this week you will hear more about this as well. So you can see the difference, right? These are just in general single dipole experiment or monopole experiments. Very simple, right? So these kind of things you can just, right? You can do your experiment and have lunch at the same time here, so in the desert. But of course, right, all jokes apart, right, such an experiment as EDGES has, of course, claimed a detection of a signal that we're all wondering about. Why is it so deep? And why is it so sort of flat and sharp? That's still an unsolved question. I think all the experiments that have been done and tests they are doing over the past years have not made this gone away. But of course, that has led to a lot of speculation. If it's real, right, we need to modify standard physics because getting such a deep signal is simply not possible in standard, with standard physics and cosmology. Of course, here in India, Saurabh has been doing an experiment together with others, of course, with SARAS-3 excluding, at least at the roughly 3 sigma level, disclaimed edges detection. So I hope to hear more about that as well in the coming days. So let me now move on to something I do know a lot about. It's our own program called CODEX, which brings together many of the experiments that we have been doing with LOFAR, and I will explain ARTFAC in a moment. ARTFAC is a part of LOFAR, but it correlates all the dipoles. So we actually get a much larger field of view and therefore more sensitivity. NANOFAR, I mentioned, the French telescope where we have a large program running to observe the cosmic dawn, and we're also starting to have experiments in space. So this is just the range of redshifts that with all these experiments we are trying to cover. We actually have an experiment in space already in L2 behind the moon on the relay satellite of Chang'e 4. I will not talk about that today. I will talk about mostly this and then some other future space-based experiments. So these are the experiments we in our group are involved in. And again, I will just talk about the ones in red. LOFAR, ARTFAC, which is LOFAR in a different mode, NANOFAR, and a new concept for a mission to the far side of the moon. So for those living under a rock for the last 15 years, this is LOFAR from space. Not the entire LOFAR, because there's baselines out to 2,000 kilometers. This is the core, but this is really the stations where we get the most sensitivity for the experiment. This is called the super terp. A terp in Netherlands means an elevated area where people in the Middle Ages and before used to live when everything was flooding all the time. So we called it a terp. But it is an artificial one, obviously, but it has been flattened to fractions of a wavelength. Everything is very flat. And there are some stations around it, and then they're extending all the way out to hundreds and even thousands of kilometers. There are two different antennae, HBA, the high band antenna, covering a different frequency and redshift range, and the low band antenna. I will focus largely, well, I will actually talk about both of them. ARTFAC uses the low band antenna, and with the standard LOFAR key project, I will be using the HBA antennas at higher frequencies. So we are covering different redshift ranges. So what observational windows are we targeting? This is an image actually created with the ARTFAC instrument. It does an all-sky instantaneous image. So we just plotted on the windows that we have focused on. With the LOFAR Reionization key project, we are focusing on the North Celestial Pole and some flanking fields, and maybe a few other fields that we have observed as well. With ARTFAC, we're doing an all-sky, well, northern sky survey. With NANOFAR, we are roughly covering this region as well here of all these circles combined, because it's lower frequencies, wider field of view. And NCLE I will not talk about, but it's a global experiment, all sky. And just to mention, we already have 3,500 hours of observations on these fields with ARTFAC 500, and with NANOFAR, we're already over 1,000. This is an old number, so we're already over 1,000 hours. So we have a lot of data on disk. So first, the LOFAR Reionization key project, of which I am the PI. So again, we focus on the North Celestial Pole. This is just a different projection on this sort of rather radio quiet area. A zoom in here, wide field. But actually, we're only really analyzing this inner little bit here, which is more or less covering a single beam of LOFAR. Now, 3,500 hours of data is many petabytes of data, so we need a really, really powerful compute system. And we recently bought a new petaflop GPU cluster, which you can see part of over here. It's now being assembled and will probably go comes in action in a couple of weeks' time. But we have an older cluster that runs in parallel as well, so we'll have two GPU clusters processing these petabytes of data that we have on disk. And we need this. We need a petaflop compute power to process all of these data with all the complications that, of course, we've discovered in the last decade. These are just the specifications. So now the data analysis is really right. If we have a new person joining the group and we show them this diagram, right, they hide under a desk for a couple of weeks and then emerge. So this is really complicated software. We've developed everything, more or less everything in-house, and many of these softwares are now being used globally as well. So they're all open source as well. So everything that we do, you can use as well. This is the current pipeline. It has had a lot of improvements since 2020 when we published our latest upper limit results, especially in the calibration and also in the foreground removal. So this is the field with the zoom in. This is a wide field image with the zoom in here. You can see how many sources are in this field. It's really puckered with point sources, but underlying there also diffuse emission. It's very hard to see in here. If you remove a sky model that we built with 30,000 sources from this field, you'll see that it cleans up, but not perfectly. But we remove that with another method, with Gaussian process regression. And this is the little box that we analyze. You can see the fall off of the primary beam of the instruments, about 4 degrees. We analyze about this area within the primary beam so that we don't deal too much with beam issues. As I said, this, if we go back here, this is not empty, so this we clean out, but the dynamic range here is much lower than here, so we can clean it out with a foreground removal technique that in particular Florent Mertens, one of my former postdocs now in Paris, has put a lot of time and effort in to decompose these signals into various 21 centimeter component, noise, foreground components, treating them as Gaussian processes. Now, if you look at all of the data that we have, we published about 10 nights of data, you look at the correlations, the residuals still show significant correlations within that wedge region. If you go a little bit outside, you see the correlations decrease. This is from 0 to 0.3. But if you're in that EOR window, you can see that the correlations are basically close to 0. That means it's basically noise. There's no leakage of foregrounds there. But in the wedge, we still have a problem, and we call this excess variance. We'll come back to in a moment. And we also know that if the observations are done close in LST, the correlations are stronger, which really tell us there's still something leaking from the sky into our residuals. These were the upper limits that we published a few years ago in 2020. These were the deepest limits then at Redshift 9. This is in millikelvin squared. The square root of that is what I showed as an upper limit in this previous image. But if you look at where one should be, this should all be of order unity. You can see there's a lot of excess variance. There is something in the data that still is partly correlated and uncorrelated, which is still significantly higher than the signal, or where we should be is the thermal noise. Now, we spent a lot of time in the last few years improving this, and I will show that in a moment. Now, of course, jointly with these upper limits, we published astrophysical interpretations. I will not go again in great detail, where we can set limits on the luminosity function, for example, already with these limits. For example, a paper here by Bradley Gregg, and I haven't updated this to the actual papers. We have set limits on the cold IGM model, so you can have different IGM models and temperatures, and some of them are already exceeding our limits. Now, of course, we want to push this down and exclude or measure some of these models. Right? That's our goal. We have also excluded very strong radio backgrounds, because radio backgrounds can increase the signal. So also here you can exclude a range of models already because they exceed our measurements. Now, what have we done? We have done a lot of improvements in our data processing. So this is, right, we have built much better sky models, right? We have also diffuse emission, which we are trying to include at the moment as well. We have done a lot on radio frequency interference, which is still causing problems. I think if I do this here, it will start playing? Yes. So this is, I will come back to this movie, but this is a view over LOFAR. You see all the RFI happening in real time here. Well, not real time, but this is a function of time. We have done near field imaging. We found this little nasty blob over here, and this turned out to be a little camera on top of a electronics cabinet. Now we thought, okay, that camera was on. No, because some beep drilled a hole in the cabinet to put the cable for the camera, and of course that was leaking RFI, which we found. So they, of course, plugged that hole. Camera had never been on it the whole time. Had a brilliant idea of drilling a hole in this Faraday cage. So we are working a lot on the effect of the ionosphere, on calibrations, both frequency and direction dependent, and on this Gaussian process regression foreground modeling. This is a very recent result, was sent to me yesterday, actually, yesterday evening. We have now also expanded our calibration regularization because you need smooth solutions. This is computation extremely expensive. That's why we need all this computing power and do it all in the distributed fashion. We can also now do that regularization, that smoothing as function of direction, which, as you can see, this is just a variance, so the brighter the colors, the higher the variance. So you see that as you change some of these regularization parameters in our model, at some point this minimizes this variance. This number is not that important, but you can see that this is what we used until now, and this is where we're probably going to go in the near future. So the variance in the gains can drop by another order of magnitude, and that will, of course, help us drastically, again, in our analysis. So this is where we are, and I just put preliminary through there in case you were taking pictures. Then you look like an idiot if you publish them, so don't. But just remember, right, the numbers here were of order sort of 10, 13, and even higher. But if you look now, this is the ratio of the noise of what you expect and what we actually measure. In very large regions, it's approaching of order 1. Or just above it. So we are doing significantly better with the same data by at least a factor of 2, exactly the same data. But we've expanded now from a single redshift to 3 redshifts. So this is what we published. Sorry? 140 hours. And again, this is very preliminary, and we'll probably soon publish this with interpretation. So I will come back to that in a moment. So we go a factor of 2 deeper with exactly the same data, but we're now analyzing 3 redshifts. So we will again update our astrophysical interpretations with this. So this is where we are, again, repeating the same plot. We are now pushing a little bit deeper, and we have only analyzed 140 hours out of the 3,500 we have, right? So, and since this runs down linear with time, with those thousands of hours, we really hope to get into this regime here. So, so that looks promising, but we need to, of course, overcome these excess variance. Oh man, I'll probably have to skip a lot. So, like all the space-based stuff, I will skip. So ARTFARC is another instrument. So this is actually another mode where we cross-correlate all the individual dipoles. So you can make an all-sky image instantaneously. It was actually built for transients. But we have sort of vamped it for a cosmic dawn experiment, mostly focusing initially on the edges signal, and actually it's narrow band because of the correlator capacity, so we can only do this tiny little region, but we should be sensitive to see fluctuations of this level. We have 500 hours of data. This is what we published a few years back in this paper here, reaching sort of the estimated noise level. And this is this RFI image over. So we are writing a paper now. We are about to publish it, how to mitigate all of this. But actually, it's not as bad as it looks because we're not really focusing on the horizon. But this tells you the RFI in the Netherlands. And this is what the ionosphere is doing. We can also measure that in real time. So we've improved a lot since 2020, again, with the pipeline building largely on the LOFAR pipeline. So again, we have made drastic advances, and with the same data, this is again this 2-dimensional power spectrum. We are doing much, much better, much cleaner. This is the ratio, so we've gained at least a factor of 3 on exactly the same data by making all of these improvements here. And this is the limit. Of course, this is at a very, very different redshift. So we hope in 500 hours to reach at least those, what I always call exotic models. Nanofar, very quickly as well, is a French instrument. Again, don't forget to mention Nanofar in your future introductions, in your things. I often see this. I'm scolding you. Right? Don't forget this. It exists. It's real. This is a picture. This is not a computer simulation here. So this is a very powerful low-frequency instrument. It has a lot of collecting area. It's probably the most powerful instrument in this frequency regime, at least below 50 megahertz until SKA, well, even when SKA comes online, because it doesn't go below 50 megahertz. We have, again, developed a whole pipeline with a student of mine and our colleagues in France. These are the images here, and one thing that I think Nichole will also hammer on, right? When you do these experiments, it's all sky. So this is an all sky image, Cas A, Cygnus A here. These are really our enemies, right? Because they leak a lot of stuff in here, but when we do our modeling and cleaning, we can see, right, we can make all those bright sources disappear. This is when we subtract our model from the sky, and this is then what we analyze with Gaussian process regression. Also here we do ground-based imaging. We found another nasty little container here which was leaking. I think it had an RFI outside without a Faraday cage, very smart. So that was put around it. And there's something still over there which we haven't identified, probably some broken cable or so. And these are, again, the very first limits that we will publish in the next few months. So again, preliminary. Now, since I have minus 1 minute on the future, I'll skip SKA. I know you all have heard of it. Let me go over this. Let me quickly show in the last minute something that we're doing from space. We are now working with ESA on a mission to go to the backside of the moon on one of their first few EL3 landers in about a decade's time. They've asked us to design an instrument on the backside of the moon. Here. Sorry, let me skip over this. We've gone through a CDF study with them in 2021. It's a 300-page report. It's already standing on the moon. Oh, no, wait a minute. This is an artist impression. This is what it will look like. It will be extremely compact, and actually we are considering using an FFT concept to do the correlation, because you can't do a standard correlation on the moon. So it will be extremely compact, all sky, cross-correlating as an FFT telescope. And again, we should be able, and the goal is to go to the dark ages. So let me summarize and conclude. Well, actually, let me stop here and let me allow you to read the conclusions. I think it is a very promising field. We have not made a detection yet. But nobody said this was easy, and in fact, if it was easy, I wouldn't be doing this, because I like these hard problems. But we are making extremely good progress in this field over the past years in everything, and as I always said, somebody has to do it, right? So give me money next time, right, if you're on the grant proposal committee, because somebody has to do it, right? And there are only a few people, hardcore people in this room, right, that dedicate their lives to making this happen, like people did in the CMB. So think about that, right? CMB also took decades to measure fluctuations. Now, on that positive note, I will stop and thank you all. Thanks. And sorry for running over time.
Thank you, Leon, for a wonderful talk. We have time for a few questions. Yeah.
Thanks, Leon. That was great. I was wondering if you could share any lessons that have come from NCLE to the next generation experiments you've planned in space.
Oh, I hope that question wouldn't come. Well, what shall I say? It's being live streamed, right? So let's say don't do this experiment as fast as we did NCLE. That was done too fast, and that has caused a lot of problems, especially with the electronics. It actually did work when we all went to China years ago. The first data came in, but after that, there were problems with the electronics, with readout and so on. It has to be done in a very particular mode, and it's still being tried, but yeah, we'll have to see if that works. But we are now busy with the Chinese for a mission on Chang'e 7 to put a much improved instrument in space as well. So I think the lesson learned is, don't do it too quickly, but it had to be done quickly because it was just going to fly and it needed to be put on there. I can tell you one story that, so when the instrument, right, was a little cube where this instrument had to fit in. So when this was fitted in by the Dutch, right, they went in there, was this hole there, and there was this cable running through. And I said, okay, I cannot put this box in there because there's cable coming through. So they ran out, right, they negotiated, they came back and they snatched the cable, tick, and then they put the box in and shot the thing into space. I'm not sure if that had to do with the problems we have now, but it's probably not a good idea to cut cables last minute. So don't do it too quickly.
In terms of lessons learned, so many of us are in this situation where we have a little bit of our massive data set, and there's great progress here, a factor of 2 over the thermal noise. You call it excess variance.
Yes,
Some of us call it systematics dominated. Or so what have you learned from that? If you go to your 3,500 hours, I presume that ratio is going to be enormous because those systematics aren't going to integrate down. What is the lessons learned for those of us designing future experiments and controlling our systematics?
Well, the strange thing is they do go down. So we've done those cross power spectra and cross coherence tests and so between different nights. And we find that, right, it's partly coherent, but partly incoherent. Actually, what I showed is the results, of course, from a few years back. It's largely more incoherent now. So the coherence part is really stuff that leaks through, and we just need to improve our sky models, and we see it improve. I'm a bit more worried about that incoherent part because that just raises the noise level. It goes down, but it takes you maybe 10 times more integration time.
So in your case, you're looking through form beams with gains that are varying that you don't get to measure, which should be integrating down. So
yeah, there could be various reasons. It could be because the UV coverage is slightly different between nights, even if it's exactly the same LSTs. All your side loads are slightly different, and they pick up, of course, different sources that causes a noise. That could be semi-random. It could be the beam. It could be the ionosphere. Right? We're investigating all of these with forward simulations at the moment where we put all of this in and want to have a controlled experiment. The problem is that the controlled experiment is almost as expensive as the experiment itself. That's why we've not been able to do this, at least at this level until now. So, I think with everything we've done so far, we are bringing this down with improving calibration and foreground model and putting better models in. So we hope to get very close to, let's say, no excess variance.
But what are the lessons learned for instrument designers? And your answer was mainly about the sky model, about what's up there and what you know about it. I'm asking about the instrument and what could be better so that you can measure a better sky model yourself.
Well, so an argument that we had for a long time is we need long baselines because long baselines allow us to better model bright sources and just remove them, and that's also what we're doing. So I think just having only short baselines is a risk because if you run against something, you don't have the information that you get from the longer baselines to actually learn about those sources and subtract them and learn about systematics. It's just much more information in a UV. Right, if you have a UV plane that is filled 10 times further out, you have, right, 100, maybe 100 times more information. So that information can be used to calibrate the system. So that I think that is one, but it's not always possible. The other one is, make your instrument as spectrally smooth as possible because we're fighting against all of these things. Your beam, preferentially, should be as smooth as possible because all these side lobes and all these nulls, they're running around all the time. We see that in our gain calibration. So we're building in beam models now that we didn't have before to then only, because we do direction-dependent calibration, then to only having to do the second order corrections, but building the beam models in immediately shoots up your computational load on the compute system. So make it as spectrally smooth as possible, as stable as possible, right? 10 years ago we thought, we'll solve everything in the software. Nah, that's why we have these big machines now solving our problems. yeah, I think those are, and don't underestimate the sky model. I mean, the calibration, we also thought 10 years ago, right? We calibrate like we always did in radio astronomy on a couple of bright sources. No, it's all direction dependent, time dependent, frequency dependent, everything dependent. So yeah, I mean, you need to build sky models that currently have 30,000 sources and is still not sufficient, right? We want to build in diffuse models and also polarized diffuse models as well. That's the next step. We have done this a few years ago, but it wasn't good enough, so we sort of stepped away from that. Yeah, it's a lot of work.
Thanks, Leon, again, for a wonderful talk.
Thank you.
Our next speaker is Anastasia.
Okay, thank you for the invitation. It's great to be here again. Last time I was here, I think in 2016, for a very nice conference, and I'm really glad I have another chance to visit and talk at this anniversary meeting. So I will be talking about existing reionization constraints, mostly, of course, focusing on my own work, so it's not as much of an overview, but I tried also to cover the other people. So after Leon, I'll skip some of my slides, but we are looking at constraining the epoch of cosmic dawn and reionization with 21 centimeter experiments. And that's the first time ever we can actually peer that far into the universe and learn about the formation of the very first stars and galaxies that reheated and reionized the universe, leading to the epoch of reionization. So I'm actually adopting some of Leon's slides as well, because they're so nice, it's a compliment. So I'll be talking about what we already know about this epoch and what we will learn in the near future, hopefully with 21 centimeter experiments, and also about the challenges. So that's kind of a big picture of what we know about the current universe. Of course, we have a map of of CMB fluctuations that we heard about yesterday in great detail. And we, thanks to this type of experiments, we know that we live in a universe that is close to lambda CDM cosmology, dominated today by dark energy and with dark matter that is very closely cold. And then closer to home, so at much lower redshifts, we have large surveys that cover large parts of the sky, going all the way to redshift around 3, and in various bands, and there are plenty of telescopes looking at galaxy formation, structure formation, large-scale structure, and statistics of galaxies on very large cosmological scales. However, as we go further and further, we don't have as much information as most of the sources drop below the sensitivity limits of telescopes become too faint and redshift to lower frequencies. So at very high redshifts, we have very few observations actually, which with some of the highest redshift galaxies going to out to 13. Of course, JWST is changing this picture very actively. But I'm not showing these results yet because I think they're still converging in their analysis. So we have these very bright galaxies at very high redshifts already showing that galaxy formation started quite early on in the possibly first 100 million years after the Big Bang. So if you extrapolate star formation in this galaxy to when it should have started, we get very early on into cosmic dawn. And we also have a handful of high redshift quasars. So at very high redshifts, out to redshift 7.5, there are just a few of them because they become very rare. But these quasars allow us to probe the epoch of reionization and constrain neutral fraction already today. So there are some limits on reionization that we have today. This black line is a model, but the rest are the observations. So the gray band shows our understanding of reionization from Planck. There are quite a big errors still because CMB photons are not so sensitive to the epoch of reionization. And there are also other limits from galaxies that emit Lam alpha, and Lam alpha photons are absorbed in neutral gas. So by counting and observing Lyman alpha forest and Lyman alpha emission from galaxies, we can also put constraints on the neutral fraction of the universe at those times. And these observations are consistent with Planck showing that the reionization culminated at around redshift 6 and started quite late at redshift around 9. So it was a very sudden transition, very abrupt kind of and sharp transition. We, of course, learned about UV luminosity of high redshift galaxies from telescopes such as HST, and of course, again, JWST is changing this picture as we speak. So from Hubble, there were very few galaxies at high redshifts that could inform us about reionization, but JWST can push this frontier far away from us, so going all the way out to redshift 20, that's what they claim. And they are working on it really actively. There is a big group at Cambridge to whom I'm talking to about this, and they are showing already very exciting results with galaxies all the way out to redshift 17, but again, these are still not confirmed, I think. However, even such a sensitive telescope as JWST is probing just the tip of the iceberg of population of galaxies at high redshifts that are bright and are above the sensitivity limit, while most of the galaxies at that time were probably fainter, and we don't see this population yet because they are too far and too faint from us. So, of course, that's the major science case, as we heard from Leon also already, for 21 centimeter cosmology, that will be sensitive to all structure at high redshifts. And we will be probing most typical population of galaxies and most typical structures that live at high redshift universe. So we already heard that there is a plenty of telescopes putting limits out there, and I personally was involved in this HERA analysis. I will leave to Josh cover most of the details and show you just some results. So this one specifically was done by a group of Andre Messinger using their models, and they put some limits on, although very weak still, on neutral fraction, constraining reionization, weakly, and the spin temperature together. So these limits will, of course, improve as telescopes such as HERA, LOFAR, NANUFAR collect more data and go down into with the sensitivity limits. So again, Leon covered some of it, and I will try to be complementary. So 21 centimeter signal, as we predicted, is very sensitive, as a sensitive probe of various astrophysical processes, not just reionization. It's a probe of the whole history of the evolution of the universe from the basically CMB decoupling once we started having neutral gas all the way to the end of reionization. And it's sensitive to effects such as star and structure formation, formation of black hole binaries that reheated the gas, formation of stars that in the first place couple the spin temperature of this 21 centimeter transition to the gas temperature, and then eventually the epoch of reionization. So actually reionization in terms of the 21 centimeter physics takes a pretty narrow parameter space, and with the signal we can go much further and explore formation of the very first galaxies and stars in the universe all the way to very high redshifts, especially if we can go to space. So I like showing this slide, especially that there are many young people in the audience, just to give them kind of an idea of what's going on. And this is an equation that basically shows the dependencies of the 21 centimeter signal on astrophysics. Of course, there is neutral fraction here because that's a probe of neutral gas. But this neutral fraction was very close to unity through the whole, most of the course of the evolution of the universe. And as I showed from observational constraints, it was dropping pretty quickly, but at the very end of this epoch of cosmic dawn and reionization. In addition to that, the signal depends on the amount of UV light that stars produce, especially in the Lyman band. because these photons couple the spin temperature to the actually temperature of the gas. So without these photons, there would be no deep absorption in the signal, and we would not have any chance to observe the signal today. So we actually, due to the formation of the first stars and the production of these Lyman photons, we have a chance to see and probe this epoch. So that's the crucial effect. And finally, the signal depends on the fraction, on the ratio between the radio background temperature that usually is assumed to be the CMB that just backlights the hydrogen clouds and goes through the hydrogen gas, and the spin temperature, which is very close to gas temperature at those epochs. So what we try to measure is this contrast between and predict this contrast between gas temperature and radio background temperature at all redshifts. And of course, there are sources that are distributed non-uniformly, creating fluctuations in these 21 centimeter maps. And as the signal is sensitive to various bands of electromagnetic radiation, every type of photons have their effective horizons, imprinting fluctuations on a variety of scales. So at the end, we get this rich map of structures that evolves with redshift and scale. And as Leon mentioned, we can do various statistical analysis of this map. So it's in fact a 3D scan of the universe. So we can contract the spatial scales and study how the signal evolves with time. And this is the global signal that Leon mentioned. But we can also study fluctuations, of course, and higher order statistics that people do. Again, adopted from Leon because it's such a nice summary. And I didn't want to forget Nenufar that Leon also covered very nicely. But I want to mention a bit more about REACH. REACH is a global signal telescope that is PI'd by Cambridge and South Africa. Stellenbosch University, it's in the process of actually being deployed in Karoo Desert, same site where Hera is. And that's one of the next generation global signal experiments that is trying to detect a broadband signal from cosmic dawn and reionization. So there is a big group of students and postdocs working on REACH, trying to build a self-consistent pipeline that accounts for both calibration, antenna design, signal, cosmological signal that we expect, and is trying to do everything together consistently. And there are people giving talks after me on, Leon covered LOFAR and Nenufar, and there will be talks on MWN, Hera, and Saras also, so I'll leave that to the speakers. So let's talk a bit more about the existing astrophysical constraints, and now I'll focus a bit more on Hera, because that's the latest I've been working on. And so far, to my knowledge, these are the best limits that were available to me, at least. So these are the best constraints we have at the moment. So I showed already that Hera is sensitive to reionization. It can constrain neutral fraction, although these limits are still very weak. But interestingly enough, it is also sensitive to the heating history of the universe. And again, using Andrea Messinger's models, the group showed that there are limits on how efficient X-ray sources can be, assuming that CMB is a background radiation. With my students and also with Rennan, we went further and we considered a different type of models where a background can be CMB plus something. So assuming these models are motivated, of course, initially by edges, but I think they are interesting in their own right. So assuming that there are any other sources that create radio background at high redshifts, they can be either astrophysical or exotic. These sources would boost radio background temperature, increasing this contrast between background and gas temperature. And so we have more chances to constrain these models. We can use them as testbed for experimental pipelines to see what experiments can do now. And we can also learn something new. So this plot shows the prior and posterior of radio background temperature on the y-axis and spin temperature on the x-axis. So gray is the prior that we had from our models. and purple is the posterior that we get after constraining these models with Hera data. So again, we consider the scenarios that were motivated initially by edges, and Leon mentioned that there are two possibilities. One is that dark matter cools down the gas, and I think Rennan will be talking about that in his talk a little bit. And the other is that the radio background is much stronger. So we are looking at these scenarios with Hera data that I'll show you now. So if we add a radio background radio sources to our model, we get much stronger bubbles around Lyman alpha coupling sources, and the power spectrum is actually enhanced, so we have more chances to constrain it. So we initially created these models to explain the edges absorption deep, and we saw that also power spectra are boosted accordingly just because there is more contrast, but there are also enhanced fluctuations from these radio sources. And again, Rennan will be talking a bit more about our latest developments with these models where we took into account fluctuations along line of sight properly. So this would boost these predictions a bit compared to what we had before. So we used a large set of these models, around a few thousands that we ran on HPC to see what Hera can actually say about this class of models. And here we see Hera data points that I think Josh will be talking more about that, so I'll leave that to him. But that's how our theory models look like compared to this data. And the black line shows our upper amplitude of models with when the CMB is the only source of radio photons. But again, if we boost that and add some radio sources, we get models that exceed Hera limits by quite a bit. So here I show a collection of power spectra versus wave numbers color-coded by the likelihood with respect to Hera data. So purple models are not ruled out, they're consistent and have consistent with Hera, and orange exceed the upper limits, so they can be ruled out. So the question is what we can learn about astrophysical processes using these models. And we worked with some of my students on that. So from Hera, you can actually constrain a combination of these astrophysical parameters that probe the intensity of radio background and the intensity of X-ray background, because that's what regulates the contrast seen in the 21 centimeter signal. So this plot shows this parameter space spanned by radio background intensity versus X-ray background intensity of the sources at redshifts 10 and above. And purple space here shows what is actually excluded by Hera. And we also see that Hera is complementary to radio surveys such as Arcade and that Jens mentioned in his talk, and LWA. So these are surveys that measure directly radio backgrounds today. So this would be directly sensitive to just radio background, ruling out sources with very strong radio emission. And also Hera is complementary to surveys that probe directly X-ray background, for example, Chandra, that has limits on how strong unresolved sources can be. So this is a preliminary plot that we are working on now, but using public Hera data. Here I show you a model that we just constructed recently, where we have actually population 3 star formation, so the very first stars, and I will be talking about that at the end of my talk, more about modeling. So that is this panel here, showing the population 3 star formation intensity, and we also have population 2, so the later generation of stars that were more metal rich, and that we see that Hera is actually slightly constraining the star formation efficiency of the stars, because that's what dominates the signal at the redshifts observed by Hera, which is around 8 here. But the main constraining power, as we saw from this plot already, right, comes from radio and X-ray processes. So we see that the probability distribution of X-ray luminosity shown in this plot is constrained by Hera, and this drop is due to our constraints from Chandra X-ray background. So we're starting to constrain the X-ray heating of population 2 stars here. And we also are sensitive to radio background intensity, because if we are too intense, that takes us above Hera data points. So here we trained actually artificial neural networks going from this set of simulations that are kind of discrete in astrophysical parameter space to a more continuous set. So these neural networks are very fast in predicting theoretical models or shapes of the signals, and can be used in MCMC or another Bayesian analysis routines to go from set of parameters to the likelihoods and constraints. So Saurabh will talk about Saras, and I just want to highlight what we did with the data set in terms of learning about astrophysics. So we looked at both Saras-2 and Saras-3 data with my student Harry Bevins at Cambridge. And we looked how Saras can constrain the parameter space of the same models that we looked at with Hera, so those that are enhanced due to radio sources at high redshifts. And I hope you can see here in blue we have a prior range of models that we checked. So it's quite deep. We went and explored the extreme scenarios that are not necessarily motivated astrophysically, but it's still interesting to see what telescopes can say about them. And then we propagated this model through a pipeline that takes into account Saras-2 and Saras-3 sensitivities, and saw what we learn about these models. So green here shows the posterior after propagating it through the Saras-2 band, and red is from Saras-3. So we see that both experiments, because they're probing different frequency ranges, so Saras-2 is more EOR experiment, looking at 6 to 12, roughly, and Saras-3 is probing redshifts of about 15 to 25, so much more into cosmic dawn. So from these posteriors, sorry, how much time? So from the these posteriors, we can see that both experiments constraining different types of signals, and Saras-3 constraints are much stronger at cosmic dawn, as we expect, because that's where the observations are made, while Saras-2 is the posteriors are dropping stronger at reionization. So these are complementary experiments, and they're probing the 4 different parts of cosmic history constraining different processes, so it's interesting to look at them together. And on the bottom, you can see this KL divergence that is a measure of information in each data set. So we see that for Saras-2, it peaks at lower redshifts where the information from this instrument is greater, and from Saras-3, it's peaking around redshift 20, so that's where we can learn the most about astrophysics from this experiment. We also did the very first synergetic attempt at putting data from an interferometer and of a global experiment together. So here we also looked at Hera and Saras-3, because that's what we had, the best limits that we had at that moment. So Harry, the same student, combined the data and derived joint astrophysical constraints using these 2 data sets. So again, looking at priors versus posteriors, yellow here, purple are priors on the power spectrum this time, and global on the bottom, and global signal on the top. And then applying each telescope separately, we see that they have different constraining power, and joint analysis shows that it benefits from both having an interferometric data and the global signal here. Of course, these limits are still very weak, so we don't learn much actually about real astrophysical sources, but we still can rule out some of the parameter space that, again, is characteristic to very strong radio sources and very low X-ray efficiency of these sources. So same physics, but new type of constraints. So because these limits are still weak, we mostly learn from Hera at the moment. So the Hera limits are strongest over the most redshift range, even though Hera constrains only redshift 8 signals. Because we use our models that are evolved through the whole cosmic history, we can explore what they imply for the high redshift universe. And so we can propagate Hera's constraints through our modeling. It's, of course, a model-dependent way, but we can learn what we know about cosmic dawn signals in that case. While Cyrus 3 information directly comes at cosmic dawn, so it pins down these models directly at redshift 20. So we learn that our information here, we don't need to extrapolate, we can interpolate between the data points. We have also very weak constraints on actually properties of star-forming galaxies, such as their star formation efficiency, shown on the bottom panel, on the left panel here, and x-axis, and the minimum mass of star-forming halos on the y. So you don't see much, not as good constraints as we have on radio and X-rays, but there are some weak limits that we start getting. So one of the first limits on cosmic dawn signals. Okay, so I want to now depart a bit from observational constraints and talk a bit more about what we put into modeling that I just showed. So we try to do our best and account for the possible effects at cosmic dawn and reionization, mainly focusing on cosmic dawn actually now. But I'll show you just some examples of what we have been doing in the last year or two, which I think it's exciting. So again, 21 centimeters sensitive to reionization, radio background, gas temperature, and star formation through Lyman alpha coupling. And I was interested actually on what we can learn about the very first stars, so population 3 stars from cosmic dawn signals as soon as we detect them, say with NuFAR or Hera. And at the moment, our knowledge is very poor. We don't have observations, so we have hints from JWST that star formation started quite early, but even numerical simulations are not converged yet. Different groups report different results. And this is a plot of possible masses of first stars, which are called population 3 stars, as it evolves with years. So it's not my plot. I adopted it also from someone. But it's very nice and shows how our knowledge slowly converges through numerical simulations. But we still, some simulations get masses of 1,000 solar mass of these very first stars, while others go below 1 solar mass. And in reality, probably there is some distribution to the first star masses, so it's called the initial mass function. And we can try to probe it with the upcoming 21 centimeter experiments. So that's what we tried to do with another student, Thomas Gacy-Jones at Cambridge. So he modeled the impact of initial mass function on 21 centimeter signal by using population 3 MESA tables for stellar evolution. So they exist in collaboration. So this evolved star from from zero metallicity clump all the way to its end of its life. And then he used the stellar atmosphere codes to understand what's the emission of the stars as a function of stellar age. And then he integrated that over stellar lifetimes and also the initial mass functions to study the impact on 21 centimeter signal. So here on the bottom plots, you can see how 21 centimeter signal depends on stellar mass through this Lyman alpha effect. So Lyman alpha coupling, we also include Lyman alpha heating and some other effects like Lyman-Warner, so coupling and Wolfshausen, so Lyman-Warner feedback on star formation by the stars. And here you see that both global signal shown on the left and power spectrum shown on the right, they are color-coded with respect to typical stellar mass. In this case, and we see that if stellar masses are below 20 or so, the signal is very sensitive to it. So we could try to extract these masses from the signal if we observe it with high precision. However, if first stars were massive, with a typical mass higher than 20, the signals saturate because the stars live very short times, and they produce very similar amount of Lyman alpha radiation throughout their lifetimes. So signals would not be able to distinguish between initial mass functions. We also looked at supernovae impact. So depending on how fast, so these first stars, especially if they're very massive, they live short lives, explode as energetic supernovae. They expel gas from mini halos, and then the gas recollapses and forms population 2 stars that are more metally rich. So how fast this gas recollapse actually can be also read off 21 centimeter signal if we are lucky. And these models show examples of global signal as a function of this typical recollapse time. So you see that if the collapse is fast, it's this magenta line. If it's slow, it's this blue line. So there is some delay and some effects that can be teased out probably. Maybe we haven't done the full study yet. We also looked with Rennan at how X-ray spectra can affect, so X-ray binaries formed from this population 3 stars and population 2 stars. They would heat up the gas, changing the gas kinetic temperature. And we found that the details of this population, for example, their spectral energy distribution, would imprint signals in the 21 centimeter signal. And by studying this heating bubbles, we can learn about actually properties of these first X-ray binaries. And we are now exploring this further with my postdoc and the student again. So we again used population synthesis codes with MESA tables for zero metallicity to calculate X-ray spectra for population 3 binaries, and depending on the initial mass function of the first population stars. Depending on the initial mass function, there would be different balance between high mass to low mass black hole binaries and this in turn would affect the total X-ray spectrum that these populations produce. So this work has been submitted and is in review. And then we can use this self-consistently to see how the signals are seen in 21 centimeter signal. And I also want to highlight that, but probably I don't have time. If you have questions, I can tell you more about that. And I'd like to stop here and thank you for attention.
Thank you for a very nice talk. We can have a few quick questions.
Thanks for the great talk. I had one question on your POP3 plots. So do you assume top-heavy IMF, or when you say typical mass of the stars, is that like the average or for those curves?
So in paper, we explore several IMFs. So we go from salpeter, which is bottom heavy with many small stars, to top heavy, and we explore how different predictions they make. This is just an illustration to show you if all stars were of these masses, what would you see? So I said typical because it's just to highlight the effect.
Great, thanks.
So, but in the paper that is already published, you can see what IMFs we used and what are the predictions that we got.
So it's very nice. So when you add these extra radio backgrounds, right, you can of course set constraints on it and marginalize overall the astrophysics, but you can also do it the other way around. So how constraining are still the astrophysical parameters if you marginalize overall the radio background, because it's can be a much wider range of signals. I mean, is that really still constraining?
Well, that's what we do here, right?
Maybe I missed it,
in these models, for example. And,
okay, that does include the radio
yes,
background.
that has this. So in published HERA work, we also did the same. It marginalizes over all possible models with a very broad range of radio backgrounds.
Okay, I missed that, yes. Okay.
Yeah, so this plot, for example, shows X-ray constraints when you marginalize over radio backgrounds as well.
Okay,
right?
okay, good, thanks.
Hi, yes, interesting. I just had a question of even you and Leon didn't mention another global experiment. I don't think you mentioned the psi-high constraints. Can they be combined, and does that actually increase the parameter space?
I have to admit I'm not aware of their latest constraints. I thought they were weaker than anything else, but maybe Saurabh can comment. As a...
Might be very weak for this constraints. I believe the last was a few kelvins, residuals. So that might not be very informing for this. Since I have the mic, I have a question. For the POP3 stars on global 21 centimeter signals, how unique is that signature compared to, say, late onset of star formation, for example?
Late stuff?
Late onset of star formation. Basically, how unique is
Yeah.
that signature?
We still need to do a proper Bayesian inference. We haven't done that yet. It's mostly degenerate, so but there is some degree of non-degeneracy that I haven't quantified yet.
Hi, our next speaker is Josh Dillon from UC Berkeley. So, welcome. So, we'll start the talk now.
Great. So first off, thank you so much to Saurabh and the other organizers for having me. I'm sorry I couldn't be there in person. And I also wanted to thank Anastasia and Leon for giving a really great introduction. I think you'll see some duplicates in the first few slides here before I start getting into some of the specifics. So I'm going to be talking about some recent progress, which was alluded to by both Leon and Anastasia, but with HERA, the Hydrogen Epoch of Reionization Array. And before that, I just wanted to give a little bit more background for folks who are not super familiar with 21 centimeter cosmology. So one of the main goals of 21 centimeter cosmology is to try to understand the cosmic dawn, which we think is a process that looks something like this, where the first stars and galaxies and black holes are eventually heating and reionizing the intergalactic medium. And in particular, we're interested in using the 21 centimeter brightness temperature as a probe of this process. So the 21 centimeter brightness temperature depends on, most importantly, three key factors. The first is the overdensity of hydrogen in the universe, which traces dark matter, for example. The spin temperature of the hydrogen, which tells us about the relative population in the spin triplet and singlet states, which affects the emission or absorption of that 21 centimeter line from neutral hydrogen. And then, of course, the neutral fraction itself matters, because if the hydrogen in the IgM is ionized, there is no 21 centimeter signal to see. So interestingly, when we think about those different parts of the 21 centimeter signal, roughly speaking, they're corresponding to different phases of the evolution of the universe during this period we call the cosmic dawn. The density in particular is most interesting during the dark ages, when we're mostly just seeing matter collapsing under its own self-gravity, driven by dark matter fluctuations. The spin temperature is primarily driven, at least where it's most important, by the first stars and the first black holes before it probably eventually saturates. And then finally, the epoch of reionization, which is this key science question facing a number of different experiments and instruments across all of astronomy, really, or much of astronomy, is the thing that is, of course, driving the neutral fraction, or equivalently the ionization of that hydrogen. So there's a lot of open astrophysical questions that we're interested in. We, as Anastasia alluded to, we don't know that much about what the first stars looked like and how they formed or how they died, whether they were the progenitors of the black holes that we're starting to see with LIGO, or the seeds of the supermassive black holes, which appear to have begun to grow and appear quite early. We also don't know that much about the thermal history of the intergalactic medium, as has been alluded to with questions about edges and Saras. If there's something interesting going on, or new physics at play, or new radio backgrounds, these things might be more visible through the thermal history of the intergalactic medium. And finally, we don't actually know which galaxies or some other process was actually responsible for the ionization of the universe. We haven't directly observed enough galaxies going far enough back to have reionized the universe. So if we want to understand the 21 centimeter signal, as Leon was showing, there are two primary statistical probes. Here I'm showing 21 centimeter signal, sort of a slice through the universe as a function of time or redshift, as it gets hotter and colder, and we also see fluctuations. And so we can look at both the global signal, which is that sky averaged quantity, or we can look at the power spectrum, which is the amplitude of fluctuations on different spatial scales, both of which we expect to evolve in time. So I won't say much about the global signal. I just wanted to mention that there's this ongoing tension between the reported edges detection at redshift 17 and the Saras non-detection, which is at least 2 sigma inconsistent with that at at the maximum likelihood value that that Edge has reported. So hopefully we'll hear more from Saurabh in a few minutes about this. But I wanted to focus more on the power spectrum. So that's the measure of fluctuations, because I think that's a somewhat easier thing to go after, despite needing much larger telescopes to do it. And so a large array of arrays, so to speak, of telescopes really got us started in this game. And these things look quite different, and they employed very different strategies. And I'm, of course, not showing every interferometer that there ever was, but highlighting a few that were really focused on the epoch of reionization. And until last year, this was the kind of state of the field. So here I'm showing the power spectrum on this axis versus K, or Fourier wave number, as a function of different rough redshift bins. So we expect to see some evolution in the signal, as I said, as a function of redshift and as a function of K. And what we're seeing across the board here are upper limits from all these different experiments. But if you take some information we have about how reionization proceeded and what we think galaxies were probably doing during this period, and you sort of create a prior that's informed by other instruments and other probes, there's a wide range of possible values. Here I'm showing the sort of 95% credible interval on that posterior, subsequently constrained by other probes. And there's a huge range of possible values that the 21 centimeter signal can have, and yet most of these are not really impinging very much on those values. They're not really constraining the possible range of models that might explain the 21 centimeter signal. So what we do is what we always do in astronomy, is we went bigger. So we built this telescope, as I'll show you here, in the Karoo Desert in South Africa, which is one of the more radio quiet sites in the world, and also home of the Meerkat and eventually SKA Mid. And this is our giant hexagon in the desert, which we call Hera. So Hera is a hydrogen epoch of reionization array, and I should mention it's led here at UC Berkeley, but it's a collaboration of institutions across North America, Europe, and South Africa. And I should say that we're very grateful for the funding that we've gotten from both the Gordon Benny Moore Foundation and the National Science Foundation here in the U.S., who have really enabled this thing and made it possible. So Hera is enormous. It's substantially more collecting area than any of the other competing telescopes, in part because we're trying to measure this very, very faint signal, and having a lot of collecting area makes that easier. So Hera is made up of 350 14-meter dishes, and here's one me for scale, but it's also made of relatively cheap materials. It's PVC pipe, it's wire mesh, it's telephone poles, in order to build these giant dishes. And because we're observing at something like 2-meter wavelengths, chicken wire mesh is a mirror. So we're able to build a lot of collecting area relatively cheaply, and what is complicated or expensive about this is the computer backend and the analysis that we have to do to actually make it work. And because Hera is a somewhat simple physical instrument, in the sense that it all it does is really just look straight up. So we're sitting at about minus 30 degrees of latitude, so we can just see minus 30 degrees declination, which is plus or minus 5, because our sort of field of view is about 10 degrees. So what we're mapping out really is a stripe across the sky that includes the galactic center here. But because we're doing cosmology, it doesn't matter that we can't see the whole sky. All we're trying to do is a statistical measurement of this 21 centimeter signal. We're not yet at the point where we might map out a huge fraction of the volume of the universe, which is the ultimate goal with 21 centimeter cosmology. So between the hydrogen in the early universe and us, of course, is all of this other stuff, our galaxy, other galaxies, and all of it is, as Leon was talking about, much, much brighter than the 21 centimeter signal we're looking for, something like 4 to 5 orders of magnitude brighter. And so the only hope we have really of separating the two is by using the fact that while the foregrounds are very, very spectrally smooth, at least intrinsically, because they are generated by processes like synchrotron and free emission, the 21 centimeter signal, because each frequency maps to a different redshift, maps to a different part of the universe that are quite separated, we're talking about things that have a lot of spectral structure. And so fundamentally, it's about that spectral axis where we can hope to separate these two things, despite the fact that we have to achieve this sort of 10 to the 4, 10 to the 5, 1 part in 10 to the 5 level dynamic range in order to be able to detect the 21 centimeter signal. So the design of Hera, and I won't go too much into depth here, though I could talk your ears off about this question. Our design was quite different from some of the other telescopes that I mentioned earlier. And in particular, we were really focused on a very compact array, which focuses the sensitivity generates as much sensitivity as possible by measuring the same modes over and over and over, and also trying to minimize spurious spectral structure that will take, if you multiply that 100,000 times stronger foregrounds by something that has spectral structure due to, say, calibration or issues or reflections or things like that, those kinds of effects can wipe out the modes where you're trying to make your measurement. In particular, Hera was designed to use this technique called redundant baseline calibration, where because interferometers are measuring visibilities, which involve pairs of antennas, and which depend only on the displacement of the difference between their positions rather than their absolute position, when we're talking about a relatively small array, the fact that these two this pair of antenna and this pair of antenna are measuring the same thing, and likewise these two pairs in green, that gives us a set of repeated measurements, and we can use that internal consistency to try to calibrate out some of the nuisance parameters, particularly these complex gains, which themselves are frequency dependent, potentially in a quite complex way. So we need to make sure that we build an instrument that is both as calibratable as possible, and also trying to make that calibration challenge as easy as possible with a relatively simple instrument, though, of course, no instrument is truly simple. So I could be happy to answer more questions about that, but I think I wanted to focus more on the results and the future outlook here, because I think that's more interesting for the broader community. So before Hera, this was where we were, as I just showed earlier, and with just 18 nights of data, with just 40 of the eventual 350 antennas, we published our first upper limits, which were the world-leading upper limits on the 21 centimeter power spectrum. And as Anastasia was talking about, we went through this exercise of actually starting to do parameter inference. So this is showing the results from one of the 4 models that we looked at in our first parameter inference paper, where we specifically 21 CMMC, so that's showing derived constraints on the power spectrum from that. And what we can see is that these upper limits are starting to bring down the range of possible models consistent with what we've measured. So I'm showing here again the 95% posterior range given our priors, given other probes like the cosmic microwave background, which gives us this interval constraint on the total number of electrons between us and the CMB. We are able to make a significant improvement in the range of possible models. But of course, this was not just one. I'm really skipping over a lot here in the sense that not only did we have these limits and their astrophysical interpretation, but there was a whole suite of supporting papers, which I don't really have time to go into too much right now. But these were laying the backbone for the Hera analysis and showing, for example, and I'll just mention specifically, end-to-end validation, where we really simulated faithfully as faithfully as we could all the systematics that we knew about, push that through with a known power spectrum value, and show that with the analysis pipeline exactly as we applied it, we got back out what we put in. When we can measure the sort of low-level biases and the potential for percent-level signal loss, the worry being that if you do some analysis to mitigate foregrounds and you don't mitigate, and that ends up erasing some of the cosmological signal, that's something you need to quantify precisely. But of course, we didn't stop there. So from that same season of observation, we had not just 18 nights of data, which was sort of the first deep dive that we did, but actually 94 nights of data spanning a much larger range of LSTs, or equivalently right ascensions, and we had much greater depth on the right ascensions we had already observed, plus more that we hadn't from that set of 18 nights. So we go through the same exercise we did before, where we pick the 2 bands where we had sort of the minimal RFI contamination that we think were probably overflagging, and excising RFI that was not actually there, so it's possible to maybe do a little bit better. And we broke that Hera stripe into 5 different fields where we'd independently measure the power spectrum, and then finally only combine them when we're talking about constraining likelihood. So there are 5 independent measurements of the power spectrum at different LSTs, so that we would be able to make sure that if there are systematics, for example, from Fornax A, that's our enemy. Thankfully, Cas A, Cygnus A are not visible from the south, or at least not particularly easily from Hera. If there are systematics that are specific to particular foregrounds or the fact that the galactic center goes through our field, those are the things we want to avoid, and we want to break up the set of LSTs that we observe so that we can minimize that effect. And so we go through, again, that same exercise where we set power spectrum upper limits. Here I'm showing the noise curve that we, sort of the 1 sigma noise, and then these in pink are all 2 sigma upper limits as a function of the particular field and the particular band. And in particular, I'll just highlight that we set our single best upper limit here at Redshift 7.9 at 457 millikelvin squared, which is a more than a factor of 2 improvement from what Hera had done before, and a considerable, and again, a world-leading limit by quite a margin. So, to remind you, here's where we were before with the Hera results, with just 18 nights and the inference we were doing, and now we're putting yet lower upper limits as we continue to march down and make progress in this field, setting upper limits at both Redshift 7.9 and 10.4. And when we went through the same exercise of trying to do astrophysical inference with this, using the same set of codes we'd used before, something actually pretty exciting happened. And the power spectrum limits, sort of the range of likely power spectrum values, again, this is our 68 and 95% posterior interval, or posterior credible interval, actually came down a lot more than we expected. There were substantial improvements where there's large sections of parameter space that now appear largely ruled out. And the reason for this is because both of these limits, especially the improvement at 10.4, which is actually bigger than the improvement at Redshift 7.9, talk to each other. They both go into the same likelihood, and they're both constraining the same underlying combination of parameters. And what we've shown is that the intergalactic medium was heated, likely by X-rays, but it was heated above the temperature it would have had it just been cooling adiabatically since recombination, both at Redshift 7.9, which is what we had shown before, but it was also clearly heated above adiabatic, so that's this cross-hatched area where that would be the adiabatic cooling limit. It was heated above that at very high confidence, or excluded by, if we wanted to be proper Bayesians, it's way outside of our 95% credible interval, at both Redshift 10.4 and 7.9. And this then has a pretty big impact on the power spectrum because of this term here that I showed before, where one of the ways, assuming that the radio background is the CMB, and Anastasia and her group have explored possibilities where that's not the case, but assuming that the radio background is the CMB, then the only way to make the 21 centimeter temperature very bright, and therefore the power spectrum very bright, is to have a very low spin temperature. And as soon as this spin temperature is large, this term just saturates to 1. Whereas if it were very small relative to TCMB, or somewhat small, this term could actually be quite large and negative, and that would make the power spectrum quite large, and therefore something we would have observed. And one of the interesting consequences of that, and this is specifically in the context of the 21cm fast-based inference technique, 21cm MC, was that if the intergalactic medium was heated by high-mass X-ray binaries, which is the sort of leading theory for how the intergalactic medium was heated, in particular by soft X-rays from these binaries, we think, therefore, that this gives us a constraint on the X-ray efficiency, the soft X-ray efficiency per unit star formation. So the idea is that we're saying that these high-mass X-ray binaries must have been more efficient than those that we observe in the local universe. We've ruled out the local relation, and what we're seeing is much more consistent with the relation we see or we predict from low metallicity high-mass X-ray binaries. Now, we're talking about Redshift 10.4 and above, so I don't think it's surprising that we're seeing low metallicity, but we're now seeing a very consistent picture and some direct or somewhat direct evidence that that this heating, if it was X-ray binaries, should have been driven by specifically evolved low metallicity stars. So I was mostly talking about results from 21cm-MC, but we actually looked at 4 different models, including the radio background model that Anastasia talked about a little bit. And while they have different ways of being interpreted, one way in which we can sort of plot them all on the same axes is by looking at the spin temperature divided by the radio background temperature, whether that's a CMB or something more exotic. And they all agree that they're inconsistent with adiabatic cooling. They all require some amount of X-ray heating at both Redshift 7.9 and also Redshift 10.4. What we're not able to say much about quite yet is the sort of ongoing tension between Saros and edges. In particular, one could construct a model that is sort of nominally consistent with both of them and also completely consistent with Hera, and invoking sort of exotic null-charged dark matter as an explanation for why the spin temperature was so cold at Redshift 17. So it'll with the data we have now, which only allowed us to go out to less than Redshift 12, we can't say that much about it. But that hopefully will change soon. So what's next for Hera? Well, one thing that I am particularly excited about on the analysis side is that there's another technique which we've been developing, and this has been led by a graduate student here at Berkeley, which is to use not just redundancy to calibrate the array in the way we normally think about it, where we have different pairs of antennas measuring the same mode. Here I'm showing the phase of our visibilities. If you have that same separation, you should see the same phase as a function of frequency. But also, there's spectral redundancy, where different pairs of antennas that have the same orientation but different lengths, if you instead of plotting it as a function of frequency, but instead as a function of Fourier mode, which is basically tells you about the baseline times the frequency, there's actually a quite considerable agreement. These things really start lining up, which is to say that they're seeing the same sky, and the sky evolves very smoothly. So in phase, they're kind of measuring the same thing. Now, it's not quite exactly the same thing. It's not as precise of a redundancy as before, but there is a kind of redundancy that we think we can exploit. So if you think now about not just two different baselines with the same orientation, but all the different baselines with the same orientation, which is something you can do because of Hera's very regular grid, what we're seeing is that, and here I'm plotting the actual data, where the color is the phase, you're seeing those phases line up over many different baselines, all at the same Fourier mode, but at different frequencies. And so what Tyler Cox, who's the graduate student at Berkeley that I mentioned, has been working on is how do we model this with a relatively smooth model of the underlying signal so that we can actually fit with fewer parameters than we have measurements, and to start to actually say something deep underlying about what the foregrounds are really doing, using their intrinsic smoothness, despite the fact that we have actually measuring things in terms
You
of
have
Fourier, but
2 more minutes.
in terms of a long line frequency. 5 minutes?
2 more minutes, actually.
2 more minutes. Okay.
Yeah.
So what's exciting about that is that this is actually, with just a little bit of data, really seems to model the measurement that we have down to the noise level. And I think, and this is really speculative, I'm not sure that Hera is going to be the instrument that will really do this, but this might be the technique that would allow us to work within the wedge. And this is simulated data with no problems with the instrument itself, but this is some really interesting preliminary work. So I'll also mention, as the status of the array, that we're observing now with over 200 antennas as we build out to the full 350 and commission that. And everything is new, including the feeds, which will give us a much wider range of frequencies, from 50 to 250 megahertz, which allow us in principle to go out to something like Redshift 7.29, though we won't have much sensitivity there, of course. And with that full sensitivity and the full array, we should really have plenty of sensitivity to detect different models of reionization and how that affects the 21 centimeter power spectrum, but also what's going on during the epoch of X-ray heating, or whether there's something more exotic going on. If edges is right, it should be blindingly obvious in the 21 centimeter power spectrum. We should see it. Regardless, by having a high signal-to-noise detection of the 21 centimeter power spectrum during the epoch of reionization, we should be able to really precisely constrain the ionization history of the universe way better than what's available with the current set of probes, which, when you combine that with the cosmic microwave background, becomes really exciting. So that basically eliminates the degeneracy that the CMB has between A sub s, or equivalently sigma 8, and tau, the optical depth to reionization, And this is particularly exciting with CMBS4 because this might enable, by combining Hera and CMBS4, a detection of a non-zero detection of the sum of neutrino masses, which would help us determine their hierarchy. So this, I think, will be one of Hera's first major contributions to fundamental physics. Of course, there's more to do than just the epoch of reionization. There's a lot of interesting astrophysics as we push toward the first X-ray sources and the first stars. And we've done some preliminary work showing how you can constrain all these models altogether with the kind of Hera data that we expect. And I won't go too much into this particular chart. And also, as mentioned, that there's some exciting potential with at least a few years of Hera data of measuring velocity acoustic oscillations, which would give us a new standard ruler at Redshift 16, which is kind of an interesting intermediate place between, a high redshift, we're talking about the CMB, and Redshift 1 or so, where the supernovae seem to be in tension about what the Hubble constant is. If we do get a new standard ruler, that might say something about the current Hubble tension. So, to sum up, since I think I'm out of time here, I'll just say that with the full season of what we call Hera Phase 1, very conservative analysis techniques that are throwing away a lot of our sensitivity in order to be robust to systematics, we've set this world-leading upper limit on the 21 centimeter power spectrum. Our results require that the IGM was heated above that adiabatic cooling limit, at least by Redshift 10.4, if not earlier. And this basically rules out a set of models that we think of as cold reionization, which would have given us a very high amplitude power spectrum. So because we don't see it, we can rule those out. And instead, what we believe we're seeing is X-ray heating of the intergalactic medium, likely driven by evolved low metallicity stellar binaries or high mass X-ray binaries. But with the full array and the wider bandwidth, we should really have plenty of sensitivity to detect and characterize the 21 centimeter signal from both the EOR and the preceding cosmic dawn with the kind of data that's really coming down the pipe right now. So with that, thank you so much.
Thank you for a nice talk. We have time for a few quick questions.
Well, since no one else is asking questions, can I ask a naive one? You said the synchrotron background is assumed to be smooth, and that is the strategy behind your subtracting it out. But it was clear in Leon's map, the one from LOFAR, you can see the galactic loops. These are nearby old supernova remnants. They have been known since the 70s. Actually, they were found at Groningen by Eli Berkwitzen. Now, those are clearly structures. They are localized, and it's not clear to me that they would be capable of being approximated as a smooth background as you assume for the subtraction strategy. Do you have any comment on that?
It's a good question. So I may have equivocated a little bit here, but I want to be clear that by smooth, I mean spectrally.
Yes,
for us, the main axis of trying to remove these things is by looking at their spectrum.
No, I
so
understand,
they may have a complicated spatial
that, but
structure.
even spectrally, these are regions of compressed, cosmic ray electrons and magnetic field. Their spectra are typically flatter than that of the surrounding regions. They are not the same spectrum. So you
they don't have to be. They don't have to be the same. All they have to be is smooth, and you can take basically any power law, and you can add together a bunch of power laws. You still get a smooth thing. The key is that if you look at it, say in Fourier space, that it needs to be a relatively smooth continuum. It can vary from place to place on the sky. The key is that it has to be smooth.
I understand. I think that needs to be data driven, not assumed.
With some small exceptions, like radio recombination lines, where we know the frequency, all of our measurements across all these different experiments have not demonstrated that there is a fundamental unsmoothness. And we think we understand the physics of synchrotron radiation.
I'll just comment on that a bit. So we've done some work here along the same lines, more for the global signal. And we've taken the current then up-to-date measurements of the sky maps across the sky with some spatial resolution. And if your beam is wide enough and you don't introduce chromaticity from your beam, there is good reason to believe that when you sum over various power laws in these bands, so not several octaves, but at least a couple of octaves, and you average them over the beam, even if you have some spectral structure in terms of different slopes and amplitudes, there is good reason to believe that they average out into something like a power law, but not quite a power law, but it's still smooth to the current, I guess, simulation/measurement abilities we have reached. But the challenge is, again, beam introduced chromaticity and other chromaticity from the instrument. But from current limits on these spectral all-sky maps that we have used, there is reason to believe that 2 millikelvins, they can be smooth spectrally as well, including these structures on the sky. Yeah, but I had a question. Yeah.
I elided over that point, but I think it's a good thing that you mentioned the beam, because the beam sky product, which is really what you're measuring, not just the sky itself, can have more spectral structure. And so Hera's dishes were designed in part to try to avoid some of that, to limit the sort of the highest delay of sort of internal reflections inside of the dish. And there was a number of papers led by a number of my collaborators on that particular point. But we were trying to minimize the spectral response of the instrument as well as we can.
Is there time for a question? Okay, I have a question. So along the same lines, since you brought up a lot of the work that has been done on the beams, I know you've thought a lot about it, but can you say a bit more about mutual coupling effects from having antennas so close by and so on?
Yeah, so this is an area of active research, and there's definitely some concern that you effectively get visibility leaking into one another. And this is particularly worrisome when you're talking about long baselines, which have more intrinsic spectral structure, effectively leaking into the shorter ones. So there was one paper doing some simulations about this by Alex Josiadis. There's another paper which has been in a little bit of limbo, but hopefully will be coming out soon, that showing that some of these effects do appear in our real data, and it seems to be a little bit worse with Hera Phase 2, that these new Vivaldi feeds sort of see each other more than our old dipole feeds. But we think we have a strategy for mitigating this based on the fringe rate structure. So fringe rate is the Fourier transform of time, which is a fancy radio interferometry term, but it basically means how is the signal changing in time, how the foreground changes in time, and we think we have a handle on that just based on the particular baseline orientation and how the fringe pattern, or the constructive and destructive interference, changes, as the sky moves through that fringe pattern. And so we think that what we'll need to do is a more aggressive filtering to basically throw out all modes inconsistent with those on the sky, or perhaps even those in the main part of the beam. And this will incur some signal loss, and that's something we'll have to quantify. But we're talking about order 10%. But with those kinds of techniques, we should be able to, the mutual coupling will introduce signals that are inconsistent with just coming directly from the sky. And so those kinds of filtering techniques, of course, need to be propagated through, and we need to understand fully all the power spectrum statistics, because this introduces complicated correlations. But I think that's likely the way forward for data with the Hera Phase 2 and eventually with the full array.
We have one quick question, last question.
Okay, thanks, Josh, for a great talk. I was wondering about the time you use. So you have 96 nights, that must be up to 1,000 hours. But the difference with the 18 nights is that's a factor of 5, but you only have a factor 2 improvement in the delta squared. So there's some efficiency factor there. That how many hours are you effectively observing?
I'm not sure that it's right to think about it as effective number of hours. So there's a few things that have, you're absolutely right that if you just multiply that amount of time by 5, you should have a power spectrum upper limit come down by 5. There's a few effects that made that not work quite as well. The first is that we are observing over a much larger range of LSTs, and so you don't get to coherently integrate over them. So, we're seeing more like a factor of 3 to 4 at the sort of best observed set of times, rather than a factor of 5, and we're not getting that much extra constraint over here and over here. It's adding a little bit, but most of our information comes from just going up like this. So that there's a question of what you can incoherently versus coherently integrate. Another thing which I elided over in the interest of time was that we are doing a slightly a slightly more aggressive cut based on residual mutual coupling that we weren't able to remove using the same set of data analyses that we applied to that 18 nights. I think there is some space to try to do a reanalysis where we could bring back some data. The thing that hurt us the most actually was removing the shortest. The first analysis had already removed 2/3 of the 14-meter baselines, the shortest pairs. We had to end up removing the last one, the 14-meter east-west baseline. And so that was our most sensitive baseline, and we had to remove it because of excess systematics. I think it could probably be brought back with better analysis, but the idea here was to try to apply precisely the analysis we had done before and had really deeply validated. So I'm not sure that this is the last word on this data set, but also we've got so much more data that we want to look at as well that, it's hard to be motivated to go back and look at the old data when there's all this brand new shiny data to look at.
Thank you. But we'll have one last quick question before we say bye.
Great.
A lot of last questions.
Yeah, the last question. Thank you. Josh, from all of this work and the great improvements shown here, what advice do you have for future instrument designers? The same question I asked Leon. What would you change in the future if you could do this again? Hardware.
More as a broad lesson, I think we need to co-design our instruments and our analyses. So we should be building our instruments in a way where we say, this is how we think we want to analyze the data, and we can actually show with realistic simulations that the analysis technique we're doing is sufficient for what we're seeing. I think in particular, a thing that my personal vision of the long-term future of this field is we probably want simpler, smaller elements, maybe fixed dishes that are actually more redundant with one another, that are really measuring the same thing. Hera's dishes are floppy, to put it lightly, and there are substantial differences, and when you have to suspend the feed from the prime focus, there can be the feed positioning errors can have a relatively big effect. I think those kinds of things will prevent us from really successfully working within the wedge and gaining back that sensitivity. So I think an array needs to be very precisely as designed and truly understood, and I think redundancy helps a lot for that. But building something out of smaller fixed dishes, for example, like the kinds of dishes that are being used for Hyrax and Cord, as an example, I think are an exciting possible way forward. There's always cost trade-offs here, and as you go to smaller dishes to get the same collecting area, you need a lot more elements, which is why continued work on the sort of fast Fourier transform telescope techniques, I think, is particularly exciting and likely the long-term future for large ground-based experiments. And perhaps space-based as well. I like that FFT from the moon. That was pretty cool.
Thank you, Josh, for answering all the questions and for a very nice talk. We thank the speaker once again. So, So our next speaker is Nichole Barry.
Yeah, so thank you for inviting me to the conference. It's been really great. And I think it's really important to bring people from distinct yet somewhat related cosmology fields together. So these languages, these things that we were learning can actually cross-pollinate. And today I want to dive a little bit more deep into the Epoch of Reionization and some of the things that are problematic. In particular, I want to have a good whinge about wide field and why it's really difficult to get wide field observations correct, especially for Epoch of Reionization science. So I'll be showing only one type of plot today. It's a power spectra. It's a 1D power spectra. And these are the two separate things we expect to see in the power spectra for the 21 centimeter signal. We expect to see foregrounds. The foregrounds are typically spectrally smooth, though not always. And they are spread out to a variety of K modes due to the chromatic response of the instrument itself. It's inherent to the instrument. But there's plenty of other K modes in which to look for the Epoch of Reionization signal. And so colloquially, as you have heard, we call this stuff towards the left the foreground wedge, and the stuff towards the right the EOR window. And there's two separate analysis strategies. One is to go into the foreground wedge and try to get the best signal to noise that you can on the epoch of reionization in there. And then the other strategy is to go, let's just go look for where it's simpler, and that's in the EOR window. So that's what I'll be concentrating on today. So that's what we expect to see, right? This is idealized. What you actually see is something like this. So if you accidentally introduce spectral errors into your analysis, you can actually spread out those really bright foregrounds into all of these spectral modes, all of the K modes, in which case you can't measure the epoch of reionization at all. And these errors that I'm showing here in this little simulation are calibration errors. And this calibration was a very typical radio astronomy calibration scheme. It didn't work, obviously. So this has kind of spurred a whole array of different strategies to try to avoid these spectral signals, these spectral errors. One way to do it is to build an instrument that doesn't have any drastic spectral differences, so that you can just fit a polynomial and call it good. That's idealized, obviously. But just to head off Matt Dobbs' question, just build something spectrally smooth. There you go.
No, but you know it's spectral, since what you're saying is impossible.
Yeah, I know. This is me at the Murchison Wide Field Array, so this talk is going to be a little bit focused on the Murchison Wide Field Array, the MWA. However, the lessons learned apply to all wide field instruments. This is me in the Outback, playing with some of these dipoles and playing with the receiver boxes as well. It's an extremely simple instrument, these radio interferometers. It's a set of dipoles attached to an LNA board, essentially. And they cost about $100 each, so they're really simple, pretty cheap. But the power comes in having many of them. So this is just a drone footage of the MWA to kind of give you an idea of how it looks. The Outback is really flat. There's not a lot going on there. And we've spread out these dipoles over an area of roughly 3 kilometers. And it's an observatory. So the main difference between LOFAR and the MWA and HERA as being distinct is that LOFAR and NWA are observatories. They're meant to see other things. They're meant to make images. HERA is really deep diving into the epoch of reionization signal, and so they built these redundant baselines. But you can't make a good image out of it. So it's really specialized science. And just to give some context for the question that I want to ask, this is what an interferometer measures. It measures a visibility. And a visibility is the beam response, so what the elements actually measure on the sky, their sensitivity, times the thing that you're trying to measure, the sky intensity of the thing that you're pointed at, and a geometric phase term, or a sampled mode dependent on the distance between the antennas or the baseline. And this visibility is the mutual coherence function, and if the thing that you're trying to measure is infinitely distant away, you can reconstruct the image that you get of the thing on the sky by taking the Fourier transform of your visibilities. That's great. You can tell that this isn't quite a Fourier transform, especially if the A term is complicated, and in which case this isn't just quite as simple as taking a Fourier transform. So in traditional radio astronomy techniques, you generally just avoid the A term. You say it's 1 or something, and just kind of move on with your life. But for a wide field radio interferometer, the A term is not simple at all. So this is the question that we want to ask. We want to ask, how accurate does that A term, the beam sensitivity, need to be? And this breaks down into actually 2 separate questions. It breaks down into how accurate does A need to be when you are combining visibilities together, or what we call gridding. Or, in addition, how accurate does A need to be when you're generating models, essentially doing the reverse of the gridding process, doing degridding? So this is what that A term looks like. If you laid flat on your back and looked up, this is what the instrument would see. You can see that there's a primary lobe. This is where most of your sensitivity is. And then you have these side lobes. And these side lobes exist purely because your dipoles aren't perfect. There never will be. But this is actually a really simple side lobe structure. And this circular edge here is the horizon. Now, this is something that an engineer gave to me. They ran a FECO simulation with a bunch of parameters and stuff in it, and they gave it to me, and they're like, this is your beam. Great, cool, thank you. I actually need the beam in UV space, because the visibilities are measurements in UV space. The visibilities are Fourier space, so I need that A term in Fourier space. And if you take the Fourier transform of the thing that engineers gave me, you can see it's actually quite ripply and gross. These ripples are inherent to the fact that you have side lobes. These side lobes are essentially a two-slit experiment. And when you do a Fourier transform, you'll get ripples. So it's really hard to get something accurate when it has a lot of ripples and it's really extended. So what I really wanted to test was I wanted to build a simulation where I input a known analytic beam. This isn't an analytic beam, obviously. This is very discrete. And so I decided I will do my best to make it analytic. I will decompose it into a series of Gaussians, which get Fourier transform of a Gaussian is a Gaussian. Cool. So this is my Gaussian decomposition of the beam image. Those with astute eyes should see I'm missing something. The horizon. The horizon is not a part of this Gaussian decomposition beam. I'll include it later, but I would be remiss if I didn't mention that this is very similar to the taper gridded estimator, at least in its theory, in its basis. So we'll hear a lot about the taper gridded estimator, I think later today and tomorrow. I think we'll hear about it a couple of times. Essentially, what it boils down to is you'd like to suppress your side lobes. And when you suppress your side lobes, you make things smoother. This is essentially keeping the side lobes, but making them smooth anyways. So they're related in their theory. So this is what a total observation would look like from the MWA. You have your visibilities here at different baseline lengths, and they have kind of a kernel to them. They have they're extended in this UV space based on the A term that you've calculated. And they overlap in various regions, right? And so this gives you an opportunity to calculate the maximum likelihood if you actually propagate the errors, given that you know what the A term is. You can calculate what your sensitivity is at each and every pixel. And these propagated errors are great because then you don't have to bootstrap your errors later in order to create a noise curve. So this is kind of the basis for why we want to get this A term right in UV space. Hypothetically, we could do some image-based corrections and call it good, but then you have to bootstrap your errors later, and that comes up with a whole host of other problems. So we would like to get it right from the beginning. And so I built this simulation with this analytic Gaussian decomposition beam. And this is just showing that there's a variety of different modules that you have to go through and various tests that one can do. It's quite a complicated process. But if you input that Gaussian decomposition beam all the way down to double precision, and then you ask, well, how far out do I need to go into the kernel in order to measure the epoch of reionization? You get these sets of curves here. So in gray here is the epoch of reionization. You'd like this curve to dip down below it so that you can see the epoch of reionization. This is just a simulation with foregrounds. And so if you go really far out, you can get down really deep, which is great. If you go midway, you can still dip down below, but this is obviously This assumption is no good, no go, so you need to go out further. And I'm bringing this up. This seems like a really simple thing to me, but you need to find out how far you can go and get away with the most that you can, because you are gridding visibilities and you generate 4 million visibilities every 2 minutes. So if you can cut down the number of pixels that you are including in your kernel, you drastically increase your computational ability. So the green curve here would be the one that we go with. And I want to mention that these lines are along a constant derivative. And if I flip to the next slide and choose a different kernel, one that's much smoother, has no side lobes, you can see that the contamination, again, seems to be consistent with the derivative that you go out to, or where you cut and what that edge derivative is. But you can see if you have no side lobes, you can get away with far fewer pixels. So this would be fantastic, a fantastic beam kernel to have, because you can get away with murder, essentially. And so to answer the question, well, how accurate does the A term need to be for gridding? Actually, from a purely combination point of view, it doesn't have to be accurate. It just has to be smooth. And so here, for those who are aware of like noise propagation and optimal map making, this is comparing a variety of different kernel shapes, one of them matching the actual instrument, one of them with bad side lobes, and one of them with just that single Gaussian. You can see their noise curves are lining right on top of one another. So you don't gain anything by including the side lobes, especially from a noise perspective, from a signal to noise perspective. So we don't have to do optimal map making in that sense. We don't have to try to recreate the instrument perfectly. But if you're trying to answer the other question, how accurate does A term need to be for generating models, that's a different story. So I input my analytic model with my analytic beam, and then I ran it through everything using, my discretized pixels like one normally does in an analysis, and I got this green dash curve. That's terrible. That says that even if I knew about all of the things on the sky to 100% accuracy, even in the best of circumstances, you still cannot measure the epoch of reionization if you've discretized your model. So that's pretty bad because there's all this infrastructure built around degridding. It was a really popular technique because it was just the reverse of the thing that you were doing to combining the visibilities. And so it made a lot of sense to reuse it. And if you get your beam kernel wrong when you calibrate, you again have severe contamination. And this should be very reminiscent of the calibration systematics I showed at the beginning when I showed you the first power spectra. It's essentially the same thing. Try to calibrate with a bad kernel and you will do poorly. So what about the elephant in the room, the thing that I missed? What about this horizon edge? It's there, it exists, we should include it. You can include it in an analytic sense because you have a bunch of Gaussians and the horizon is a cylindrical top hat. You can do a convolution to actually calculate the analytic form. And this should scare you because it's infinite. So Gaussians are infinite, but they taper off to below double precision at some point, right? This circular top hat cuts through a Gaussian, and so it makes an infinite kernel. Does this say that all of our visibilities are correlated with one another, even if they're drastically separated in baseline space? Probably not. But again, this is very similar to what I was given by the engineers. The facule simulations that the engineers run, they have to assume an infinite ground plane for their simulations to run. And so they have an infinitely hard edge at the horizon. So we don't know what the horizon is doing. And that, you'll see, is dangerous. And this also poses a problem. If you have an infinite kernel, you don't know where to cut because it goes out infinitely, and so you'll always have some sort of hard edge derivative. And for this particular case, it sits right at the epoch of reionization level. So the solution, at least for that second question of generating models, is to go to purely analytic models. This is really computationally expensive. You need GPUs to do it. So Jack Line created a simulator called Woden. This is actually a GIF. If you look closely, you'll see some differences, but this is his GPU-based model and the actual sky, and comparing the two. So it's really quite good. But this is the way to get around that second question, at least. So now I want to show what that looks like in data, what some of that stuff looks like, and it'll show a host of problems, which is generally the case for epoch of reionization. You solve one problem and you see 100 more. So this is looking at one observation of the MWA with all the known sources removed. This is the primary lobe, and you can see the side lobes coming in here. And this is using the beam that we had before from the engineers. And this is the beam that we have now, which is that Gaussian decomposition. You can see it really cleared up towards the edges of the beam. It's not where we're most sensitive, but what it did is it allowed us to see something that we hadn't seen before when we went all the way out to the horizon. Now we see whatever the heck this is. This is the galactic plane setting. So we schedule our observations to be in a dark spot on the night sky and where the galactic plane is not in view, but obviously not well enough because the galactic plane is setting here. And I've removed all the known sources in the sky here, and so you can kind of see like this diffuse stuff in the background. This is now the brightest thing on the sky, even though the galactic plane sits at 0.3% of the maximum beam level. So we're really digging into the weeds here. And one thing that was obvious with this continuous beam that was not obvious with the discrete one is that we actually see that galactic plane aliasing throughout our image. So the galactic plane sits on the horizon. It's extremely bright. And so you have something that's bright, 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 not bright. And so again, that's a hard derivative. It will alias. And this is inherent to the measurement itself because you measured a Fourier space instrument, or a measurement.
You have about 3 minutes.
Great. So our model needs to include the galactic plane because we're really worried about what this galactic plane is doing as a function of frequency, which is really the killer part in power spectrum space. And this shows you what it looks like when you subtract the galactic plane. You can see that it's subtracting somewhat a ripple throughout the entirety of the image that when I'm showing this GIF seems to be somewhat obvious, but when you're just looking at a static image, not very obvious at all. So that was a really important part of getting this right. And I wasn't able to generate images for you today because my Python package broke yesterday, as it does. But if you go in the other direction, if you make an image out to the horizon and in the north-south direction, ironically, we see Cathay. Just barely it goes up here. It just comes in just barely, and it does the exact same thing that the galactic plane is doing because Cathay is super bright. And so even though, like, we didn't even model Cathay before because we just figured it was so low down, 0.3%, that it wasn't contributing anything, but it does. So we took care of that as well. And now with being able to generate horizon-to-horizon images that are fairly clean, we now see a bunch of RFI that we have not been catching. RFI coming from Perth, most likely, towards the south. Sometimes we see RFI over here, I don't know, from the middle of the outback. That doesn't make any sense, but we see it regardless. And it's not being caught by any of our mitigation systems. So I want to give you an update on where we're at right now. I'm doing an analysis. It's not that much data at the moment. I'm currently actually doing it. Here on the right is a paper I led in 2019. It's not the best MWA limit anymore, but it was at the time. And in this dashed line here is the noise curve for that set of data. Black line is the actual measurement itself. Gray is the 2 sigma error bars, and then the upper limit sits at the top of those gray sigma error bars. And we're trying to get down to this brown line, the EOR itself. And so we were systematics dominated in this 2019 limit, in the sense that we measured something, but it's obviously not the EOR, so it's an error. We measured some sort of error. And the data analysis I'm doing right now, its noise curve is higher, so it's not as much data. But the promising thing is that it is noise dominated still, which at this point is very promising. One thing I will mention is that I wanted to have the most updated version of this as possible, and so I quickly integrated my last bits that hadn't been integrated in last night. And this bin jumped up from almost negative to here, and it's like, God, that's the name of the game. And I know exactly why that happened is because I think there was some residual RFI that I didn't catch because I was going really fast. Which brings me to my next slide, is that this is what the other polarization looks like. It sucks. So it was really bad in 2019, and it's still bad. And I can say that given the amount of RFI I'm seeing and their distribution on the sky, that this is RFI dominated at this moment, which scares me for the other polarization, because even though it seems to be affecting the east-west polarization more likely, it's going to be in this data set as well, right? So it's still there. So we need to somehow employ harsher RFI mitigation techniques. All right, so that concludes my talk. I'm willing to take any questions you have. Thank you.
Thank you. Are there any questions?
Very nice, but very scary.
Yeah.
So in your beam model, you assume a real beam, I assume, but in reality, of course, the beam of every, let's say, station, or your case tiles, might be slightly different, right?
Yeah.
And that leads to a complex beam, and then
Yep.
all the sources are not just, right, changing their amplitude, they're changing their positions
Yeah.
as well. So have you looked into this?
We've done some preliminary work on it. So Aman Chakshi, a student that I supervise, was measuring the variations in the beam shape using OrbCom satellites, which has been done before, but he tried to see exactly how the side lobes were changing, which is really where the changes happen the most. They seem to happen the most in the side lobes if you have like electrical failures in your dipoles, right? So at the NWA site, the rain is slightly acidic, and you have this nice red dirt, and it somehow gets into on top of the LNA, and when it rains, it creates this like acid that will actually burn through your circuit boards. And so you have dipoles dying. And so your beam actually changes drastically, and as the MWA has grown older, we see it changing even more drastically. So this is actually really early data. This is 2014 data, so that instrument should have been really healthy then. So I don't think it was really affecting this, but it will have to come into play as we go into the later stages of the data processing. And it's really scary because what Aman saw with the ORCON satellites is that ORMCOB is looking down at you when it's passing overhead, but as it goes away towards the horizon, it's no longer looking at you. So you can't actually measure what the side lobes are doing. So you still don't know what the instrument's doing at the horizon. It's still an open question. Can't even seem to measure it with communication satellites. So it's an open question, and it's very scary.
So maybe if I have time for a very short question on the RFI, of course, right? I mean, the strange thing is, right, we have LOFAR in probably the busiest RFI environment you can think of.
Mm-hmm.
But MWA seems to suffer more from it than we do. I mean, maybe we're naive and we're suffering from it, but we don't think we are at this level. So,
Right.
So why is this?
Yeah, I've always thought about that. My best guess and this is not a fun answer, is that our AO flagger parameters aren't tuned right. That's my best guess, because it shouldn't be different from your environment, which is much worse, right?
You have a wider beam, maybe you're also picking up RFI more easily.
That could also be it. So the RFI that I didn't show the images of is actually seems to be coming from below the horizon. So that's super weird, and I don't think that's something that LOFAR deals with a ton, because it doesn't go out that far. But what you're getting is through the curvature of the Earth, the radio signal from whatever station or whatever is slightly curving around. And so you can't even make an image of the RFI itself. You can just see the PSF structure kind of going down to below the horizon and then mysteriously disappearing. That could be a part of why we can't flag it very well.
Thanks.
Yeah.
I think obviously an interesting problem that we've tried various things on as well. But one thing I didn't quite understand conceptually is, you showed these complex A's.
Yep.
But in reality, these things are different for the two polarization states.
Yeah.
And meaning, at the end of the day, your visibility and also your foregrounds are also polarized. And you showed, even in I, that's a big problem. In polarization, I don't think it gets any easier. There's additional spectral structure, which is not smooth to start with. So it seems I'm missing, maybe that's too much detail to be putting in your talk, but what do you do about polarization? It just seems makes this problem infinitely more complicated.
Yeah, no, that is a fantastic question, and that is the next step. This is really the base level expected contamination, the idealized portion. The polarization aspect is terrible, because you get expected polarization leakage towards the edge, and you can try to correct it, but we're not correcting it very well at all. So just because you mentioned it, I will point this out. None of the diffuse maps that I was able to take have done very well in the primary lobe itself. So the diffuse structure in this primary lobe will be very faint. So it's off the galactic center itself. So it's a really faint measurement, but I can't seem to make any models look good. And if you look really closely, you can see that this particular model is introducing structure a little bit, maybe like here-ish. And I think it's because of polarization leakage, that I'm not getting the polarization leakage right. Or maybe the measurements will, we have like an MWA diffuse map as well. Maybe it had polarization leakage in it, and I can't translate it into these observations because they experience a slightly different polarization leakage. It's really terrible, and something that we really do need to work on. It's basically like a second stage correction on top of this. So yeah, no, it's definitely the next stage towards corrections. Yeah.
Thanks, Nichole, for a very nice talk. So our next speaker is Saurabh Singh.
Okay, so let me get started. I'll be talking about Cirrus. You may have heard about it in some previous talks, but I'll just give a few more details about our past analysis and also what's going on right now. So at the outset, a big shout out to all the Cirrus team members. Many of them are here in the audience. And also we acknowledge a lot of support from our mechanical electronics services, along with a lot of observatory supports from Gauri Vidnoor and also from Hanley Observatory. So I think this has already been talked about. Cirrus is an instrument just to measure the monopole component of the 21 centimeter signal. And it's very simple setup, right? Because all you need is a single antenna. The key is it has to be absolutely calibrated, which means we have to measure the absolute temperature, unlike the fluctuating component, across a range of frequencies. So it's a wideband absolute calibration. So in some way it's similar to what FIRAS had done for CMB, which is the black body measurement. And what we are looking for are signals like this, and in the past talks, Anastasia has talked a lot of this. So we have these standard models corresponding to lambda CDM by sweeping over a range of different astrophysical parameters. And the right side is more exotic excess background models, for example, that are more easy to constrain given their large amplitudes. So yeah, we'll be touching upon these models later in the talk. But as I think it's a continuous theme across the day-to-day, that we have extremely bright foregrounds. So the right panel here is basically averaging over the entire sky to show what the synchrotron-dominated foregrounds look like compared to the suite of standard 21 centimeter signals that we want to detect. Per se, this is not a big challenge, as people before have pointed out, that there is a degree of smoothness in the foregrounds, which has also been tested using what Mayuri has mentioned before, standard sky models, and trying to see how many spectral modes are really required for this. And turns out that if it was just this case, an instrument was not doing something funny, in spite of this huge dynamic range, it's possible to detect the signal. The problem arises because our own telescope is very chromatic in different ways. Some of them are unique to global signals experiments, but many of them also share a lot of challenges with the power spectrum measurements that we had seen before. One crucial difference is the first term, which is the primary beam, which is basically this, and also the transfer function. In some way we call it return loss or impedance, whatever. The problem is that because it has such a wide field observation, it's very hard to calibrate these properties externally, unlike interferometers where we use these bright point sources, of course, with their own set of problems. So in global signals, we have to do some kind of an external modeling for this. Along with it, we also have these multiplicative gain terms, which is again a very common thing. We use these standard noise source injection, which is I think fairly common across all the global experiments. We also have additives which are non-sky additives, contributions coming from our own amplifiers, and also the way antenna is interacting with the ground. Again, this is something not that can be in situ calibrated, but externally modeled, and I'll touch upon all these three and how Cirrus aims to address these things. But going back to the smoothness part, because that's really the driving force and has been already discussed a lot. If you have a foreground and a 21 centimeter signal that's shown here, and you only fit a very smooth function that can fit to these very low spectral modes, what you see is you are able to subtract out the entire foregrounds, but you are able to preserve a lot of the 21 centimeter signal. So that has been the design philosophy of Cirrus, that instead of having non-smooth components and trying to accurately model them, we would like to have as smooth a response as possible and then try to model. So even if there are calibration errors, they're not really showstoppers, because the kind of accuracy that we need in modeling our instrument itself is very high. So go as smooth as possible, but at the same time try to model it as accurate as possible. So this is what the instrument looks like. It's a very simple system, honestly. It's just one antenna, analog receiver, and digital receiver. So what really can go wrong here? But there are lots of different aspects that we have worried about in order to minimize internal systematics and the way sky couples to the system. So antenna, as I said, this is one of the most critical parts of these experiments because they cannot be calibrated. We need to have something that has as low frequency dependence as possible in its primary beam pattern, and it needs to have a transfer function which is as smoothly changing as possible, because the sky signal is literally multiplied by this. So any kind of spectral characteristics in the response function will be imprinted on the sky. So we go with this monopole antennas and deliberately design them to be electrically short. What it really means is that we have a very poor match, which is very different philosophy from typical applications of antennas. But what we ensure is by operating it in such a poor matching regime, we are able to preserve the smoothness of these responses. The analog receiver sits just below the antenna, and it has been extremely miniaturized also so that if there are reflections in the system, because there are impedance mismatches, and therefore we would expect standing waves, we don't want multiple cycles of those standing waves because they do share a lot of the modes that we expect in the 21 centimeter signal. So extreme miniaturization basically helps to sample only a very small part of that. Later down the chain, we have this backend system, which are basically related to the filtering and amplification parts of the signal. Along with, there is a special phase switching that happens, which basically flips the output signs here. So any systematics that are added later down the chain are completely uncorrelated when we split the signals. So in some way, even if we are looking at a single monopole signal, we are actually cross-correlating. So it's like a pseudo cross-correlation experiment. And of course, the digital is shielded with some 80 dB isolation. And at the same time, we have another set of isolation between the front end and the back end, also to basically avoid any kinds of back reflection. So this is basically all the effort that has gone into making Saras as ideal or spectrally smooth as possible. And the way we have designed these systems are basically doing a very realistic forward models, where we have these antenna beam models convolved with different kind of diffuse sky models, and getting this data and assessing how well can this design be used to detect the 21 centimeter signal that we are looking for. So basically, based on these different variations, we have optimized the monopole design. And this is not really the first of its kind. Saras has been experiment running for a very long time. We started actually with a dipole antenna, which is what most of the other experiments are using, but we saw intrinsic problems with the dipole in terms of its calibration. So we quickly moved to something which was a monopole antenna and also very poorly matched. Since then, we have observed the different frequency ranges, worked around with different profiles of radiators, of reflectors, and also the observing media, which is what we are today. So I'll mostly be focusing on the results that we have got from these monopole components. So the first science constraints that came from here in terms of its cosmological implications was Saras-2. This observed in 100 to 200 megahertz, again using a spherical monopole antenna. And based on some 60 hours of observations, we were able to reach a sensitivity where we could rule out a bunch of standard 21 centimeter signals. That's basically the color bar here. What we were most sensitive to, which is also probably true with other results, are the cold IgM scenario, where the gas is very cold and therefore the contrast between your background and your kinetic temperature is vast. Also, we were very sensitive to the rate of reionization, simply because if the brightness temperature increases sharply, it's more non-degenerate with the foregrounds, and therefore you are more sensitive to it. So those are the kind of classes that we ended up rejecting with Saras-2 observations. Later on, this work has been extended by Harry, Anastasia, and others, where they also included a set of very non-standard models that had a lot of excess radio background. The conclusions were roughly the similar, which is, given this prior space, the kind of signals that Saras-2 was able to constrain was the one that had very low extra efficiency, which basically meant very cold IgM, and also very excess radio background, so that the contrast was huge. Then we shifted gears and we said, let's go to the low frequency band. A lot of exciting things happening there. Cosmic dawn, absorption trough, one of the most visible features of the signal. So this was done in 2018 with very different antennas. This was done in Ladakh. The problem that we clearly saw, especially at these frequencies, is how sensitive the antenna became to the profile of the ground. So it was not just looking at the sky, but it was also looking deep meters into the ground. And therefore, a lot of systematics due to those stratifications started affecting the data, and therefore it's also started affecting the spectral smoothness of this. So Kavita has been doing a lot of these simulations of trying to see what kind of different stratifications can cause. So what we are looking for is the S11, or the transfer function of the antenna. And the two colors here, especially the green and the orange, basically show just if your soil is layered and non-layered, what are the kind of differences. So it's not just the change, but also the spectral nature of the signal changes completely. Therefore, we decided, okay, let's go for something which is more homogeneous, and that's when we moved to water. So water clearly is a more homogeneous medium than ground. And the orange curve and the blue curves basically show the simulation and the measurement comparisons when we had deployed Saras-3 on water. Again, there is a problem there, which is the depth. So we still have a length scale in the system, which is a multipath propagation impinging one directly at the antenna and another reflecting off the lake bed. So we do have requirement there. If you have shallow water, that's the green line, you start seeing ripples. So water is good, but it should be taken with a grain of salt. We have to have very stringent constraint on what kind of properties do we want. So with that, the deployment happened in 2020 with a very specific aim, as many of you are aware, which was the edges signal, which was very anomalous. And there have been works before the Saras observations also happened, including ours, and Girish is here in the audience, about trying to also look at edges data from a very model independent way and basically assess if this flat profile was really a unique solution, and turns out no. There are lots of systematic driven models that can also give rise to very similar kind of goodness of it. So, but really the key was to have an independent verification from a different instrument, from a different site, and that's what we did in 2020. So it was similar deployment like 2018, but on water with a very revised system. And we collected around 80 hours of data. This was not as radio quiet as the Ladakh trip that we had, but we would, by a very stringent RFI flagging, we could get around 15 hours of data. So I could totally relate to your experiences of the deeper you dig, the more RFI you find. So at the end of the day, it was just 15 hours of data that we had to basically examine if the edge signal was there or not. So in addition to the bandpass calibration, we also have some external calibrations to the antenna. This is what I discussed in the beginning. So we have the efficiency of the antenna, the internal systematics, which is basically the additives, and also the contributions coming from the media. In this case, it happens to be water. So we do have some variations of these based on our modeling, and therefore that's also taken into account of how well we can absolutely calibrate the data. So after all of these corrections, the blue line is what is the so-called true sky or the measured true sky model with Ceres. So now the final question is that if you have this LST averaged all corrections done data, how do you go about finding this flat profile that you have been looking for? So we basically had a two-component model, the one that had represented some foregrounds and if there are any residual systematics because of our antenna-related issues. Along with it, a flattened profile, the best fit profile, scaled by a free parameter. And the idea was to model them jointly. What we found was the scale factor right here was very consistent with 0 at around 95% significance. That included our systematic errors as well. And therefore, we disfavored the presence of the flat profile that Ceres had claimed the detection. Of course, the question is how sensitive this result is to all the different analysis choices that we have made. So for example, we have been correcting for these things externally. So we have measured it in some way, but how accurate those measurements are. So then we went around basically cross-matching and also sometimes not even correcting for these things to see if we are still able to say something or do our conclusions change. So these different scatters are basically different scale factors that we have got by changing our analysis choices and perturbing them. And what we see that in all these perturbations, we have always been consistent with 0. And therefore, and this has really gone into assessment of errors as well. The second question is how sensitive you are to the region of the sky you are looking at. What if it's just some magical cancellation has happened? So we then split the data into different kinds of time slices and tried to look at the results. And again, we find that in all our different slices, basically looking at different LSTs, you still find that your signal is consistent with a scale factor of 0. So with all these different cross checks, we basically concluded that the profile that Edges had claimed was not in the data. I'll probably gloss over it. I'll come back to it if the time permits. But really, one question that we have always received, and that's a very well-pointed question, is there are differences, both in terms of our choice of bands, choice of foreground models between Edges and Ceres. So is it really an apples-to-apples comparison? So we ended up taking Edges publicly available data and basically made sure that it is exactly at the same level as Ceres in terms of frequency resolution, in terms of bandwidth, everything, and then applied the same foreground model on both. So in this is as close as apples to apples comparison as we can get. And what we saw here are that the residuals between them were completely uncorrelated, or basically saying that even if we applied the same analysis choices, in one case we detected the signal when it was Edges data, and we did not detect it when it was Ceres data. So the residuals themselves were consistent with a 0 correlation, and this was at a 98% significance. So this basically again pointed to the same thing, and then that was followed by expanding on the parameter space itself. So we went over the range of the flattening parameters, the center frequencies, the amplitude of the signal, and the width of this flat Gaussian. And again, the conclusions remained similar. That is, we ended up rejecting the entire parameter space with different degrees of significance. And the parameter that we found to be most sensitive to was the amplitude, of course. So larger amplitudes were ruled out with a very high level of significance, and it reduces as you push low and low. So that was basically the inference that we drew from the Edges analysis. Again, collaborating with Harry and others here, we tried going beyond edges and trying to ask what about the other kind of standard models that were there, and could we say something about them. So what we found is if we again construct a suite of these signals, some with standard cosmology built in, some with also having extra radio background, we could constrain a lot of these parameter space. So this was the plot that I think Anastasia showed before, which is by taking CERES-3 data, we could actually constrain both the X-ray luminosity and also the radio luminosity. So we are again constraining some kind of an excess radio background. We are still not sensitive to the standard 21 centimeter signals yet, but we are able to root out a lot of them that have a lot of radio excess, which is motivated not just by edges, but also measurements from LWA and ARCADE that claim to be detecting some excess at these frequencies. I think I'll just skip it. So it's the parameter space and shows that what kind of numbers we are more sensitive to. So star formation efficiency along with the radio and X-ray luminosities are the one that was most well constrained with CERES-3. So right now this is where we stand, which is we have this parameter space that have been ruled out in addition to a lot of excess radio background model which is not here. But going back to the standard regime, we still see that there is a sufficient parameter space that needs to be explored, and of course we need to detect the signal eventually. So that's where we're heading now. How much time do we have? Okay, thanks. Yeah, so one of the major questions again from the earlier analysis was the spectral complexity. So if you could see here, when we did this foreground and systematic modeling, we needed a sixth order log-log polynomial, which I'm sure many of us know that if it was just true foregrounds, we definitely need less number of terms, which basically means we did have some residual systematics that needed that high order of polynomial to be consistent with thermal noise. And of course, that has been taken into account when we were looking for the signal and the kind of signal loss that we would incur because of that. But then the question is always good to be spectrally smooth, as the design has been. So then we have been looking at all different possible sources, including optical modules, instabilities, and various other things, and what can cause this. So over the last few months, we have basically made a few changes in the receiver, and at least in the lab, we are able to see a much reduced complexity in terms of the spectra. So this data, I think we took just sometime last year, and what we see is that of course, this is not sky data, so instead of antenna, we have some antenna simulators that mimic the response, and we are able to get down to the noise levels. But another level of systematics that we have is coming from the antenna itself. And again, I keep coming back to it because that's really one of the things that's really a bottleneck. So Kavita has been doing a lot of simulations of different kinds of systematic errors that can really percolate. So for example, water is not known for its firmness. Antenna can have tilts, antenna can have variations of height, and how these different kind of variations finally come down to the signal detection prospects. So we have been doing a lot of parameter sweeps in the electromagnetic simulations, trying to assess what kind of data that we will see. And Yash here has been also working a lot on trying to assess how these different systematic errors can finally give you the residuals that can, what is basically the accepted level of residuals, and therefore the expected specifications within which we are still able to work. So for example, if you have conductivity variations of water, of course in some way it's good because your signal that's going down the lake bed will be attenuated faster, but at the same time, it also behaves like a conducting plane, and therefore your beam might get more chromatic. So, and that's basically shown here. When you are increasing the conductivity, your kind of residuals that you expect just from foreground being observed by a chromatic beam shoot up. And then if you have tilts, for example, that's even more detrimental. So all of these different kinds of constraints have now gone in the way we conduct our experiments, and what is this allowed parameter space in which we can observe this. Finally, we had our test observations just last month. So this was done at the same site as 2020 observations, but the site is not the same anymore. So the left side and the right side are both the data sets that we took when we had deployed it there. The difference here is within the system, we have provision to look at what the system response is, which is the right side, and what the sky response is, which is the left. And as with all other experiments, you see a lot of this RFI. Of course, beginning of the night, it's hard, it's very strong, kind of reduces, but there is still chunks here. This is just the galaxy rising. We are still working through this data. We have some 4 nights of data trying to see if we can extract some useful data sets. But looks like this site has become louder in radio. But at the same time, we have also seen that system performance has really improved compared to the last deployment. So really our key effort now is to find a site that is more radio quiet. So that is one exercise that we have already begun, and we have had some characterizations of sites in different places. So one of the most promising place was Ladakh, the same place we went to in 2018. Well, not exactly the same place, but the same region. We deployed our antenna not for science observations, but for characterizations. And it turned out that in terms of radio quietness, this was one of the best places that we could have gone to. So for example, the time frequency plot for our field station in Gaudibinur, which is near Bangalore, looks something like this. So you clearly see FM lines, you see a lot of these low frequency stuff, which is again very common at a very usual site. But the moment you go to Ladakh, for example, of course you see OPCOM and we better see it, it's everywhere. But lower than that, it is just extremely pristine. You do see some bits of FM reflections when a plane passes by or a meteor passes by, but otherwise, at least the sensitivity of our RFI system, we are not able to see any persistent RFI. It's actually looking at the occupancy of this region, it is very competitive with what we see, for example, in Western Australia. So we are now slowly gearing towards science deployments. Right now it is inhospitable. We are waiting for summers. So the idea is that we'll take our instrument there and basically do science observations at a site like this, and hoping that it continues to be like this. So basically, Ceres has been very custom designed to have spectrally smooth characteristics, and also a lot of effort has gone into modeling those smooth characteristics. And what we have also seen is if you're observing this on a very homogeneous medium, it really improves, reduces the systematic error and improves our chances of detecting the signal. So we are basically right now observing on water. And we have been able to address a lot of these challenges that are common to the 21 centimeter experiments, and therefore in the last few deployments we had constraints on astrophysics, and we are basically gearing up for the next science deployments. And any of you, if you have better sites in mind, please let me know. Thanks.
Thanks, Saurabh, for a very nice talk. Questions?
Yeah, so this is really inspiring, Saurabh. Very nice, of course. So, couple questions. One was a very interesting idea from your group about foreground cleaning was the maximally smooth function idea, but it was not used in this analysis.
Yes.
What was the reason for that?
Yeah. So that is basically the residual systematics, and that has been.
Can I quickly add my second related question,
sure.
and then perhaps you could answer the both together, which was you mentioned that you needed this 6th order polynomial, and that was a potential source of worry. But what's interesting is that the edges analysis used a 5th order polynomial. Shouldn't it be interesting to correlate your residuals against the 5th order polynomial, even though you don't understand those, with the edges data? Shouldn't the analysis only use the foregrounds that edges have used?
Yes. No, great questions. So I'll answer the first one, which is 6th order. Yeah. So definitely, first of all, we were not able to use maximally smooth functions at all for Ceres 3 data. And the simple reason is that this residual systematic component really dominated. And this was changing actually with LSTs, and therefore we know it was not something cosmological. So they do need 6th orders, and therefore they are not maximally smooth. We have looked at different origins of this residual systematics. That's really been one of the driving forces post this deployment to basically reduce the complexity, the spectral complexity of our system response itself. Part of it, again, it's not a single factor that has contributed to this. The two major ones, one is we are using these optical modulators and demodulators, which are not as stable as RF modules. So we have worked upon improving their performance. And the second one is the total efficiency of the antenna and how it changes based on the media on which, basically how, when it's floated on water, how temporal variation affects the signal detection prospects. So these are the two lessons that we have taken forward from this deployment, and basically now we are at a position, especially in the last test deployment, where these things were brought much under control. So that's the first one. The second one that relates to the model choices. So yes, we have actually done that, and it's both ways, which is we have applied our model to edges and edges model to ours, basically 5 and 6 terms. And our results are again same for the two orders.
Very, very nice. I was sort of trying to think of the connection to what we're trying on the moon is that, right, you have an experiment on the lunar regolith and, right, you don't have a ground plane, it's too expensive, it's right there on the surface, right, waves penetrate, they reflect back, and then in an experiment like this, right, you're not just measuring the autocorrelations of the signal directly, but also, right, the reflected signal. So do you see, because you mentioned in one, you said, oh, we know it's roughly a couple of meters deep and it goes back. So do you see that sort of baseline ripple in your data? How do you know it's a few meters deep? Because, right, the same problems will be happening on the lunar surface.
Absolutely. So maybe Mayuri would talk more about it in a talk. But yes, ground profile independent of the planet or the satellite would be a problem. And therefore, we have also been looking at the regolith profiles that have been done by Chandrayaan and other experiments to see if we can get an access of, trying to simulate if there is a lander, what happens. Coming back to Saras, how do we know that they are actually from there is basically from these EM simulations that we have done. So essentially, it's a very non-linear process. So the length scales don't match. For example, if we have a meter, it won't just correspond to that periodicity. It's a very cumulative effect of different layers and how their conductivities and permittivities change. So even with a small change of these properties, just the height changing by a few centimeters, for example, your S11 can drastically change, as you see there. So it's if we are going for an experiment with no metal screens, in some way it's good because it's electrically small, so probably no side lobes. But at the same time, I think we need a very rigorous analysis, maybe using radar or something to actually map out the profile.
Of course, that's a bit hard on the moon, but, and of course, just maybe one point, of course, on the moon, right, you can penetrate hundreds of meters and go back, so that's an extremely long baseline, right, and you reflect about 7% back, so that will give a very short frequency ripple.
That's
so that the problem might actually be worse on the moon. Here it's spectrally more smooth because the sort of the depth you go and the reflection is less long.
Yeah, I think both extremes might be okay. Either the length scale is so high that it's all constrained to like what we.
Then you just filter it out. Yes.
Yeah. So basically, it's some high delay filtering. It's the intermediate boundaries that are real problems. So even for example, not just ground, right? If you are in a satellite around the moon, you would expect some reflection of the moon.
Indeed.
So, but there at least we are safe because the length scales are large.
Thanks.
Yeah.
What you wanted to be found, is there any problem with ice?
Yeah, I mean, the properties do change. The antenna properties are not exactly the same on the two, and also it might melt the ice because the receiver gets heated.
Sorry?
The receiver gets heated, so it might actually melt the ice.
Be sitting on a big plateau of ice like at the Antarctic, you won't melt much.
The local regions around the antenna affected the most, so the near field part. But in principle, I mean, it's not out of bounds to think about those.
That's radio quiet.
Yeah, it should be. Yeah.
Yeah, we are already overshot the time, but we'll have one last question. Maybe you can. Yeah.
Thanks. Do you gain anything from combining your data sets from similar measurement locations, like the lake you went to a couple years ago and the lake you're going to go to coming up?
Combining from different deployments?
To try to control for some of these, from different deployments to control for some of the environmental factors.
Yeah, we haven't attempted that yet, but that is one thing we certainly want to look forward to. So like one of the plans going ahead is also go back to low redshift, 100 to 200, for example. So going all the way to 6, you might have, it's impossible to design, at least not impossible, but very difficult to design one antenna that covers the entire range. So you might want to combine different experiments, different antennas, and also like different deployments. That definitely improves constraints like what Anastasia was talking about, Hera and Ceres combinations. So that way we do have plans going ahead, but right now we haven't done it.
We'll thanks the speaker once again.
Yeah, welcome back everyone. Our first speaker today is Rennan Barkana, who will be talking about 21 centimeter cosmology in the dark.
Okay, thank you. So Harold asked whether my title, whether I meant to say that we're all still in the dark, but actually I was just referring to dark matter in the dark ages. So I've been here, like some other people here, you can search for yourself in this picture from 2016. It's very nice to be here again at RRI. So we've heard a lot about 21 centimeter cosmology today. I'll just highlight a few points related to my talk. So the spin temperature is this effective temperature that is defined in a way that describes the relative abundances of the excited and ground state of the 21 centimeter transition. And of course, through this technique, we hope to study the epoch of reionization and cosmic dawn. And for cosmic dawn, the main equation is just the dependence of the 21 centimeter intensity on the spin temperature through this combination. And then, as was mentioned today, we have the Waldheisen field effect, where Lyman alpha photons from the first stars interact with the hydrogen atoms, and they couple the spin temperature to the gas temperature and turn on an absorption signal if the gas is cold. So we also heard about the edges experiment and this unusually strong absorption that was claimed to be detected, and Sarah's now contradicts it, but it's only at about 2 sigma, so the situation is still unclear. But if edges is correct, then to try to explain this, you go back to this basic dependence, and one way to explain why you have stronger absorption than expected is to have the spin temperature go to the gas temperature, and the gas be colder than expected, and you're dividing by a small number. And the suggestion was that the combination of Lyman alpha coupling from the first stars plus cooling the gas below the expected temperature, which would naturally happen if it's coupled to the cold dark matter with some kind of scattering interaction, this could explain edges. And the nice thing about this model is that it predicts a very clear, very strong pattern of 21 centimeter fluctuations at the same kind of cosmic dawn redshift. And that's basically coming from the baryon acoustic oscillations, from the velocity differences between the dark matter and the baryons coming back from before cosmic recombination. Now, if you actually try to construct a specific particle physics model that allows for this type of interaction between the dark matter and the baryons, you run into many different constraints, because a new type of interaction, a new interaction of this type, would allow the dark matter to also interact with itself, and that would be self-interacting dark matter, which is highly constrained by the distribution, by the properties of dark matter. And it would also give the baryons a way to interact with themselves. This would be a fifth force, and that's very strongly constrained by lab measurements. So a nice solution was suggested by Munoz and Loeb, and that's Millet charged dark matter, to have some part of the dark matter have a tiny electric charge and not have a new interaction, but just electrostatic, just a Coulomb interaction with electrons and protons mostly. So this model can give you this effect. However, with Kovac et al., we showed that this model, if you look at all the different astrophysical CMB, and cosmological CMB, and particle accelerator constraints, it's only viable over a narrow range of parameter space. And over that parameter space, actually, this pattern is predicted to is erased in this model. The reason is that before a combination, when the universe was completely, the gas was fully ionized, this interaction with the Millet charged dark matter was so strong that it took the Millet charged dark matter particles along with the baryons and the photons and erased this relative velocity. But then Liu et al. Suggested a slight twist called the interacting Millet charged dark matter model. So where you start with the Millet charged model, but you also have some kind of long-term or long-distance, long-range interaction between the Millet charged part and the rest of the cold dark matter. And this allows the Millet charged part to share its energy with the rest of the dark matter. It turns out that this simple idea actually opens the parameter space much wider, and it also brings back this prediction of a strong BAO pattern. So basically, just to write it out in more detail, so you have the baryons, and it's the ionized part that matters, and it interacts with the Millet charged part, which is some fraction of the dark matter. There's some particle mass for the Millet charged dark matter, and the charge is Q in units of the electron charge E. And then there's this long-term or long-range interaction with the rest of the dark matter, just the normal cold dark matter, which can have a different particle mass, and there's some coupling constant. So I don't want to go through all of this figure, which is from Liu et al., just to show. So this is just showing the parameter space for the two main parameters, the mass of the Millet charged particles and their charge, again, in units of E. So ignore all the lines, just look at the shaded region. So in white is the viable region given all constraints. So you see that there are many orders of magnitude in both of these parameters that are viable compared to the simple millicharge model, which is basically only alive in this little corner of the parameter space. Okay, so this summarizes the basic results. So this is a paper with Anastasia and with two of the co-authors of the Lewedal model. So this summarizes the prediction for the global signal, so the absorption depth and the power spectrum, so the fluctuation squared at a particular k. Both are at redshift 17, roughly the center of the edges feature. And up here in purple is the entire range of normal astrophysical models without any dark matter interaction. Now, and the main parameter that is being varied here is this Q, the charge of the millicharge particles. So if Q is low, you see that we have these points where the global absorption is roughly the same as the maximum allowed for normal astrophysics. This shows basically the maximum global and power spectrum signal possible for each of these different values of Q for the millicharge dark matter. Now, if you increase Q, you see that you predict stronger and stronger power spectra, and also you get into the edges range of the absorption, so you can get the edges global signal, and you can get power spectra that are 2 orders of magnitude larger than the maximum in standard models. And the point is that this range is going to be tested very soon. So this shows a forecast for Nenufar, it should reach this kind of level. Hera, the forecast it should eventually do even better, and SKA would be forecast to do even better than Hera. So this is all coming. Now, as was mentioned today, there's a different class of explanation for edges, which is going back to the simple equation. Instead of decreasing TS, you can increase TCMB by complementing it with an early background of strong radio emission, low frequency radio background. And so this was suggested already in the edges paper, and then various other people looked at this. So in 2020 with Anastasia, we first simulated this kind of model, which I think the most plausible version, which is just that the early galaxies happen to have to be unusually efficient in producing radiosynchrotron, and they are in this case responsible for the enhanced radio background. And then more recently, so led by my student Sudeep Sigdar, we made a more complete calculation of this, including the fact that at early times when the radio sources, when the galaxies were quite rare, what you see depends mainly on whether there's a radio source behind you. So it becomes almost like a 21 centimeter forest. So you can see that compared to the previous work when we were just doing a uniform, basically spherical average, with the line of sight effect, you get significantly larger fluctuation. This is just an example of 21 centimeter slices perpendicular to the line of sight. But even more interesting is if you look along the Z direction, the line of sight direction, now you get this kind of pencil beams because of, again, it's like a forest of background strong radio sources in this case. Of course, once you put in foregrounds, the foregrounds also, are smooth along the line of sight. So it still remains to be studied whether you can see this anisotropic signature even in the presence of the foregrounds. But this is just pure signal here. And as mentioned, the most promising experiment for the cosmic dawn is a square kilometer array. But in my remaining time, I want to talk about the dark ages. So this was mentioned briefly today, and there are many different efforts now, pretty seriously looking at going to the space and going to the moon. We're lucky to be at a time of an international space race to go back to the moon, and different countries are actually looking for a scientific excuse for this. And 21 centimeter cosmology from the dark ages seems to be the best, truly good excuse. So I won't go into details. There will be at least a couple talks specifically about this on Friday. So let me talk about the theory. So there have been a number of different papers on how, if there's anything exotic going on, such as a baryon dark matter interaction, this would produce a whopping signal during the dark ages. But I want to consider here the more conservative case of just standard lambda CDM. How well can this do as a cosmological probe compared to Planck and other cosmological measurements? So in a couple papers in 2005, we looked at this and noted that what the dark ages 21 centimeter signal would measure is the era of baryonic infall. So basically, so here is the delta baryon over delta dark matter versus K. So at the early times, the baryons were connected, were coupled to the photons. So delta baryon was very low, and over time it catches up to the dark matter. Of course, 21 centimeter signal is also sensitive to the baryon temperature. So this is the ratio to the baryon density, and also it starts low and goes high with time. And we noted that the 21 centimeter signal would be quite sensitive to the values of the cosmological parameters. And actually, Loeb and Zaldaryaga already pointed out that, in principle, 21 centimeter cosmology should be able to beat the CMB in the sense that you have many more modes to measure. You can go to much smaller scales, and you have a wide redshift area, or wide redshift range. But the question is, if you actually consider some observational reality, does this still work? So to find out, we used the CAMB code, which of course calculates power spectra at high redshift very accurately. And we added to it a few things. So this is work with my postdoc Rajesh Mandal, who will talk about this in greater detail on Thursday. I'll just summarize some of the main results. So this shows the global 21 centimeter signal. This is the predicted signal. So again, it's the average intensity on the sky at the brightness temperature versus observed frequency or equivalent redshift. So this basically measures the decoupling of the gas from the CMB. It cools faster and gives you an absorption signal. But as the universe expands, the collision coupling, which is what couples the spin temperature to the gas temperature in the dark ages, it starts to weaken and the signal goes down. So this is compared to the level of thermal noise for different integration times. So of course, in any realistic experiment, the real problem will be getting rid of foreground. But the thermal noise gives you a baseline level for how well do you need to remove foreground in order to reach the thermal noise at corresponding to a given integration time. So this is 1,000 hours, and this is sort of the ultimate limit of maybe 100,000 hours. So you can see that the signal is greater than noise for a wide redshift range up to about 100. So what can you actually do with this? Well, before going into the detail, let's go to the other case of the power spectrum. So this is showing the fluctuation squared, millikelvin squared versus K. And let's start just with these curves. So these are just the theoretical curves showing the power spectrum, again, versus K at various redshifts. So starting from 150, and signal goes up until about redshift 50, and then again, it starts to decline. Now, this is compared here to various thermal noise curves. Now, when you consider the power spectrum and an interferometric array, you have not just the integration time, but you have another key parameter, which is the collecting area. So our minimal configuration, which we call the A configuration, is 1,000 hours of integration time with 10 square kilometers of collecting area. So as I'll show, this is the minimum you need to compete with the global experiment. And since an array is much more complicated and expensive, you want to at least beat the global, the minimal global experiment to make this worthwhile. But then if we can go even better, then configurations B or C multiply by 10 one of these parameters, and configuration D multiplies both of these parameters by a factor of 10 compared to the minimal. So so these are shown for the A or B configuration, and based on the colors you see at redshift 75 or redshift 40. So at redshift 40, these two noise curves are well below the signal, right? This is like an order of magnitude here. So certainly this looks promising if you can measure it throughout this redshift range. And so I don't have time to go through it, but we also added the Alcock-Paczynski effect, which is quite important here. The fact that you don't measure distances directly, and the light cone effect of the varying redshift within each bin. So in terms of the constraints, for the global signal, it turns out you mainly measure just the overall amplitude. So the shape of the global signal is actually quite insensitive to varying the cosmological parameters. So you just measure one overall quantity, which corresponds roughly to the amplitude. Now, for the power spectrum, it's more complicated. You do have some sensitivity to the shape, but still there are very strong degeneracies among the cosmological parameters. So when you look at the ability to constrain individual parameters, you get some interesting information, but it's pretty hard to compete, for example, with Planck. However, things are not so hopeless. So how much time do you have? 8 minutes? Oh, okay. So I have a lot of time for this last last slide before the summary, so I want to go through it. This is basically the main result here of what you can do from the moon with the global and the power spectrum measurements. Okay, so here we have this is all 1 sigma limits or errors. So this is a relative error in percent. So this is 1% here. And this, so when we're talking about the cosmological parameters, as I mentioned, for the global case, you can only measure a combination. There's almost complete degeneracy among the parameters, and it's only sensitive to 2 parameters, basically the baryon density and the total matter cosmological density. And then roughly in this combination, which we call the global combination, so C global. And what comes out, again, with the thermal noise is that for a 1,000-hour integration, you can get roughly a 5% measurement, right? This is 1 and this is 10%. So roughly a 5% measurement of this combination. So of course, that would be quite interesting. This would be independent of all other cosmological probes. So 5% is pretty good, but it doesn't compete with the typical Planck constraints and parameters, which are sub%. But still, this would be nice and independent. And then if you can go to 10,000 hours, then you go to about 1%. And in principle, if you can go towards 100,000 hours, you can get sub% and approach Planck, but only for this combination. Although this combination is different from it's not a combination which has particular importance for other probes like the CMB. It's specific here, so this would be quite interesting to get a good precision on this. Now, what about the power spectrum? So for the power spectrum, again, you have some more information, but the best information is on this combination of all the parameters. So these are the 5 standard parameters that are used by Planck. So again, it's in both cases, the main parameter, which you're most sensitive to, is the baryon density, omega b h squared. And then after that is the matter density, and then the amplitude. So you have the amplitude, the primordial amplitude of the fluctuations, like sigma 8. And just like the CMB for all sub-horizon modes, what you actually measure is a combination with the fact that the fluctuations are damped by the rescattering of photons due to reionization, just like for the CMB, so you get this e to the minus 2 tau. So all of that is also sensitive. And then there's just weak sensitivity to the scalar index of the power spectrum and to the Hubble constant. The Hubble constant sensitivity comes purely from the Alcock-Paczynski effect. Okay, so if you consider this combination, then with our configuration A, you can measure it roughly again to 5%. That's why we chose 10 square kilometers in area. You get something for, again, 1,000 hours integration. You get a similar constraint to the global case for 1,000 hours. But then, in principle, you can improve much more with the power spectrum. So if you go to configuration B or C, you get to the sub% level, again, only on this combination, but it starts being complementary and comparable to some of the Planck constraints. And in principle, with configuration D, you would do much better. You would get to below 0.1% precision. Now, in addition to measuring these combinations of cosmological parameters, the other thing you can do is include some additional parameters, which also Planck treats as additional parameters to the standard set. So we looked at 2 of them in particular. One is the mass fraction of helium. And of course, this comes in because in the 21 centimeter signal depends on hydrogen. So you're particularly sensitive to the relative mass fraction of hydrogen compared to helium. And the other one is the total mass of neutrinos, where you get a reduction in the power spectrum due to the neutrino free streaming. So you're also sensitive to that. So let's start with the helium mass fraction. So for the global 1,000-hour integration, or for the power spectrum with configuration A, you get roughly a 10% measurement. Now, Planck actually, either on its own or with the BAO information from galaxy surveys, gives only roughly a 5% constraint on this. It's not particularly sensitive to this. So still, you're not getting to that level, but if you go to 10,000-hour integration with the global case, then you're comparable to Planck, and in principle, you can do a little bit better. With the power spectrum, with configuration B or C, you're already doing much better than Planck. You get to 1%, and then you can do even better in principle. And finally, for the neutrinos, so the global signal is almost insensitive to neutrinos. So only with the ultimate case, you can start getting some limit, but it's still not close to the constraint of Planck. So it's not too interesting. But for the power spectrum, well, again, configuration A doesn't come close to Planck, but configurations B and C are already comparable. And in principle, you can do much better on the neutrinos as you start to add collecting area and integration time. Okay, so to summarize, 21st century cosmology is very promising over what's quickly becoming a very wide range of different redshifts, from cosmic reionization, where of course, I mean, this is where it's most promising to do imaging of the H2 bubbles, hopefully maybe with the SKA. And then cosmic dawn, where we hope to see the Lyman alpha coupling era and the first era of cosmic heating and learn about some of the earliest stars and galaxies. And dark ages is quite interesting, and of course it's moving much more rapidly than anyone expected due to the race to go back to the moon. So maybe it will happen actually on a similar timescale as SKA, and that can be very, very interesting, very promising. And I talked mainly about three different topics. So one is this interacting Milli charged dark matter model, which is the only model really that currently exists that has a very large parameter space which is still viable. So it's hard to rule it out. Of course, the dark matter model is getting a little more complicated, but we have no idea whether the dark matter sector is not necessarily very simple and boring. So we'll have to let the observations decide. And what's nice about this model is that it will be tested by observations pretty soon, because it generically predicts this very strong pattern of 21 centimeter fluctuations at cosmic dawn. And the other alternative type of models are early enhanced radio background, which is significantly above the CMB, or at least comparable to the CMB at low frequencies. And this can either come from some exotic dark matter model, or just from radio galaxies being unexpectedly brighter by at least a few hundred, relative to the star formation compared to modern galaxies. Brighter in low frequency radio waves. Of course, that would be surprising, but it's consistent with all observations. And then in that case, you have a very interesting line of sight effect, which actually is so interesting or so large that you might be able to measure it even in models which are not consistent with edges, where you have just moderately efficient radio galaxies and not extremely efficient. And finally, about the dark ages, so I think the conclusion is that it would be easier to start with a global 21 centimeter signal, go to achieve a 1,000-hour integration. So as you go to high redshift, all the difficulties for the rays, for the power spectrum, get harder, faster with redshift than for the global signal. So it's easier to start with the global signal. But once you detect the global signal, there's only so much you can do. For the future, the great promise is the 21 centimeter power spectrum. It would be, again, it would take a large effort to get started, but in principle, it can become a very powerful cosmological probe. Okay, thank you.
Yeah, thanks. Do we have any questions?
Is there any chance of detecting these very bright radio galaxies using XK or something like that?
So, yeah, so with the paper with Anastasia, we had some plots, and yeah, if you get something bright enough to explain edges, then it's quite close to current limits for some of the radio surveys. And yeah, that's so actually, as radio surveys improve, that would increasingly produce an important constraint on this. Yeah, absolutely.
And I mean, would you expect a kind of a trough or something on the spectrum of these sources then? I mean, would they be just like you do quasar absorption line studies?
You mean a trough due to what?
Due to the H1.
Oh, you mean due to just this H1 to actually see it in the spectrum of an individual source?
Yeah, yeah. So I was asking that. That's a question.
Oh, okay. Well, yeah. but we're talking. I mean, if you're motivated by edges, you're talking about redshift 17. I mean, you need. I mean, I'm not sure whether you can see the individual sources. Of course, one problem with these radio smooth sources that you often don't know the redshift. So, but I'm not sure if they would be bright enough to see the individual source actually from those redshifts. I mean, the other issue is that again, to explain edges, you need these early sources to be so bright in radio that at some point galaxies had to stop being so bright, because if you extrapolate down to something like redshift 6 or 5, you start getting above the limits on the radio background, right? The general radio background. So so modern galaxies cannot be so bright. There would have to be some kind of early population that was extremely bright in radio. But it's a good question. I don't know if we looked at whether you can see individual sources from those very, very high redshift. Yeah, we should look at it.
Hi, so your talk was very interesting. I just had a sort of an amateurish question. So I come from a CMB background and I'm not very well aware of 21 centimeter studies per se. But you mentioned in your talk that you are also exploring some exotic models apart from the standard lambda CDM context. So could you elucidate a bit on that? Like, for example, like in the CMB sector, a lot of studies have been previously done, like say with some anisotropic spacetime geometries or these kinds of things. So is it related to that, or is it just exotic dark matter models?
So here by exotic, I mainly meant what was motivated by edges. So these are the two classes that I talk about. But I mean, I talk about it mostly for cosmic dawn, but these can be also exotic models that are relevant for the dark ages. So in particular, if you have some dark matter interaction, and again, it depends a little bit on these different models. For example, in this interacting Miller charge model, so at early times when the universe was ionized, the Miller charge dark matter actually goes with the baryons and you erase the velocity. But then later, after recombination, when there's only a small residual electron fraction, that scattering becomes much weaker, and then the Miller charge dark matter goes back to the rest of the CDM and you rebuild the velocity effect. But so as a function of redshift, during the dark ages, you have all of these effects happening, and that will certainly cause a probably much larger dark ages signal than what I was showing here for the standard case. So there have been some papers on how you could constrain various exotic dark matter properties, for example, during the dark age. Now for the radio, if it's what I was showing here, which is radio from early galaxies, it wouldn't be relevant, of course, to the dark ages. If it's some kind of early dark matter related background, radio background, it would be present in the dark ages also.
So I'm a total ignoramus on this, but would the milli-charged dark matter also interact with photons, and is there limits on that? Because, right, I mean, if it interacts with charged particles, baryons, it should interact with photons, so the photon propagation through the universe should be affected by these milli-charged particles, right? Has a limit been set on that, or is it just that particle physics exclude that? But
it's a good question. I think that's part of the constraint for early on, but if I have it right, I think that during the modern universe, that effect is small, I think.
But that must depend on the mass of the dark matter particle, right? I mean, you can have a very low mass, but then you can fine-tune the mass.
No, but it wouldn't be so different from the photons interacting with the residual electron fraction. Because we're talking about, for the Miller charge model, either the original one or the interacting one, it can only be at most like 10 to the minus 4 of the dark matter. Because otherwise, I mean, during the CMB era, it would look like more baryon, more electrons, basically. So that gives you a limit. It can't be much more than the baryon number density. So that's why it has to be a small fraction of the dark matter, and the Miller charge will be a small fraction of the electron charge. So I think it actually would be a smaller effect than the interaction with just with normal residual electrons.
Okay, thanks.
I have a question about the neutrino mass constraints. So do you have a sense of which redshift you're picking up most of the constraints from?
Yeah, so actually, so even though the signal goes up to redshift 50 and then starts to decline, the thermal noise goes up so fast with redshift that it's basically the lowest redshift that you include is where it's dominated. So we included in these results down to redshift 30, and we looked if you go a little bit higher. So basically the lowest redshift, the main constraint is just that around redshift 30 in many models, astrophysics begins to make a difference, and then it becomes much more complicated. That's the main issue. So yeah, so it's the lowest redshift that you can include.
I have a question about the long-range interaction. What is the length scale of the interacting self-interaction length scale? Megaparsecs?
Long range? Trying to remember. I think that's quite. If I remember correctly, I think that's quite flexible.
So I was wondering whether it has any effect on matter power spectra, like sigma tension or anything.
So the long range interaction would be between the Miller charge part and the dark matter. So you're saying that the dark matter itself would behave differently. Yeah, that's a good question. I mean, I'm not sure this. I'm not sure this was taken into account. I mean, it's not in any of these constraints. Yeah, well, that's a good question that should be looked at. Yeah, I'm not sure.
Last question.
Yeah, so in your dark ages power spectrum, you see these beautiful BAO features. So what will it take to detect these BAOs in the dark ages power spectrum?
So, well...
Is it feasible, or you have to cover half
So
the
you're talking
moon?
about this?
No, next.
For the BAO...
The dark ages.
Oh, you mean these BAO?
Yeah,
like
yeah.
Just these BAO. So, I mean... So from what we looked at, you're not extremely sensitive. I mean, if you notice that, the BAOs are very strong, right? Because what you're measuring basically the baryons. Now, over time, the baryons are catching up with the dark matter, and therefore the BAO signal in the baryons becomes weaker and weaker, right? So if you go to Redshift 30, it's a much weaker signal than
No, so it also depends on the bandwidth. If your bandwidth is small enough, then the BAO feature, but you lose sensitivity.
No, that's right. So we were averaging over all of them. But we found, so the way we see that it's not very sensitive is that if you take, we took fairly large K-bins, but if we took smaller K-bins, it didn't make much of a difference, which suggests that you're not really sensitive to the detailed shape yet. Of course, if you go, once you start getting to the deconfiguration and to very high, at some point you do get, very sensitive to that. So it depends, but not for the minimal kind of configurations here. Yeah, but eventually, of course, you would be able to do that.
Yeah, thanks everyone, and thanks the speaker. Our next speaker is Garrelt Mellema.
Okay, so we've heard a lot about observing and telescopes. We've heard about cosmology. So this talk is more about the astrophysics. I will be talking about a few things that I worked on with various people, and I'd like to thank them here. And I also included a picture of a water lily to please Leon. So what we'll do is, it's about large and small scales and how they connect. So we'll begin with the scales in cosmic dawn and reionization. And then I'll tell you about three essentially, so 2A, 2B, about how you produce ionizing photons inside galaxies and protogalaxies, and how small-scale absorption of ionizing photons in the ionized intergalactic medium is important. And then end with summary and conclusions. So reionization is sometimes said it's the last time that all the baryons in the universe got together and did something interesting. It's a large-scale cosmological event, but it's driven by small-scale physical processes. And those processes essentially are the production of ionizing photons, or X-ray photons, if you want to look at the heating. And that happens on very, very small scales inside galaxies and protogalaxies. And they produce the ionizing radiation and also the UV radiation that does the Lyman alpha coupling during the cosmic dawn. So those are the sources. Then on the sinks side, which is, I guess, is the process, we have, of course, the large-scale neutral hydrogen in the intergalactic medium. That's a large-scale distribution there where you create these big ionized regions. But once you've created those big ionized regions, inside them, there will be still absorption of ionizing photons through small-scale density fluctuations and small-scale absorbers. So those are the small-scale sinks. Now, if you want to simulate reionization, and you want to simulate, for example, to interpret your observations, you need to simulate it at large scales. So more than 200 megaparsec co-moving. So both because the H2 regions will get quite large. Also, if you look at the end stages, you'll find there's a picture here. Wait, sorry. This is the very late. This is 1% neutral fraction. So you see there are these rare neutral islands. In order to pick those up, you also need to have, this is 700 co-moving megaparsec across. And of course, this is sort of roughly the field of view of the interferometers that we're using. So in order to match the observations, you will also need large-scale simulations. Now you can simulate that with various methods. There's 3D radiative transfer, where I did most of my work with C2Ray. There's also CRASH by Benedetta Ciardi. That's quite time consuming, so maybe you can do paint one spherical ionized regions using 1D radiative transfer as developed in the Bears and Grizzly algorithms, or you can use very efficiently the excursion set formalism, which is most famous because of 21 centimeter fast by Andre Messinger, but there are several people here in the audience that developed similar codes. So these are all methods that have been used to do large-scale simulations. If you go slightly down in scale, you can do the coupled hydrodynamic simulations, but not yet at the scales where you want to reproduce the observations. However, all of these work on grids, and so you have finite resolution, and the small-scale effects that we need, the sources and the sinks, cannot be directly simulated in these radiative transfer simulations. So how do we deal that? Well, let's start with the sources. So obviously, and even for the hydrodynamic simulations, star formation has to be done with subgrid recipes. And so for these kind of radiative transfer simulations, for large-scale radiative transfer simulations for reionization, the classical approach has been, well, let's assume the amount of the number of ionizing photons being produced is proportional to the mass of the dark matter halos which contain the stars, or the galaxies which contain the stars. There's been in recent years push to make them slightly more advanced by adding a power law, but you can also choose the even more detailed way by combining semi-analytic models for galaxy formation, so-called SAMs, which rely on merger trees, and to combine these with, for example, excursion set formalism. So this was done in Australia with Meraxes, and in Groningen in Astreas. So there's a new player in this game, and that's called Polar, sticking to the Bears theme. And this is a combination of L Galaxies 2020, which is one of these semi-analytical models for galaxy formation and evolution, based on merger trees, with the Grizzly code that was developed by Raghu Gara. And so there's a paper by Qingbu Ma and Raghu where they show the first results of this code, and where you can then study how does your 21 centimeter power spectrum and UV luminosity and star formation history depend on the parameters of your semi-analytical galaxy formation model. So as a quick preview of this, here's a bunch of 21 centimeter power spectra. So against K, here's the delta 21 centimeter for at, I think, the midpoint of reionization in this particular simulation. And you see a solid line in each panel that gives the value for the fiducial value of the power spectrum for the fiducial value of these parameters of the SAM model. And then the dot dashed line is if you choose a slightly smaller, and the dashed line if you should choose a slightly larger value of that parameter. And so what you see is that for these parameters, there isn't much sensitivity to the choice of the parameters, but there's quite a bit of sensitivity when you change the parameters of the supernova feedback model, so it's very sensitive to that. I think this was also seen in previous semi-analytic modeling. And maybe not so surprising, the elephant in the room when it comes to this game, the escape fraction model makes a big difference. So this was just the first proof of principle, and we'll be using this in the future, potentially to derive upper limit results on future upper limits from LOFAR. Now, of course, those semi-analytical galaxy formation models are typically calibrated against low resolution, low redshift observations, and that's how you calibrate your parameters. But if you push into the cosmic dawn, or generally, I guess, into high redshift, those galaxies may behave very differently. So we've, in Stockholm, we've been working on a new ab initio model for early star formation, so star formation in midi-halos. And we're soon to submit a first paper on this, in which we present a new analytical model to calculate the threshold halo mass for efficient cooling, so which is the requirement for being able to form stars in those halos. So that includes the effect of the molecular hydrogen cooling, but also the various feedbacks, so it's Leimer-Werner feedback, photoevaporation feedback, including both of these, including self-shielding and the baryon streaming. And so to give you an idea, here's a picture, a figure where we show the threshold mass, halo mass, as a function of redshift for the case of no radiative feedback, so it's just about the molecular hydrogen content. And the solid lines are the model that we developed, where this is sort of the average value, this is the minimum, so the lowest halo mass in principle, and this is the highest one. And included in the model are many figures, many points from various numerical simulations that try to study this problem. And so we seem to actually capture most of these. There's also these lines are from a recent paper by Schauer et al., which is also numerical, but they provided some sort of line fits to their typical and minimum mass. And this Kulkarni model, which is a different Kulkarni from the one that's in the audience, which seems to be actually somewhat low compared to everything else. So the good thing is that this is a recipe that can be included in, for example, your simulation. So it's based on the merger tree. So if you have those, you can make an estimate on this type of early star formation. If you include the various types of radiative feedback, you have to assume something about the Leimer-Werner background. We took it from this paper, and the photoionization background, which we took from that paper. And then depending on the baryon streaming, so no baryon streaming, it's sitting on the no radiative feedback line up to 20, and then it goes up because of the Leimer-Werner feedback, and as you move towards the end of reionization, it jumps to the atomically cooling line, which is this one. And then photoevaporation, or I guess this actually makes it jump to up to 10 to the 9 after reionization. And of course, if there's baryon streaming, you increase the halo masses because the very lowest halo masses are unable to accrete baryons. Okay, so that was about the sources. Now we turn to the sinks, the other small scale. So we know observationally that ionizing photons can only travel a finite distance through the ionized intergalactic medium. And so here's a plot from Becker et al. That shows various measurements, historical measurements, which see, okay, so at very low redshifts, it's hundreds of proper megaparsec, but if you go to redshift 5, it's about 10 proper megaparsec. This seems to be some sort of power loss, so the expectation was that at redshift 6, maybe it would be 5, 6, 7 proper megaparsecs. However, the Becker et al. Paper claims that they measure a value which is much lower, so less than 1, well, within the error bars of 1 proper megaparsec. So this finite distance the photons can travel is because, partly because there is residual neutral hydrogen in the ionized regions because of the recombinations, and you have fluctuations in that due to the, I guess, the density fluctuations, but there are also these discrete absorbers, and it's the combination of those two effects that set this finite distance. Now, what is interesting is that we discovered last year that there is actually a dependence of the 21 centimeter power spectrum on the value of this mean free path. So what you see here is a plot at about 20%, what is it? It's, yeah, so that's about 25% neutral hydrogen left for various 21 centimeter fast simulations where we've used different values for this mean free path parameter, which is called Rmax in 21 centimeter fast, so 10, 20, 40, and 70 megaparsecs. And so what you see, if you look at the blue curve, this is for 10 co-moving megaparsec, you see that we have a very strongly K-dependent bias, the bias being the ratio between the 21 centimeter power spectrum and the matter power spectrum. Very strongly K-dependent, and then there's a sudden transition, and then it sort of becomes a linear bias, so almost scale independent. And you see this coming back, but the transition point shifts, and it shifts actually according to this relation, so T2 over R max. So there's a very strong dependence of this transition point on what is the mean free path for ionizing photons in the ionized intergalactic medium. So but what we're looking at here are low K values. So this is the large scale 21 centimeter power spectrum. But when the large scale 21 centimeter power spectrum starts behaving as, gets the same slope as the matter power spectrum, that transition point depends on the small scale effect of the mean free path. So there's another observable that comes into play if you think about the mean free path, and that is the UV background, which is often called, expressed with variable capital gamma. And here's a plot which shows as a function of redshift the values that have been measured, or simulated maybe, for this UV background. And so what is interesting is that you see for the highest redshift, redshift 6, there is actually also an observation which says that gamma is about 2 times 10 to the minus 13 per second. Now, if you go historically back to simulations that people have done, very many of them don't manage to reproduce this number. They overshoot it, sometimes by a factor of 10, which I think has been known, but sort of ignored. So we've been looking a little bit more at this, and here's a plot of the gamma value inside ionized regions as a function of redshift for 4 different reionization simulations in a large box. And here's his Calverley value. And so what you see, this is actually typical. The blue line is typical of the types of simulations we used to do, where we chose the mean free path to be about 10 proper co-moving parsecs, which means proper megaparsecs, which means 70 co-moving at redshift 6. And you see that we overshoot by a factor of 10, and this is typical. But then if you lower this mean free path value, and this is in a, I should have said, this is in a C2Ray 3D radiative transfer simulation, you actually do manage to hit the right regime, so 10 or 20, and then the behavior of how the evolution of these things depends also somewhat on how you implement this mean free path. So these green and brown lines, it's a hard barrier, as it is for the blue line, whereas in this orange line, it's more of a gradual absorption. So really, the models also really want quite short mean free paths, more consistent. These are the co-moving values. So more consistent with what was measured by Becker, maybe. And I thought it's actually possible to do a simple estimate of this. If you say that to reionize the universe, the collapse fraction, so the fraction of matter in dark matter halos, times some brightness factor should equal 1 plus the losses due to recombinations, which could be 2 or 3 or something. So that this is your condition. So if you had at a certain redshift reach this collision collapse fraction, then you have reionized the universe. Then you can evaluate what is the production of ionizing photons at that time, which depends on the time derivative in this very simple model. And then there's a relation between gamma and this anion. So given an anion and giving a certain mean free path, you can get a certain value of gamma. So very simple model. They can make it much more complicated, but it gives us a sort of order of magnitude idea. So if you want to reionize by redshift 6, you have about factor 2 for the recombination factor. So you need 3 photons to ionize all the one hydrogen in the universe. And the minimum mass for halos doing everything is 10 to the 9, and you use a Bresch-Schechter collapse fraction prescription. You find that if you want this low value of gamma, you actually need a very low mean free path. So this sort of explains why most simulations that used fairly simple models under the hood actually struggle to get this right. You do need to use quite short mean free path values. Okay, so currently we're working on how to best include this mean free path effect, so this absorption, in our numerical simulations. And it's important both to get the end of reionization right, to get the 21 centimeter power spectrum right on large scales, to get the UVB right, and also an effect that I have, or an observable that I haven't mentioned, but the Lyman alpha optical depths we measured. We know that, of course, a hard barrier, and this is often how it has been included in simulations, is unphysical. It's not that all photons get stopped after 10 megaparsec. You know, some get stopped sooner and others get stopped much further. So it should, plus that there should be I guess, both a redshift dependent and a position dependent in that. And so we're working on this and trying to also collaborate with some of these hydrodynamic simulations where this can be directly measured. Okay, that concludes my talk. So I told you about how large-scale reionization, of course, depends on small scales, where both the sources and the sinks are small-scale processes. And these need to be included using subgrid models in simulations of large-scale reionization. And I showed the first results of this polar code, which combines the Grizzly reionization code with this semi-analytic model for galaxies, L Galaxies 2020, and a new semi-analytic model for star formation in mini halos called Anaxagoras. On the sinks part, I showed you that the mean free path near the end of reionization can be quite small, and also has a considerable effect on the shape of the 21 centimeter power spectrum. And we're currently working on best ways to implement all of this in our numerical simulations. And I'd like to thank you and say happy birthday, Raman Research Institute.
Hey, nice talk. So for the mean free path estimation, I presume it will be also depend on the typical halo masses or the gas densities in the halos. So do you consider that option, like whether is this coming from a system which is extremely gas rich or heavy halo masses in comparison to other?
So the mean free path, I'm not sure that I understand the question. The mean free path is basically, so the photons travel through the ionized intergalactic medium. So how many they may hit a galaxy, which is contained in a dark matter halo. Yes. And that's, yes, so in that sense, the relation between this, people have worked on this for many decades, it's not entirely trivial. I mean, for example, you could make a very simple model where you say, okay, every halo is represented by its virial radius. If you do that, you get the wrong scaling with what the observations tell you. So it's not that simple. But yes, there is a relation, of course. Yes.
But is it taking something like which is depends on the masses, which is typically hitting, or something which is constant at all line of sights? Do you take it direction dependent or position dependent, or do you take it constant? Because I presume it will be position dependent. So.
Yeah, I'm not sure that we're talking exactly the same language, but yes, it will depend. I mean, a region that contains very many galaxies is likely to block more photons that are coming in from the outside. I mean, the mean free path effect we're talking here is in the intergalactic medium, so the photons come from somewhere else, sure. And they maybe hit the outskirts of a galaxy. Yeah.
Okay, but we can discuss this.
Yeah.
Thanks for the really nice talk. I had one question about your calculation, which was really great for the mean free path in terms of n dot. I was wondering if you consider clumping, because potentially that would introduce a factor of a few, right? So is clumping important, the C?
So the clumping, you mean in this model?
Yes.
So the clumping is in this factor, right? So because of the clumping, you have
Okay,
you
so you
boost the
absorb
number
it.
of recombinations.
So whatever, so if f brec is 2, then your C is something like some
I don't
square
know the
root.
relation
Okay, so,
between the two, but,
okay,
but
thanks.
there is a relation, yes.
Tirth?
So Garrelt, in this semi-analytical model for this ab initio star formation which you did, I mean, are you accounting for spatial relations in the sense, for example, when you are doing photoevaporation, it will depend where the galaxy is sitting with respect to other galaxies. So do you?
Yes, it is. It's dependent on the value of the local value. So I showed the model. The model I showed is for a. Sorry. So here we've chosen some average photoionizing background, right? But
Won't
yes,
it
you
depend
can,
on the reionization bubbles? And
yeah.
things
So
like that?
but this is the model is just you give it an external photoionization flux, and then it will tell you how this affects the
I mean,
star
not
formation.
only the flux, but also the inhomogeneities in the flux, right? With how many bubbles are there, what the sizes are.
Well, the model is per halo, right? So your halo is sitting in an environment, and presumably, so there's no. The model assumes an locally isotropic ionizing background. So it doesn't. It's not. It doesn't do like an ionization front that runs over the halo. It's supposed to come from. That's the model, but you can then change that variable and it will give you a different answer. Yeah. And so in a big simulation where you have lots of halos, you can have different answers in different locations.
So is the minimum halo mass same for the sinks and the sources? Or, I mean, for the sinks also you will have a minimum halo mass, right?
For the, well, the sink, yeah, so the sinks, that's actually a difficult, because some of the sinks could be just a filamentary structure in the IgM that you happen to hit where it's quite long, let's say, right? So then it's not a halo, it's actually a structure in the intergalactic medium. But yes, so the sinks, many of the sinks will be, let's say, the circumgalactic medium of galaxies. So, and yes, that depends then on how well they can retain their gas. And maybe also then the times how long a region has been photoionized.
So how do you implement it in your code? Do you have...
right now we're not actually... there's an earlier model that I developed with Hemant Shukla and Ilian Iliev, and there we picked basically the same type, so the same halos that were sources in that simulation, we assigned a certain opacity, let's say, in terms. But then we adjusted that to get the right mean free path, or what we thought was the right mean free path. But I think this is not entirely known a priori, how this, because I can imagine you still have halos that have stopped forming stars, but are retain enough gas to be sort of opaque, and so it would be a lower minimum mass. I don't think we actually know this. This would be, I mean, this should really be studied in coupled. So radiative transfer plus hydrodynamics and cosmological simulations, and maybe we can try to extract that information from there.
Yeah, no, just, continuing on this. So, I mean, typically one would associate a cross-section, right, with a, do you have some number or something like that? Or, I mean, for a whole sink, isn't it?
No, not at the moment, no. As I said, we developed a model where we tied it to the virial radius, or it scales with the virial radius, but I don't think we actually know that that sounds reasonable, but I don't think we actually know that that's the correct scaling.
Okay, thank you.
Yeah.
Okay, then let's thank the speaker again, and the next speaker is Suman Majumdar.
I would like to thank the organizers for allowing me to speak here about my work. So here is the list of my collaborators, and I will be speaking mostly about these two manuscripts that we have prepared together. And apart from this particular talk, there are 3 posters on bispectra, which were by Raghavendra, by Janki, as well as Chandrasekhar. So I would request you all to have a look at them. So before I start talking about 21 centimeter bispectra, I would like to say a few words about the place where I belong right now. So it's IIT Indore, and there is a department called Department of Astronomy, Astrophysics and Space Engineering, and it's a unique department in the IIT system, first of its kind. We, apart from a PhD program, which is running quite well since 2016, we have 3 master's programs. One of them is MSc Astronomy, the other 2 are MTech in Space Science and Engineering, and MS Research, which is a unique master's program in Space Science and Engineering. And we are going to start a BTech program in Space Science and Engineering since from this July 2023. And additionally, we are organizing the ASI meeting next week, so I hope to see many of you in Indore. So let's start. So this particular work that I'm going to present here has been done mostly by this PhD student, who was a former PhD student at IIT Indore, now a postdoc at Uppsala, Mohammad Kamran. So as Harald has already introduced, that the small scale physics essentially affect the large scale 21 centimeter signal that is coming from cosmic dawn and epoch of reionization. And I would specifically talk about the period when these 2 physical processes that go on in the intergalactic medium, that is Lyman alpha coupling and X-ray heating, are dominant. So they affect the relative population density of these 2 levels in neutral hydrogen, and that results in that essentially results in the fluctuations in 21 centimeter brightness temperature. So I will try to argue that using 21 centimeter bispectrum, you would be able to disentangle which one among these 2 processes are dominating. So that's more or less the motivation to essentially disentangle the Lyman alpha coupling and X-ray heating's impact on the 21 centimeter bispectrum coming from cosmic dawn. So as Harald has already mentioned, that the astrophysics part comes from here, rest is cosmology, more or less. So astrophysics essentially affect the spin temperature as well as the neutral fraction, which is space and time dependent. So the usual way of quantifying the fluctuations in 21 centimeter brightness temperature that we have already heard quite a bit is 21 centimeter power spectrum. And it essentially gives us the variance at different length scales. And it can describe a field completely if the field is a Gaussian random field, a pure Gaussian random field. However, I would like to argue that the 21 centimeter signal that is coming from cosmic dawn and as well as epoch of reionization is highly non-Gaussian because of, again, astrophysics. And this non-Gaussianity is intrinsic, first of all, because the sources that produce this X-ray, Lyman alpha, as well as UV photons, they are not necessarily randomly distributed. They are located at biased regions in our matter density distribution. So that's why it's intrinsic as well as time evolving, because how these sources behave, that changes with time, and the photons produced by them that essentially affect the intergalactic medium differently as the time progresses, as cosmic dawn and EOR progresses. So the next thing, if you are dealing with, there are various other ways of quantifying this non-Gaussianity, but if you are dealing with Fourier statistics, the next obvious quantity that you would like to calculate, if you have an observation, is 21 centimeter bispectrum, which is nothing but ensemble average of Fourier transform of the sky brightness temperature at for 3 K modes, which form a closed triangle. So you essentially have 2 free parameters in this case, K1 and K2. K3 is dependent on the other 2. So, and I would like to, as I said repeatedly again and again, that it contains probably more information compared to the power spectrum, because power spectrum cannot capture the non-Gaussian information that is there in the signal. And additionally, we will see that the bispectrum simply because how it is defined. If one of these quantities are negative, the bispectrum can be negative, or three of them are negative, then also bispectrum can be negative. So that's why bispectrum has a sign. However, the power spectrum by definition is always positive. So that is another, let's say, clue that bispectrum provides us, and we would like to use that information. And for this particular work, we have focused mostly on squeezed limit bispectrum, where two of these K modes are equal to each other and the angle between them is close to 0. So K3 tends to 0 with respect to K1, K2. Definitely the results I will present here, K3 has a finite value. K1, K2 also have a finite value. And I would like to focus only on the large scale squeezed limit bispectrum. So I would particularly focus on K close to 0.1 to 0.2 MPC inverse. K1 and K2 equal to 0.1 and 0.2 MPC inverse. And why did we choose this particular shape of the triangle? Because as you can imagine, there are various shapes and sizes of the triangle can be possible. Precisely because we have shown earlier that the bispectrum has a maximum magnitude for UR as well as for CD for this shape of triangle. And additionally, Rajesh Mondal and Himanshu Tiwari, they have independently shown that it is possible probably to detect the squeezed limit bispectrum that has the highest detection probability thanks to its very high magnitude with thousands hours or more SK observation. And so the hope is if this squeezed limit bispectrum can have some sort of information about the large scale IGM physics, then we can say something about which IGM process is dominating at what cosmic time. That is the goal of this particular project. So to set up the signal, essentially we used a 1D radiative transfer code called Grizzly, which is developed by Raghunath Ghada, who is a postdoc at Open University of Israel. And to set up the problem, we had essentially defined 4 different models for our cosmic dawn. In the first 3 models, model A0, A, and B, we assumed that one of these 3 processes dominates. In the 4th model, all 3 processes are included self-consistently. This is because we would like to understand what kind of impact each of these processes has on the bispectrum, or features of bispectrum to be more precise. And based on that, those features, then we would be able to recognize their signature on this most realistic model one. That's the goal. That's why the problem has been set up like this. So, yeah, this is again bispectrum. So let's start. So for model A0, there is only Lyman alpha coupling. There is no X-ray heating. There is no ionization, etc. So you start to see these kind of small Lyman alpha coupled region forming around the very first halos that are formed in the intergalactic medium. So, okay, just to be clear, this is the late stage of cosmic dawn and this is the very early stage of cosmic dawn. And we kind of stopped our simulation by the time IGM is 10% ionized because we didn't want to complicate our conclusions by including EOR. We wanted to restrict it only to the cosmic dawn, let us say. And so if we look at the bispectrum for this particular model, this is higher redshift. As we go from high to low redshift, we see that the amplitude of the bispectrum actually increases. It's negative and it increases and it kind of saturates and then goes on. So why this is so? We can understand it by using a very simple toy model. So this model has been discussed in various papers by Bharadwaj et al. And etc. But this was specifically to describe the signal from a heated IGM where you have, let's say, non-overlapping ionized region distributed. So what you will have for a single essentially ionized region in a uniformly heated and neutral IGM, you will have a window function with a negative sign in front of it. Now imagine that there are many such ionized regions, so they will be, and they are non-overlapping, randomly distributed, so that will give rise to the summation over their centers locations, e to the power ik dot r. So we can use this as an inspiration to build our model. In case of when we have only Lyman alpha coupling, let's say there is a Lyman alpha coupled region around the source, the isolated source, and the background is cold. Lyman alpha coupling has not happened there, and also neutral. So it is essentially a weak negative background on top of which you have a negative signal, a strong negative signal. So the large scale signal or brightness temperature fluctuation in Fourier domain would be negative. So that is precisely what we see here. And as these Lyman alpha coupled region gradually grow in size, you essentially see the amplitude of this signal to increase. Okay, so the next model where we have Lyman alpha coupling plus photoionization, there is no X-ray heating, we see that the bispectra, which is now for the model A, is represented by this red dashed curve, kind of follows the black solid line up to a point, let's say redshift 13 or so. So up to that point, essentially Lyman alpha coupling is still the dominating physical process, and that's what determines the sign of the bispectrum. Then we see a sign change. Bispectrum changes from negative to positive. And why does this happen? Let's go back to our toy model again. So now, because you can see Lyman alpha coupling kind of saturated, have saturated. So it's a strong negative background on top of which you have created some ionized region, because ionized regions are forming now. So these isolated ionized regions on a strong, on a cold Lyman alpha coupled and neutral background will give essentially a large scale positive signal in terms of 21 centimeter fluctuations in Fourier domain. So that will lead to this sign change, and that's why you will get a positive bispectrum here. Now let's go to the third model, which is where we are including X-ray heating, but we are doing something unusual. We made the IgM, Lyman alpha saturated, even before the sources were born. So it's a Lyman alpha saturated background on top of which you have your sources which are producing X-ray photons. Now they are essentially creating heated regions around them on a strong negative background. And also we have ionization as well in that. So the bispectrum now is represented by this purple curve, starts as a flat negative bispectrum, because that's what is expected from your Lyman alpha saturation. So, and then it changes sign first at a very early redshift, kind of around redshift 15 or so. And that is because of the fact that on a strong negative background, now you have positive, let's say, you have a positive, heated region. So that will give you a overall positive fluctuation in Fourier domain. And that remains so for certain time until these heated regions start to merge together. So once they percolate with each other, the entire kind of IgM becomes more or less heated. You still have some low density regions which are in absorption. So now the fluctuation is dominated by these small leftover low density absorption regions, and on a heated, bright heated background. So that will effectively be a negative signal. These are Lyman alpha coupled low density regions in a positive background, heated background, that will give you a large scale negative signal. So that essentially leads to this negative, this second sign change in the bispectrum. Then it gradually actually decreases in amplitude, because first these Lyman alpha coupled regions also gets heated eventually, and then ionization takes place. So ionization now is happening on a heated background that we have already discussed earlier, that will give me a negative signal. So the bispectrum still remains negative. So now our most realistic model, model C, which is represented by this green dashed line, which essentially follows the curve which was A0 and A, where essentially Lyman alpha coupling has not saturated to start with, but it gradually kind of follows them. But you can see there is a difference in amplitude. And the difference in amplitude is there because X-ray heating has started now self-consistently. So there is a basically tussle going on in between Lyman alpha coupling and X-ray heating. And that's why, but for the same reason, after a while when X-ray heating wins over, it shows you a sign change here. And then when the heated regions again start to percolate together, you get another sign change here. So this dual sign change still remains, though the broadness of the peak kind of disappears. And later on, it again follows more or less the model B that we have discussed earlier. So one can say that from these features directly and from the setup of our problem that the coupling was the dominating factor on the left side of this vertical black line. Lyman alpha coupling was the dominating physical process, and heating was the dominating physical process on the right hand side of this curve. And this in principle can also be seen to some extent in power spectrum, but not necessarily very clearly. This dominance of Lyman alpha coupling over X-ray heating, and when X-ray heating dominates over Lyman alpha coupling, the transition can be seen to some extent here, but not very clearly, simply because of the fact here the features are less and here features are more. So bispectrum is a kind of better probe to distinguish the dominance between these two processes when one actually is dominating over the other. So that is kind of the conclusion, but someone may ask the question, okay, what about the bin size of this K mode, or how robust these results are, right? So let us look at a few other K modes. So 0.16 MPC inverse, 0.23 as well as 0.34, and that implies the K3 value is also changing, and it goes up to 0.11 MPC inverse, and you see more or less the same feature, almost the same magnitude. And I would like to add that all of these bispectral calculations were done after subtracting the mean of the signals. So this is something I would say to some extent realistic, not necessarily fully. And further, one may ask that, okay, what about if you change the source model? What happens then? If you change the source efficiency, if you change the minimum halo mass that can host your sources, fine. So we change the X-ray production efficiency, and we change the minimum halo mass that can host these first sources of light. What we see is that the features and more or less the amplitude of bispectrum more or less remains same. The only thing that happens when you increase the X-ray production efficiency, the features appear at an earlier cosmic time. That's it, nothing else. And similarly, if you increase the minimum halo mass, it gets shifted. Everything gets shifted to the right-hand side, that is at a later cosmic time. That is what one would expect. So these features are actually generic, and they're quite robust. Okay, so that's more or less a summary of my talk. So you can use these features in bispectra to distinguish between these two processes, which one is dominating when in cosmic time, and probably these features can be used as a confirmative test if it is at all possible to measure the signal using radio interferometers after a power spectrum detection has been done. And the moral of the story is that here we are looking at the signal fluctuation. So it's important to understand what is the background, what is the background of that signal. It is not necessarily CMB, but what is essentially driving the fluctuation. It is whether it is a heated region on a cold background, or a cold region in a heated background, or a cold region in a less cold background. All of those things actually determine the sign of the signal fluctuation, and that determines the sign of the bispectrum. And that can tell you essentially something about the IGM physics that is dominating at that particular cosmic time. Okay, I'll stop here.
Thanks, Suman.
Can you show this figure where the dominant component is Lyman alpha coupling and hitting the two regions here? So if you plot the global signal, wouldn't be like the peak of the negative will be the same position as?
That I do not know necessarily, because as I said, it is about the fluctuations. So what is the background, and on top of which what component is essentially driving the fluctuation. We have that plot.
Okay, means if you overplot it, means the negative is?
Not necessarily. I don't think that is necessarily always correct. I have to check. I have not done that. Yeah.
Thank you. Do you know what we need to detect this with the scale?
Yeah, so that you should ask Rajesh. So he has written a paper.
For discussions.
Yeah. So he kind of claimed that a 5 sigma detection is possible for here in his 2022 paper, where? Yeah, here. So he mentioned a 2021 paper that a 5 sigma detection is possible for squeezed limit bispectrum. So not all shapes are detectable, but the squeezed limit is, because the magnitude is quite high.
Tirth?
So since we are discussing detectability, do we know what is the bispectrum of the foregrounds?
No, that is.
So that will decide,
yeah,
no?
Yeah.
I mean.
And okay, so I think that there will be also a wedge-like structure, but it is more complicated. So one can think of, if at all it is possible to avoid that. So that's why I showed that plot where we actually varied the K mode and kind of luckily retained the shape of the bispectrum. So if you have to throw away lots of K parallel modes, so maybe you will throw away all the K modes that are below probably 0.1 or something like that. Yeah. Yeah.
The variance of the,
Yeah, yeah. Yeah, foreground should have a wedge-like structure, but it is more complicated, I think.
Hi, Suman. What determines the amplitude of this bispectrum?
The brightness temperature fluctuation, so which is essentially the contrast between, let's say, the features, whether it depends on at what time you are looking at. So if the fluctuations are dominated by, let's say, cold patches in a heated background, then the size and distribution length scale of those cold patches will determine the amplitude of bispectrum.
Won't that be a bispectrum due to the Poisson fluctuations, etc.?
No, because this is a diffused signal, right? It is not points.
Point sources.
Yeah.
Okay, I understand. I'll speak to you later.
Yeah.
Any more questions? Yeah.
So, do you think there could also be a dependence or sensitivity to the spectral slope of the X-ray heating? So whether the heating is more, the heated regions have sharp edges or kind of softer edges?
I think still that, okay, that might determine how quickly the heating basically gets saturated. So I think then the broadness of these peaks probably will change to some extent, but we have seen that to some extent here, essentially, when we increase the X-ray production efficiency, still the features more or less remain same. Yeah, the broadness of the peak actually changes. So you can constrain probably to some extent the source X-ray source properties by looking at these features. Most likely, I've not done anything related to that. Yeah. I'm speculating.
Okay, then let's thank all the speakers for this session. Let's start our next session. So our speaker here is Girish Kulkarni.
Okay. Yeah, I hope everyone can hear me. Thank you for inviting me today. What I want to do in this talk is talk a bit about what we know about reionization without doing 21 centimeter. 21 centimeter is something we've been hearing all day. So I thought we'll continue to talk about reionization, but maybe get away from 21 centimeter for half an hour or so. So in the last few years, I want to argue that there has been a sudden burst in our understanding of reionization. And this understanding has gone into a direction of very interesting concordance, where a very wide range of observations from the epoch of reionization seem to be explained by the same model. This has never happened in this field before, and so that's why this, in my opinion, is a bit noteworthy. So this is work that I have been developing in the last few years in collaboration with several people whom I have listed here in alphabetical order. But I do want to highlight really nice work by my students Shikhar Asthana, Shikhar Mittal, and Sindhu Satyavolu, and my postdocs Janaki Raste and Thomas Soltinsky here. Janaki also has a poster outside on some of this stuff. So please go and take a look at it. So. So I think, as I said, the question really I want to pose is, what do non-21 centimeter observations tell us about reionization and cosmic dawn, right? And the conventional thinking in this matter is to look at a plot like this and argue that the great thing about 21 centimeter signal is that it starts giving us information at the redshifts where other probes of reionization stop, right? The conventional story is that Lyman alpha forest and all those very nice things don't work at redshifts precisely where 21 centimeter works, and as a result 21 centimeter is great. But what has happened really serendipitously in the last few years is that this story has broken down, and suddenly we have discovered that the non-21 centimeter stuff also has amazing amount of information, and so that's something I want to highlight in this talk. Okay, and so the probe par excellence of the intergalactic medium and reionization, in fact the thing that tells us that reionization has happened, is the Lyman alpha forest. Many of you know what Lyman alpha forest is, but some of you might not. So the idea basically is to find a very bright source at a cosmological distance and then observing through a very expensive telescope and spectrograph, so that you can have a very high resolution spectrum of it. And when you have a configuration like that, thanks to the expansion of the universe, the spectrum can encode information about the thermal and ionization state of the intervening matter. And so this is an example. What is shown in this plot here are two quasar spectra. Quasars look basically the same no matter what redshift they exist in, and so this top panel shows a quasar at a very small redshift. I think this is redshift of 0.1 something. The bottom panel is a quasar that is located at a cosmological distance at a redshift of about 3, and you can see that broadly the continuum shape of the spectra are similar. You have a flat continuum with these Lyman alpha emission line, but then immediately you spot that the lower quasar has much richer features in its spectrum, and these are the Lyman alpha. These are interpreted as the Lyman alpha forest, right? These are interpreted as lines produced by the Lyman alpha transition of the intergalactic hydrogen. And as soon as you do that, if your spectrograph is nice enough, you can actually resolve these lines and measure things like the ionization fraction and the temperature. And so it's this experiment, it's this amazing technique that tells us that the universe is hot and ionized out to some redshift, right? But then, of course, the story is, and this is the motivation for building 21 centimeter experiments like SKA and so forth, is that this amazing technique breaks down at some point for a variety of reasons, okay? Really unfortunate reasons, but it does break down. And so an example is actually here. These are the first Redshift 6 quasars that were discovered thanks to the Sloan Digital Sky Survey by Xiaowei Fan in 2006. And you can now look at the spectra of these quasars and notice that the spectrum bluewards of the quasars Lyman alpha emission is nothing like the spectrum that I showed on the previous slide. In fact, here you see almost complete absorption in all these spectra bluewards of the Lyman alpha line. What that means is that you no longer have individual lines to resolve. No matter how good your spectrograph is, you are not going to be able to measure neutral fractions and temperatures anymore. This is just one reason. The other reason, of course, is even though it's saturated, it's completely absorbed, you can't even that doesn't tell you much. Because the Lyman alpha cross section is so large that even complete saturation doesn't tell us whether the universe there is neutral or not. And so this really is a big problem. To just pile on the misfortunes, there are hardly any quasars at high redshifts. There's very few objects to do this experiment with, right? So then, of course, the next best thing after the Lyman alpha forest is the CMB. But then CMB gives only integral information. So that has its own issues, right? And so this, of course, is the story of 21 centimeter, right? But then in 2015, there is this amazing observation that came up, which kind of changed the story. And this was a measurement by George Becker, where he showed that the Lyman alpha forest at around redshift of 5.5 has a very amazing property that it changes from point to point on the sky very significantly. So here's an example where these two spectra show Lyman alpha forests at exactly the same redshift. The range is shown here, but then they are very different. In the black curve, you see a ton of transmission at these redshifts, but in the red, it's very highly opaque, very highly absorbed, right? So clearly, these 2 points on the sky are very different. You can quantify this difference by defining a mean transmission. This is just sort of, you just pick a length scale, which is chosen to be usually 50 co-moving megaparsecs over h, and then you calculate the average of the transmission over that range. It's just a way of quantifying this. It can also be usually quantified as the negative logarithm of that quantity and then written as an effective opacity. And when you do that, you can actually see this actually in a statistical sense. So here is that sort of negative logarithm of the mean transmission, the effective opacity. These are all the measurements that were available until 2018 between redshifts 4 and 6. And you can see that at around redshift 4, almost all the measurements are very similar. The mean transmission there is maybe just a factor of 2 scatter from point to point on the sky, but as you move to redshift 6, the scatter is huge. There's a factor of 500 scatter in the mean transmission in the Lyman alpha forest. The Lyman alpha forest really varies very dramatically as you go to the high redshifts. And indeed, in the discovery paper, George Baker immediately pointed out that this cannot be explained by the normal density fluctuations in the universe, right? And this is a plot which shows this. What is shown here is 4 redshift bins, and in each redshift bin, we are showing the cumulative distribution function of this effective opacity. So you can see that at low redshifts, the spread is very little, but at high redshifts, the spread is a lot. And the gray band here with the dashed curve shows the spread you expect from just normal density fluctuations. And you can see that at high redshift, that just does not explain the observed fluctuations. So then immediately, there was a lot of effort in the literature to figure out what else might be going wrong here. And the effort was directed by the observation that the tau is related to the neutral hydrogen density, but the neutral hydrogen density is set up by a very nice combination of the gas temperature, the gas density, and the photoionization rate. Okay, the photoionization rate is setting the neutral hydrogen fraction, the total gas density is setting the amount of gas available, and the temperature is setting sort of the absorption coefficients involved in the atomic physics. Now, obviously, if tau is showing large fluctuations, you could have large fluctuations in T, delta, or gamma. But none of these ideas worked. Every one of these fluctuations had issues. Temperature fluctuations required too high temperatures. Ionization rate fluctuations required very small mean free path. And then there are some other solutions, but again, those had issues as well. And in the meantime, we were developing techniques of doing very high dynamic range simulations of reionization using a beautiful algorithm, which was actually discovered in the 1970s, called the M1 closure, which allows us to solve many of the problems that Garrelt Mellema highlighted in his talk. And I won't spend too much time on this, but essentially what we do is we can construct these really high dynamic range boxes, which can uncover these small sinks that Garrelt pointed out in his talk without sacrificing on the box size. And then when we did this, we could come up with reionization sort of scenarios which look like this, where for those of you who work on reionization, this is the usual story of how bubbles form around sources at high redshift, and these continue to grow as the radiation builds up, and then eventually they overlap and form a uniform background. Okay, so this is the ionization and this is the temperature. I won't really wait until it finishes. You all know the ending. But then what was really remarkable is that these simulations we discovered was that if you did a few things right, and only a very few things right, they actually were the first models to match that amazing spread in the effective opacity. And so what is shown here, again, is the distribution functions of the tau effective in red, and then the blue shows this model. What was remarkable about this was that this model was very different from not only what we expected, but almost every single model that speakers of today's talks have drawn on their slides. What was happening here was that to get the Lyman alpha forest right, it turned out to be critical to have a really late reionization, where the midpoint of reionization is at redshift 7, and the end is at much later than redshift 6. It's actually at redshift 5.3. And so at redshift 6 and even below, you have these really long-lasting 100 megaparsec long neutral hydrogen islands in the universe was the prediction. This is in fact how the universe looks like according to this simulation, and we have been spending a lot of computing time in the last 4 years sort of poking into this picture and trying to break it down without really succeeding in doing that. So what you see here is a light cone of the neutral hydrogen fraction, the temperature, and the photoionization rate, and you can see these long-lasting islands below redshift 6. Now, what was remarkable was not just the lateness of reionization. What was remarkable was the concordance, and this is something I really would like to convey to you in this talk. What it turns out that this shift in the reionization redshift from 6 to 5.3 is exactly what you need to sort of make sense of a lot of disparate observations at those redshifts. Here is a sort of parade of a few observations. So here what we show is the optical depth to the last scattering surface, the Thomson scattering optical depth. In red is shown the Planck result, and the blue is the simulation. Here again, the blue is the simulation, and various points are various other ways of estimating the neutral hydrogen fraction, such as the Lyman alpha emitters, the quasar damping wings, and the Lyman alpha forest dark spectra. And you can see that this is all matching with that picture. That was what was the real excitement, right? In fact, things continued to get very encouraging, because then we made the model face even more stringent tests. So the next thing was to look at the two-dimensional structure, the distribution of galaxies around these troughs, and to see if the density structure around these troughs matches with what we see in the simulations, and it continued to match, right? So here, for example, is a number density of the surface density of Lyman alpha emitters along these long sight lines, and blue shows this simulation. And it really has a lot of physics to tell us when a match like this happens. The Lyman beta forest was the next thing. Luckily, Lyman beta forest measurements became a reality around this time. This is 19 measurements. By now there are 50 Lyman beta forest opacity measurements. But you can see already that within 19 there is a very nice agreement between this Lyman alpha forest inspired model, a late reionization model, and what the Lyman beta opacities look like. Just to continue this parade a bit, and then the point is not to show off the calculations that this simulation can do, but really to show this amazing concordance that results from this, is the Lyman alpha emitter luminosity functions. This is a complicated plot. I won't go into the details of this, but I can talk later if someone's interested. But the point of this is that across the redshifts where the Lyman alpha emitter luminosity function has been measured, it distinctly shows a preference for these late reionization kind of a scenario. In fact, we got almost a 250-hour allocation on the VLT. It was the largest observing time on the VLT in the history of VLT telescopes to verify this picture. And then we got a beautiful measurement of the CDFs, the opacity in about 30 very high quality quasar spectra. These are shown in the red, and the blue is the simulation that I have been showing, and the picture continues to hold really well. This has some implications. So one implication that is perhaps worth highlighting in this meeting is for the 21 centimeter power spectrum. And so the one thing that it does is it pushes the 21 centimeter power spectrum to low redshifts, right? So here is the conventional model. What is shown here is the power spectrum as a function of redshift with all the upper limits that we have heard a lot of throughout the day today. And then you can see that the preference for this Lyman alpha model inspired picture is towards higher frequencies. And perhaps that's really a thing to be thankful for, because at lower redshifts and higher frequencies, you have greater opportunities to cross-correlate. There are more alternative observables to cross-correlate with. Also, higher frequencies are a bit easier to work with than lower frequencies. So perhaps this is actually a good thing. I'll go through a few implications beyond the 21 centimeter. So one such thing was we have computed the cross power spectrum of the 21 centimeter with a Lyman alpha emitter survey using the Subaru PFS, which is now turned on, working, and we have managed to come up with sort of numbers that are required to be able to detect this cross correlation at redshift 5.5 or so. The large dynamic range of the simulation now allows you to compute the B mode. So this is something we heard about yesterday. What is shown here is the B mode induced by the reionization. This simulation is shown by the red curve. There are a lot of curves here, but I think what you should focus on is the family of curves which sort of have this shape, and that shows the various reionization model that CMB community looked at through the last decade. And it's nice that we have a sort of we have something robust to tell that community now from the Lyman alpha forest side. Some more interesting things, we can now compute more robustly the 21 centimeter forest signal expected, which is really fortuitous because now I think the radio loud quasar numbers are of the order of 70 at redshift 6. And so this is really an opportunity that I'm excited about to potentially try and detect these neutral islands in 21 centimeter absorption. Of course, this depends on the unknown temperature of the neutral regions, which we don't know really. I won't go too much into this, but basically this late reionization now really strongly affects all the warm dark matter constraints derived from the Lyman alpha forest, because the lateness of reionization changes the thermal properties of the post-reionization IgM. As a result, the small scale power spectrum of the Lyman alpha forest is affected, and therefore there is a systematic bias in the observations, in the inference of the warm dark matter particle mass from the Lyman alpha forest. This is of the order of a sigma at the current data quality. This is something that it's possible to compute now. Thankfully, we have managed to come up with some sort of semi-numerical prescriptions to fold that in. Right. There you go. I want to talk a bit about cosmic dawn, but before I do that, I want to highlight some issues that we have trouble with. Before the talk starts looking like everything's going really well with reionization simulations, there are a couple things that now are opened up. The couple questions which are very interesting are opened up with this success of matching to the Lyman alpha forest. And the first one that we really don't understand is the sources that are required for these simulations. So what is shown here is the number density of photons which are pumped into the intergalactic medium by sources. And this really is an inference of these simulations. This really is a prediction. And that shape doesn't make any sense. It's not clear why that shape should be like that. There is one paper which argued in favor of a photoionization feedback induced model, which kind of managed to get something that looked a bit like that. It's not clear if that's really a sensible model. The problem is this is a hard problem to solve because this is really the escape fraction problem. So it's not like the throwing James Webb Space Telescope time at the problem will measure this. It's not clear how to solve this problem. So this is one question that this opens up. The other thing is very interesting. It appears now that even though the Lyman alpha forest measurements that I used in this story were only out to redshift 6 or so, because the photons that you produced a bit at higher redshift hang around for some time, because the horizon size of photons is large enough, the Lyman alpha forest at redshift 6 actually tightly constrains your ionization fraction out to redshift 7, almost 7.5, okay? But the problem is, it doesn't constrain the temperature. And so we are now in a situation where we understand the ionization fraction evolution from 7.5 to 5 really well, perhaps 7.5 to 0 really well, but we don't understand the temperature at all. So what we have been doing is running a large suite of simulations covering the thermal parameter space, and it's not clear what the solution for this is. There's some ideas, perhaps this is where 21 centimeter is the only solution. I want to end very briefly by quickly talking about the non-21 centimeter aspects of cosmic dawn. We haven't had much discussion about James Webb Space Telescope in this meeting yet, at least. There is a lot of things we are learning from the JWST about the cosmic dawn. One amazing thing is, of course, at the higher redshift end of the epoch of reionization, all this nice story about the Lyman alpha forest doesn't really work. And there, indeed, it might just be the 21 centimeter that will tell us how reionization happened. Of course, we have heard the story of edges and the amazing work from the Saras people, and I am part of the REACH collaboration with Anastasia and others, and we are sort of very excited for the data to arrive this year. We've also heard from talks such as Rennan's and Rishi's that the 21 centimeter signal acts as a very precise cosmic thermometer, and that's an aspect worth keeping in mind. Anything that you do to the cosmic thermal evolution really leaves signatures in the spectrum. But what I want to convey here is something cool that has not been appreciated too much in the community, which is that this makes very strong predictions for the JWST. Indeed, what we have found is that the observed 21 centimeter, global 21 centimeter line profile can be inverted analytically to actually read out the number density of galaxies that create the Lyman alpha and X-ray background that produces the signal. In fact, this is what you are seeing for the edges case here. What is shown here is for a range of JWST surveys, some of which have already begun taking data, what we have computed is the excess galaxy number that you expect relative to a straightforward extrapolation of the galaxy number count at low redshift. If edges is the right measurement. So in other words, if edges is actually produced by Lyman alpha photons and X-ray photons produced in a familiar mechanism from familiar galaxies, then the galaxy number count had better be much higher than than our normal extrapolation. And this is a very, very straightforward falsifiable prediction for JWST, which I really find exciting. But somehow it's very difficult to convey this radio information to the JWST community. Anyway, I hope I haven't taken too much longer. I want to end here. I really want to emphasize that there is this amazing convergence in our understanding of the reionization for the first time in the last 3 or 4 years. And I think the main thing to take away, perhaps for the speakers from this morning's talks, is when you make your slides the next time, please show reionization ending a unit redshift lower. And I think this is a lot of interesting implications. And I think I should have added a fourth point that I think we really should, it would be great if we could somehow think more about the JWST 21 centimeter connection and see what can come out of it. I'll stop here. Thank you.
Thanks, Girish.
Thanks, Girish. This was really interesting. I have a couple of questions, maybe related. When you showed your n dot sources and you see that it looks strange, have you tried looking at the AGN luminosity function? Because they've been calibrated for a range of X-ray to, and you have bolometric. And wouldn't that kind of, when you integrate it, give you a sense of how this shape will look, and does it match? And the other question I have was, how are you able to say something about this recent, now I don't know how recent it is now, but Rohan Naidu and others were looking at this oligarch scenario of reionization, like massive dominated. Is it consistent or?
So the first part of the question, we have spent a huge amount of effort. Actually, I spent 5 years calculating this green curve here. So the AGN number counts do this to the ionizing emissivity. So it doesn't really help with that blue curve. So there are too few AGN as far as we can tell at those redshifts. The second question, yeah, I haven't yet managed to digest those papers. Yeah, there are a lot of interesting ideas. It will take some time to figure out what the
They claim they match all these things, so that's why.
Yeah.
Thanks.
Yeah, Leon?
So we talked about it a little bit, right, about this inversion. I think it's quite interesting, this prediction for JWST, because, right, I mean, even a few years ago, if you would go to a meeting and, right, people said, well, right, it takes the entire lifetime of JWST to find a galaxy at redshift 15, and then, right, within the first few weeks, there might be one at 17, right, which means that the density of these objects, if confirmed, is much, much higher than what we think, right? So, right, there might be something in this. Of course, right, we also need to confirm the edges signal still, and the JWST.
What's really nice about it is you can do this inversion on null measurements. So it would be very interesting to do this on Saras as well. That would itself make some predictions, right?
Yes.
I don't know what they might look like, but I think this is actually the elegance of the inversion I really liked. It's very, very nice, very simple.
But if you now take this one and feed it back to the simulations to do the power spectrum, have you done that, or have you talked to people to say, okay, now I know this excess, so I can use this as a starting point, as an input for power spectrum predictions? It might be very interesting to see what comes out.
Yeah, that should be interesting. Yeah.
Thanks.
Yeah, thanks.
Girish, in these simulations, the M1 closure is an assumption, right? I mean, do we have any understanding whether that assumption, I mean, how dependent the results are on this assumption, whether that creates any bias? How does it compare with other methods of radiative transfer?
Oh, yeah. We have worked a lot on that question, so I can talk to you outside for a long time, actually. Yeah, so I think the answer there that I can say is basically until full overlap, the M1 is a very accurate method. It matches very well with not only ray tracing, but also with even intuition from excursion set type methods that you have been working on. The M1 method has problems after overlap. So after overlap, it can be 20% inaccurate in the photoionization rate distribution. And so the Lyman alpha forest predictions from these simulations after overlap are potentially problematic. But it appears that the simulation is very robust out to redshift of 5.3 in this picture. But
at 5.3 or so aren't.
So what happens in M1 approximation, the radiation becomes a fluid. As long as there is one neutral island left in the box, M1 is accurate. As soon as that goes away, radiation starts behaving weirdly because there is sloshing effects. And so as long as there is a last bit of obstruction in the fluid, it seems to work quite well, as far as we can tell. Indeed, this picture seems to hold very well now in a range of simulations, including your own simulations, which don't use M1. So that's encouraging.
with the late reionization, the warm dark matter constraint will be stringent or will be relaxed intuitively?
Yeah, so with late reionization, what happens is, so that's slightly it's a complicated question, but I think what happens is that with late reionization, the gene smoothing is less, so the constraint is relaxed by a sigma. Yeah. So it's a complicated combination of the gene smoothing being smaller, but then the temperature fluctuations being very large because they haven't yet died down. And so it's a combination of those two. It's
so you have to see
very
which
hard
one
for me to
wins.
recall exactly which direction the combination went. It goes in some direction in one sigma. In either case, it's probably something to be corrected if it's one sigma.
So I had a question about the same plot that Hamza had a question about. So the green curve due to AGN, does that take into account the fact that there's a lot of axisymmetric obscuration very close to the accretion black hole, and also star formation regions are co-forming in the circumnuclear environment, which will also obscure?
No, so this just assumes two things. So this is just type 1 AGN. But then the universe is isotropic, so any point will see as many type 1 AGN as us. So a quasar might be obscured for some other observer, not for us, but that for that observer some other quasars might be unobscured.
But that like affect the numbers that we know, right? So
It
you mentioned
affect,
two.
right? And because of isotropy, it would be really weird if the obscuration fraction changes from place to place in the universe.
No, I mean the total numbers, because you mentioned very few are known.
Right.
In that context, it would affect that number.
It shouldn't. No, this number should be correct. Unless the observations have a systematic error that I don't know, these numbers should be correct. Yeah.
Last question.
I wondered in this the radiation hydrodynamic model, did you measure the mean free path?
Oh yeah, yeah, that's the big thing. Yeah, so we are working on it. I don't know what to say. We are working on it. What I can say is it's very complicated. But yeah, we have some very nice results.
Well, so I guess along similar lines as Tjeerd, you could think maybe it's not, you have to now force down the emissivity, or maybe it's some other effect that is actually coming up. So if you're missing...
It's not missed clumping, that much I can tell you.
Sorry?
It's not missed subgrid clumping. The resolution is good enough to uncover both the self-shielding disk density and the pressure smoothing scale.
And the circumgalactic material?
So what happens is if you add subgrid clumping, then it will just scale this up. Unless you add a redshift dependent subgrid clumping, but then it's not clear how to make that. If subgrid clumping is not unconstrained, you have to be on the log normal distribution function of gas densities.
Yeah, but I was thinking more about the collapsed structure. So the outskirts of galaxies that you're maybe not resolving so well, which...
Yeah, so I think, I'll have to think about that. I don't know. There is a lot to discuss around those issues. As you highlighted very well in your talks, we are trying to wrap our heads around it ourselves.
Thanks, Girish. So let's thank the speaker. Now we have a series of lightning talks. All of them are 5 minutes and there will be no questions. So first speaker is Anirban Chakrabarti.
Hi, I am Anirban and I will be describing my poster titled Modeling the Ionizing Sources During the Epoch of Reionization. So our current belief is that the stars in galaxies were the dominant contributors towards the ionizing photons responsible for reionizing our universe. However, we don't understand their exact contribution that well enough. And therefore, we would like to investigate that, and one of the possible ways to answer questions regarding the reionization sources is by looking at their large-scale properties. Under the framework of the hierarchical structure formation model, dark matter forms the basic skeleton on which these galaxies form, evolve, and grow. And with present and future large galaxy surveys like the HST, Subaru, and the recently launched JWST and developments in dark matter simulations, this galaxy halo connection can be exploited to build a model of high redshift galaxies and investigate their role in the process. Here we have done the same for high redshift Lyman break galaxies and would like to investigate the prospects of galaxy 21 centimeter cross correlations in the future. I would briefly describe the methodology that we follow. So we have galaxy UV luminosity functions available from galaxy surveys, and we use an empirical approach of abundance matching in this luminosity function to a halo mass function of our choice to arrive at a mapping that connects the halo mass to the UV magnitude of the galaxy that resides in it. However, at any given time, all galaxies out there will not be visible in the UV due to stochasticity in star formation and radiative transfer processes, and therefore we weigh this abundance matching by a duty cycle parameter, in which we only populate the recently formed halos parameterized by this delta T time interval with UV bright galaxies. And then we move and populate halos from a n-body simulation and obeying this MH-MUV mapping to get build galaxy catalogs. However, the way this process abundance matching technique works is that for every value of delta T weighing the duty cycle, the luminosity function is reproduced exactly. However, and when we vary the delta T parameter, we find that for a given UV magnitude, the mapping shifts to lower and lower values of halo mass when we decrease this delta T parameter. And therefore, in each model, although the abundances are matched, for every value of delta T, the spatial distribution of the galaxies will be different depending on the fiducial value of delta T that we choose. And therefore, to constrain the abundances and the spatial distributions, we compute the 2-point correlation function from our galaxy catalogs and compare with the data. That is the basic empirical framework that we follow. As I said, here is the luminosity function from our catalogs, and it is exactly reproduced by construction of the calibrated MH-MUV relations. However, when we compute the galaxy clustering in luminosity dependent bins of galaxies, the brighter and the fainter subsamples, we find that there is, and compare with the observed data, we find that there is a preference for smaller values of delta T to reproduce the observed clustering pattern. And this probably reflects the fact that star formation in these high redshift galaxies during the UR was very bursty in character. So the take-home message from our work at present is that we have been able to build, using empirical techniques, a catalog that models the abundances and clustering of high redshift galaxies, and we are presently working on improving this framework by implementing merger tree algorithms and also redshift evolution and patterns for the galaxies obtained through photometric surveys. Thank you.
Yeah, thanks Anirban. Our next speaker is Aritra Kumar Gaun.
Hi everyone, I'm Arithro and I will be speaking about the secondary E and B mode polarization of the CMB from the epoch of reionization. So let's begin. So this is like a summary slide of my talk. On the left hand side you can see the key points of my talk. So during reionization there are a lot of free electrons which has some peculiar velocity, and this E and B mode signal is dependent on the transverse peculiar velocity of these free electrons. Secondly, the spectral shape of this signal has a Y-type distortion in it, and which will be important. I will be speaking about it a bit later. What we showed is that this E and B mode path spectrum, these are sensitive to the parameters of reionization. Especially it depends on how fast the reionization happens. It provides a way to beat the cosmic variance of the primary CMB anisotropies, and in principle you can measure it as precisely as the primary anisotropies. And secondly, lastly, it can be an independent probe of different cosmological parameters. On the right hand side you can see the path spectrum of the E and B modes. The E modes are this red line here, and the B modes are this blue line here. This is done for a homogeneous model of reionization, a symmetric homogeneous model of reionization. And you can see that with this sensitivity curve of Prism and Pico, that this is still a bit futuristic when it comes to measurement. Secondly, what we showed that this polarization signal is dependent, is sensitive to both the total optical depth of reionization and also to the width of the reionization. So it depends on how fast the reionization happens. On the left hand side, you can see that varying the central redshift of, so varying the width of the reionization, you can see if you increase the width, there can be more cancellations of different kind of polarization direction along your line of sight, which kind of decreases your overall amplitude of the power spectrum. So you can see that the faster the reionization happens, the smaller the width, the greater is the signal amplitude. On the right hand side, you can see that if we vary the central redshift of reionization, the total optical depth increases, which in turn increases the power spectrum. So moving on, we started including patchiness to our reionization model, and doing so we had to shift to simulations because it was very cumbersome to do analytically. So on the right hand side, you can see the Stokes parameter, Q Stokes parameter in the case of non-patchy reionization, and on the right hand side you can see the same for the patchy reionization. It's clear that this picture is more grainier than this. So what happens is that patchy reionization incorporates small scale fluctuation in your sky map, and which is not present here, and also the overall contrast increases a bit. So the amplitude also increases a bit, which is very apparent from the power spectrum. If you see, in case of this homogeneous reionization, the E and B modes are smaller than the case of patchy reionization models. And in these dotted lines, you can see our prediction from perturbation theory in case of a homogeneous case, which very well matches with the simulations. So lastly, I want to speak about this Y-type distortion in our spectral signature, which means that if you see that there are it happens because at different line of sight, you have black bodies with different temperatures, and due to Thomson scattering they mix, and the resultant spectrum has a black body spectrum in it and also a Y-type distortion. And basically due to this Y-type distortion, it can be measured at precisely as the primary signals, because you can escape the cosmic variance limit, because you can in principle measure, it has a different spectrum and you can actually measure it precisely with different component separation techniques. So finally, I will leave you with the concluding remarks. It is essential to mention that this signal exists in the standard cosmological model. You don't have to incorporate any beyond standard cosmological model to find this signal. Good enough sensitive probe with enough kind of frequency channels will be able to observe this in future. And what we show again is that it is sensitive to the reionization optical depth and also the reionization history. And it is free from the cosmic variance of the primary signals and also the cosmic variance of the lensing B modes. And also, as you have seen, there is a black body part of it, and which has an amplitude which is like 4 times greater than the Y-type signal. So that will also be act as a foreground for future primordial B mode experiments. So if you want to know more, you can come to my poster, and thank you. That's all.
Thanks, Aritra. Our next speaker is Barun Maiti.
So, good afternoon. So, I'll be talking about my poster on exploring cosmic reionization with an efficient script. So, I'd like to start with a broad motivation behind the work. We have learned a lot about this picture, which basically gives the evolution history of the universe, and we know that reionization is still one of the least understood phases in the evolution history of the universe. And there are a lot of open questions like the precise reionization end or the start and the duration of reionization, and we don't even know the nature of ionizing sources too. But the advantage we have that there are a handful of observational probes spanning across a wide wavelength ranges. So some of them which I have mentioned here, and we have heard about this in the earlier talks also. So one would like to include all these observational probes together, if possible, to constrain the reionization physics, and that is the main goal. And in this particular work, we would also like to check the prospects of thermal history of the IGM as a treasure of reionization. And lastly, we need efficient models in order to extract physics from these different observational probes. And there, these semi-numerical models comes into the picture, which are reasonably accurate and fast enough to do the parameter space explorations. And so our model called script is basically a semi-numerical model. The acronym stands as semi-numerical code for reionization with photon conservation. So what is photon conservation? So the standard semi-numerical models, which are based on excursion set, seems to have the issue of photon number non-conservation. So all the models which we have heard since the morning are all based on this excursion set based approach. And to visualize what is photon number non-conservation, so I have shown these plots, that the left panel is the photon number non-conserved case and the right panel is the photon number conserved case. So the ionizing fronts are propagating from the two ionizing sources. It's fine until this ionizing bubble starts to overlap with each other. When they start to overlap with each other, it seems that there are some unphysical structures which are coming out. It should not come out because there are not enough number of ionizing photons to ionize this kind of kinks-like structures, but it is coming out, and that's the consequence of photon number non-conservation. And this problem is solved using this semi-numerical photon conserving code called script. And the other aspect is that it provides a large-scale convergence of the power spectra, which is going to be a probe in the near future. And using this model, we have basically studied the aspects of the effect of defined physical processes which are important during reionization. The first one is the thermal evolution of the IgM. So the ionizing photons not only ionize the medium, it also heats up the medium. So we need to take into account for that. We also model the inhomogeneous recombination. That is also basically an opposite effect of reionization. And lastly, the radiative feedback, it is a consequence of reionization heating. So as the gases are heated up, it will not be the halos which have relatively shallower potential will not be able to confine this heated up gas. So there will be a less star formation, which will in turn affect the reionization process. And with this, we can also try to constrain the reionization parameters. So I have shown a typical example of that. A new aspect of this work is that we can use the low density IgM temperature estimates as a potential probe of reionization, and it seems that this low density IgM temperature can reasonably improve the constraints on the reionization parameters, which is a kind of new aspect in this study. And lastly, we also check the prospects of 21 centimeter power spectra as a treasure of reionization. So the idea is that we generate the mock power spectra from our model, and we include the futuristic noise, assuming 1000 hours of SK observation or so. And we check if we can recover the input parameters which are going in the mocks. And it seems that with two different resolutions, we are getting unbiased estimates of the input parameters as well as the ionization state of the universe. So this is quite good. And to know more, you can go to the my poster, which is outside there. I would like to stop here.
Thanks, Gaurav. The next speaker is Chandrasekhar Murmu.
So thanks to the organizers for having me here. So I'm Chandrasekhar from IIT Indore, and I'll be talking about probing the astrophysical scatter from the year with 21 centimeter auto bispectrum. So this is the era in the cosmic evolutionary history where the first stars and galaxies emerged, and they changed the state of the universe from being neutral to ionized. But this is not as well studied as the cosmic microwave background or the galaxy redshift surveys, which probe the local universe on the largest possible scales. So the broader question that we pose is how to probe this UR universe. So one of the proposed ways is that we try to follow the redshifted 21 centimeter signal, so which is a radiation which is emitted from the neutral IgM, and which we expect to be effectively used to track the evolution of the IgM through the cosmic time. And so these are some of the examples of the interferometers which we expect to do to detect this signal. For example, the LOFAR, the HERA, and the upcoming square kilometer array, which we expect to be able to make tomographic images with these signal fluctuations. So here we'll be discussing about the bispectrum, which is the a higher order statistic in the Fourier space. So if we have these Fourier fluctuations, then what we can do is that we can correlate them in the Fourier domain in 3 length scales. So if we have these 3 k vectors and we define the angle theta as the angle between the k1 and k2 arms, and we follow this prescription where k1 is greater than k2, which is greater than k3, and cos theta and k2 and over k1 ratio lies between this range, then in principle we can identify all the unique triangle modes which is needed to estimate the bispectrum. So because we always need these k1 vectors to form a closed triangle so that we can estimate this bispectrum. So then we take the ensemble average of this product of the Fourier fluctuations for these 3 different k modes, and we normalize it with the number of modes and the volume, this which gives us the bispectrum estimator. So we try to use this estimator to see whether we can actually probe the signatures of astrophysical scatter that might be present in the 21 centimeter signal. So what we expect is that the star formation rate, which actually drives the production of the ionizing photons, we expect that it will not be perfectly correlated to the host halo mass. That means for a given halo mass, we will not have a single value of star formation rate, but rather we'll have a large spread in the star formation rate, which will usually follow a log normal scatter. And we expect that if it leaves any kind of non-Gaussian signatures in our 21 centimeter signal, then whether the bispectrum estimator can capture this. So then this ionizing photon emission rate is proportional to the star formation rate following a log normal scatter, and we generate 21 centimeter maps using which has log normal scatter in present, and we try to see whether bispectrum can actually probe this. So in our simulation, we have generated almost 100 realizations of this scatter, and average them over to see whether this impact is even statistically significant enough. So we have done this for at redshift 4, where universe is almost 50% ionized, and we see that only for this k1 mode, which gives the size of the bispectrum triangle, and that is at k1 0.53, we see that we have some significant impact due to the scatter, but whereas in other cases, the impact of bispectrum is almost, the impact of scatter on the bispectrum is almost washed away, which we expect that it might be due to the presence of ionized bubbles mostly. And also that in this case, we do not see that the impact is very statistically significant, so this almost goes up to 1.5 but not beyond. So the next thing would be to look at the case where we actually have a higher neutral fraction where we do not have any ionized bubbles, and we try to see that whether in this case we actually see some impact which might be captured by bispectrum, and whether in that case it might be more statistically significant. So please feel free to check out the work on poster FC9, and thanks for your time.
Thanks. Our last speaker for the day is Suman Pramanik.
Good afternoon. So I am a PhD student at the Department of Physics, IIT Kharagpur, and this work has been done in collaboration with Rajesh Mandal and Somnath Bharadwaj. So light cone effect should be properly incorporated in Epoch of Reionization simulation, as the mean neutral fraction statistical properties H1 fluctuation changes rapidly during the Epoch of Reionization. We have worked with this YOLO region, so which is in between redshift 7 to redshift 8, where the mean neutral fraction changes from 0.1 to 0.49. The box size is 286.7 megaparsec cube, and which extends from redshift 7.03 to 7.91. So to simulate a light cone box, we need to first have the snapshots of your simulation within the bandwidth of the observation. We need snapshots. So from those snapshots, we take particle to fill the light cone box. Now the number of snapshot what we have to choose, that by now is ad hoc. So we don't know that if we choose some number of snapshot, what will be the accuracy of our light cone simulation. So I have addressed that problem. So I use different number of snapshots to create a light cone simulation within the same redshift range. And I have checked what is the signature in its statistics like power spectrum and multi-frequency angular power spectrum. So here we can see as we decrease the number of snapshots, the overall power spectrum decreases and the error increases with respect to the first plot here, that is light cone with 26 snapshots. However, power spectrum is not a good statistics for a light cone simulation as it assumes ergodicity. So here I am showing the multi-frequency angular power spectrum for different light cone simulations, where you can see with respect to the first panel, these are the errors of the light cone simulation, and we can see the error increases as we decrease the number of snapshots. And also this kind of discontinuities are appearing at the stitching boundaries of the coeval snapshots, which can be better seen when we actually plot the CL nu, that is the diagonal element of map. So we see that as we decrease the number of snapshots, this step-like behavior in CL nu is appearing, and they are basically appearing due to abrupt change in neutral fraction at the stitching boundaries. So we can relate the evolution of neutral fraction with the diagonal part of maps. These are the errors of CL nu with respect to the first row here. So we can see the error increases as we decrease the number of snapshots, which is obvious. So the average error follows a power law. We find that the exponent of the power law is -1, which gives us this relation that average percentage error in a light cone simulation is inversely proportional to the number of snapshots used. Similar result can be obtained from power spectrum, but for small scales. However, at large scale, these two modes are large scale modes. We can see that power spectrum gives wrong result because at large scale light cone effect is prominent, and in the presence of light cone effect, power spectrum gives wrong results. So how can we mitigate this error in a light cone simulation? How can we create a light cone simulation with great accuracy and not doing much computation, because computing those in between, computing the snapshots takes time and RAM storage power. So the idea is here we introduce a new technique to mitigate this error. The idea is let's say we have some number of snapshots, so we will generate some in between snapshots, and for those in between snapshots we will skip the steps, some steps of the reionization simulation, that is the dark matter distribution. We will skip the dark matter distribution step and the halo finder step. So halo finder step is slow and dark matter n-body takes memory. So we will skip them. The idea is at any in-between position, we will interpolate the dark matter field and halo field after gridding them, and then we will use those interpolated dark matter field and halo field to calculate the 21 centimeter brightness temperature. So in this way, we can increase the number of snapshots. However, these in-between snapshots are not accurate, as you can infer, but this increases the number of snapshots, and let's see what we can gain in a light cone simulation. So now this red line, you can see this is after applying this technique, this mitigation technique. So the 10% error reduces within 1%, and all the other errors also reduces within 1% limit. Okay. However, for 2 snapshots only, we are able to reduce the error within 2%. So this is a very effective method to simulate the light cone. The average error can be seen in this table at every length scale, angular length scale. We can see the error reduces drastically after doing this, and most of the error are less than 1%. Here it is less than 2%. So this is the summary. So the error can be calculated using this formula, error in light cone simulation, and then error can be reduced following the mitigation technique which I have discussed. And this is a very fast and accurate technique which is effective to generate multiple light cone realizations, which is good for doing statistics. Thank you. Visit my poster at FC10.
Let's thank all the speakers for this session.